Skill Development and Entrepreneurship, Government of India, Shri Dharmendra Pradhan. ISER Berhampur seamlessly integrates education with research, offering BSMS dual degree, integrated PhD programs and post-doctoral research training in diverse fields. With a current strength of 932 students and 87 faculty and non-teaching staff, the institute is equipped with state-of-the-art facilities including smart classrooms, research laboratories, hostels, health centers and a sports complex. Having successfully graduated 3 batches of BSMS students, ISER Berhampur aims to foster a creative academic environment, promoting diversity, gender equality and balance.
It's a very joyous occasion. The faculty, staff and students have this wonderful moment to hold on to for the rest of their lives. ISER Berhampur is going great strides in various branches, primarily in science and mathematics, and in future we also hope to open computer science and humanities.
Beyond national boundaries, the institute attracts international collaboration, hosting young scientists from foreign universities and encouraging student researchers to explore cutting-edge scientific fields. 15 out of 29 buildings valued at 263.79 crore rupees are now operational, propelling ISER Berhampur towards its envisioned future, a beacon of knowledge, innovation and global collaboration for the betterment of the nation, humanity and the planet. सिल्क सिटी के नाम से सुप्रसिद्ध बरहमपुर शिक्षा के क्षेत्र में प्रमुख केंद्र के रूप में अपनी पहचान बनाने में सफल हुआ। 7 भारतीय विज्ञान शिक्षा और अनुसंधान संस्थानों आइसर के बीच आइसर बरहमपुर युवाओं की पहली पसंद बन रहा है।
Good morning, everyone. A very warm welcome to the 2-day Science Outreach Seminar second series organized by ISER Berhampur. This event is designed to bridge the gap between scientific knowledge and daily life, inspiring the students of Odisha to explore the wonder of science and its practical application.
सुप्रभात समस्तଙ୍କୁ आइसर बरहमपुर द्वारा आयोजित यही 2 दिनिया संस्करण साइंस आउटरीच प्रोग्राम को आपण मानको स्वागत। यही कार्यक्रम 2टी लक्ष्य, प्रथम वैज्ञानिक ज्ञान और दैनंदिन जीवन मध्य थिबा व्यवधान को दूर करवा एवं द्वितीय हला ओडिसा छात्र छात्री माननको विज्ञानर चमत्कारता एवं एहार व्यवहारिक प्रयोग गुडी को अनुसंधान करिवारे सम्मुख करवा।
Our mission is to make science accessible and relatable, sparking curiosity and encouraging young minds to develop a deeper understanding of the world around them.
आमे आइसर बरहमपुर प्रतिबद्ध अछु विज्ञानर जिज्ञासा वृद्धि को एवं युवमन भितर एहार गभीर बुझामणा को उत्साहित करिया पई।
Over the next 2 days, you will hear the eminent scientists from across India who will share their knowledge and discuss cutting-edge advancement in various fields of science.
एही सेमिनार समय रे सारा भारत रो आसीथवा प्रख्यात विज्ञानी माननको वैज्ञानिक माननको तांकर विज्ञान प्रति अंतर्दृष्टि शेयर करिया पई आमे अनुरोध करूछु एवं विभिन्न वैज्ञानिक क्षेत्र रे सद्यतम उन्नति विषय रे आलोचना करिया पई अनुरोध करूछु।
To make the experience even more engaging, Each session will conclude with an interactive segment, giving students the opportunity to engage directly with the speakers. 5 students demonstrating exceptional participation during each session will be recognized with special gift.
प्रत्येक अधिवेशन शेषରେ ଆପଣମାନେ ଏକ ସିଧାସଳଖ ଆଲୋଚନା କରିବା ପାଇଁ ସୁଯୋଗ ପାଇବେ ଆମର ଏସ୍ଟିମ୍ ସ୍ପିକରମାନଙ୍କ ସହିତ ଏବଂ ମନେ ରଖିବେ ସିଲେକ୍ଟିଭ୍ 5 ଜଣ ଛାତ୍ରଛାତ୍ରୀଙ୍କୁ ସେମାନଙ୍କର ଉତ୍ସାହ ପାଇଁ ସ୍ୱୀକୃତି ସ୍ୱରୂପ ସ୍ୱତନ୍ତ୍ର ଉପହାର ପ୍ରଦାନ କରାଯିବ।
A feedback form is included in your event kit. Kindly, at the end of the program, fill it out and submit it to receive your participation certificate.
ଦୟାକରି କାର୍ଯ୍ୟକ୍ରମ ଶେଷରେ ପ୍ରମାଣପତ୍ର ସଂଗ୍ରହ କରିବା ସମୟରେ ଆପଣଙ୍କ ଇଭେଣ୍ଟ ବ୍ୟାଗ୍ରେ ଥିବା ଫିଡବ୍ୟାକ୍ ଫର୍ମକୁ ପୂରଣ କରିବେ ଏବଂ ଦାଖଲ କରିବେ।
We hope this event provide you with inspiring and enriching experience. Let us embark on this exciting journey together.
ଆଶା କରୁଛୁ ସେମିନାରରେ ଆପଣଙ୍କର ଏକ ପ୍ରେରଣାଦାୟକ ଏବଂ ସମୃଦ୍ଧ ଅଭିଜ୍ଞତା ରହିବ। ତାହେଲେ ଆଉ ଡେରି କାହିଁକି ଚାଲନ୍ତୁ ଏକାଠି ଏହି ଅନୁସନ୍ଧାନ ଏବଂ ଆବିଷ୍କାରର ଯାତ୍ରାର ଶୁଭାରମ୍ଭ କରିବା। ଥ୍ୟାଙ୍କ ୟୁ।
I now invite our chief guest, Ms. Madhumita, our director, Professor Ashok Ganguly, and our organizing secretary, Dr. Nihar Patra, to come forward for the ceremonial lamp lighting. May I kindly request Ms. Madhumita, Professor Ganguly, and Dr. Patra to please take their seats on stage. Thank you. I now request our director, Professor Ganguly, to felicitate our chief guest, Ms. Madhumita, with a bouquet, shawl, and a memento.
Next, I'd like to invite Dr. Nihar Patra to present a bouquet and shawl to Professor Ganguly.
I request our director to present. I now request our director to present a bouquet, shawl, and memento to Dr. Patra. Thank you all for the warm gesture. To deliver the welcome address, I now invite our organizing secretary of the event, Dr. Nihar Patra. Dr. Patra, currently a librarian at ISER Berhampur, has a distinguished career spanning over 25 years. He has been instrumental in establishing modern libraries in many institutes across India and actively promoting scientific outreach. So, Dr. Patra.
Hello. So, namaskar, good morning, and ଶୁଭ ସକାଳ। ମୁଁ ଏହି ସମାରୋହରେ ଆୟୋଜିତ ସମିତିର ଆୟୋଜନକ ସଚିବ ଭାବେ ଆପଣମାନଙ୍କ ସମ୍ମୁଖରେ ଦଣ୍ଡାୟମାନ ହୋଇଥିବାରୁ ନିଜକୁ ଗର୍ବିତ ମନେ କରୁଛି। ଏହି ଦୁଇଦିନିଆ ସମ୍ମିଳନୀର ମୂଳ ଉଦ୍ଦେଶ୍ୟ ସମୁଦାୟ ବା ଗୋଷ୍ଠୀ ମଧ୍ୟରେ ବିଜ୍ଞାନ, ଓଡ଼ିଶାରେ ବିଜ୍ଞାନର ଲୋକପ୍ରିୟତାର ଅଗ୍ରଗତି। ଆୟୋଜକ ସଚିବ ଭାବରେ ମୁଁ ଆପଣମାନଙ୍କୁ ସମସ୍ତଙ୍କୁ ଏହି ଆୟୋଜିତ ସମ୍ମିଳନୀରେ ସହୃଦୟରେ ସ୍ୱାଗତ ଜଣାଉଛି। Let me begin by extending a heartfelt welcome to our esteemed chief guest, Ms. Madhumita IS 2020 batch, CDO cum Executive Officer, Jilla Parishad, Ganjam. Despite her busy schedule, she graciously accepted our invitations to join this event, and we are truly honored by her presence. I warmly welcome Professor Ashok Ganguly, Director, IJR Barampur, and Chairman of this seminar, who has been cornerstone of this event. I also extend a warm welcome to our distinguished scientists and invited speakers. Your valuable contributions, expertise enrich these seminars, and we eagerly look forward to learning from your insights. Our speakers are Professor Uday Maitreya, Department of Material Science, Emeritus Professor IISc Bangalore, Professor Rajesh Prasad, Department of Material Science Engineering, IIT Delhi, Professor P.S. Anil Kumar, Department of Physics, IISc Bangalore, Professor Bhaskar Kansari, Department of Physics, IIT Delhi, Professors Pranit K. Chaudhary, Department of Chemistry, IIT Delhi, Professor Colin Paul, Department of Computer Science and Engineering, IIT Delhi, Professor N.G. Prasad, Department of Biological Science, IJRS Mohali, Professor Pritiranjan Panda, Department of Computer Science and Engineering, IIT Delhi, Professor Samita Maitra, BMS College of Engineering, Bangalore, Professor Gitanjali Das, Vice Chancellor, Berhampur University, who is also our invited speaker, and our esteemed director, Professor Ashok Ganguly. A special welcome goes to our registrars, Sri Pradeep Rai ji, and our dedicated member of our organizing committee, Dr. Ritabrata Sengupta, Dr. Vyas Akhonde, Dr. Rahul Sharma, Dr. Samrita Rai, Dr. Tushar Chakravarti, Dr. Prabhat Parida, Dr. B.R. Selby, Mr. Snehashish Das. Your unwavering efforts have been instrumental in making this event possible. So विशेष भावरे एठारे उपस्थित विभिन्न विद्यालयर शिक्षक शिक्षिका छात्र छात्री गण एवं विज्ञान प्रेमी गवेषणा मानंकु मोर आंतरिक शुभेच्छा आपण मानकर एही सम्मिलन रे उपस्थित आपण मानकर विज्ञान प्रति समर्पण और गवेषणा प्रति उत्कृष्टता को संपूर्ण भावे अभिव्यक्त करुछि एही सभा को आगो को अग्रसर करने आगु आसतु आम्भे माने समस्ते आम देशर वैज्ञानिक एवं विज्ञानर ऐतिह्य को किछि मुहूर्त पर स्मरण करवा प्राचीन भारत में आर्यभट्ट भली गणितज्ञ और खगोल विज्ञान बासस्थान जे कि जीरो बा शून्य आविष्कार करते यही भारत मध्य भास्कर द्वितीय चरक सुश्रुत बासस्थान भास्कर जे कि गणित और कैलकुलस प्रवर्तक थिले अन्यपटे चरक और सुश्रुत थिले आयुर्वेदर जनक अन्यपटे डॉक्टर सीवी रमन को भी बा किए न जाने भारत में रही भारत में गवेषणा करी नोबेल पुरस्कार प्राप्त करिथिबा एकक वैज्ञानिक से तांकु मोर कोटि कोटि सम्मान से कहिथिले द जॉय ऑफ साइंटिफिक डिस्कवरी कम्स नॉट फ्रॉम फाइंडिंग आंसर बट फ्रॉम आस्किंग राइट क्वेश्चंस जहार अक्षरिक ओडिया माने हेला वैज्ञानिक आविष्कार बा उद्भावनर आनंद उत्तर पाइबा को नुहे बरं सठिक प्रश्न पचारिबारु आसे मोर मानिबार अछि जे आजिर स्थान होची सही स्थान जोठी आपण माने सठिक लोक मानकु पाइबे जो माने आपणक प्रश्नर उत्तर देबे So this seminar is dedicated for advancing the cause of scientific popularization in Odisha. Our objective is to bridge the gap between the scientific research and community needs, promote scientific literacy by encouraging critical thinking and inquiry, develop innovative strategy for science communications and outreach, foster collaborations among scientists, educators, policymakers, and communities, ensure equitable access to scientific resources for underserved populations. I am happy to inform that IIR Barampur conducted a similar program last year involving students, teachers, mostly from the government and other private schools. Its grand success has been motivated us to organize these outreach seminars, which aims to promote science awareness among students and citizens. This initiative aligns with the Government of India Viksit Bharat at 2047's visions. Over the next 2 days, this platform will host meaningful dialogues, live demonstrations, and interactive sessions. We have extended free invitation to 330 schools, students, and their teachers from class 9 to 12 in the vicinity of Barampur. Among them, over 50% are girls, many from scheduled tribes and scheduled caste backgrounds. This efforts also resonates with the 11th International Day of Women and Girls in Science, which is going to be observed on February 11th. We are privileged to have with us our esteemed director, Professor Ashok Ganguly, whose unparalleled dedication to science outreach is the guiding light for all of us. Having conducted over 400 science outreach programs, our director exemplifies the transformative power of bringing science to community. In Odisha, IIR Barampur has conducted many outreach programs during his period. I would venture to say Professor Ganguly started outreach activities in IIR Barampur. In my opinion, science outreach for him is not merely a task but a lifeblood, which is driving a mission to benefit the nation through dissemination of knowledge and the cultivation of scientific temper. सम्मिलन रे अंशग्रहण करिथिबा समस्तनको मु आशा करूछि सेमाने आमंत्रित प्रसिद्ध वक्ता और विशेषज्ञ मानक सह आलोचना विलोचना करी एही सम्मिलन रो उद्देश्य को पूर्ण करिबा सह ओडिसार विज्ञान प्रचार और प्रसार को अग्रसर करिबा हेबे तत्सहित आम्भे माने समस्ते एकत्रित होई भारतर विज्ञान और अग्रगति को प्राधान्य देई विश्व स्तर रे पहुंचाइबार प्रण नेबा उचित. थैंक यू. जय हिंद.
I now request our director, Professor Ganguly, to deliver the welcome address. Professor Ganguly is a global renowned expert in nanotechnology, specialized in designing nanomaterials for energy conversion and superconductivity. His illustrious career includes serving as Deputy Director of IIT Delhi and Founding Director of Institute of Nanoscience and Technology, Mohali. Professor Ganguly's unwavering commitment to promoting science among underprivileged communities has led to numerous impactful outreach programs, including this very one. So, welcome.
Thank you, Dr. Natasha. Very good morning to all. My heartfelt thanks to Ms. Madhumita, IAS, Chief Development Officer, Zilla Parishad, Ganjam District, and just came to know she hails from Haryana, has studied in Delhi, and she has served in Kandamal, and now she is serving in Ganjam, and all girls should see that how girls can rise to significant positions in different areas of administration and, of course, as teachers, nurses, doctors, engineers. So Mrs. Madhumita should be a role model for all of you, and that's why we thought of inviting her as a chief guest for today's function. Thank you, Ms. Madhumita, for accepting the thank you. So, IISER Berhampur has been functioning from a campus which was in the city. It was a transit campus. This is one of the large meetings that we are having in this campus. This hall is being used first time in this large manner. We have done some like TEDx talk here earlier, but a real classroom teaching we have not yet started. As you know that we are putting up the audio visual things. What is right now is all rented stuff, but our real audio visual is all inbuilt, which is getting started. So you are one of the first students to sit in these benches to hear lectures. So I all congratulate you for doing this opening for IISER Berhampur. It's a great feeling. See, this is the only institute of national importance in southern Odisha. So you must think that the government of India has put in a lot of money and a lot of people who are very well trained so that their knowledge and the infrastructure, the benefits percolate to this region, to other institutions, other universities, colleges, and school. And we can give you some knowledge transfer from people who have worked in science. This meeting is for science, but not only science, mathematics, and computer science, which we have started, and also humanities, which we are going to start. It should percolate to all of you. And we intend to bring top of the line speakers, practitioners of the subject, those who are doing research at the highest level. So where is science taking us, science and technology? You see, today, the kind of screen that you are using was not being used 10 years back. This was not common screen in most places. But now it is very common even in this remote part of Ganjam district. You are right on the Bay of Bengal. Bay of Bengal is hardly 400 meters or 300 meters from. Actually, this building is closest to Bay of Bengal in our campus. If you just walk past this, you have a small forest, it's a cashew nut groves, and you are into the Bay of Bengal. And science and technology you are learning here in one of the remote places to see that advancement in technology should percolate to every corner of our country, right? So today, as you know, where has technology gone? You are hearing of cryptography, right? All of you know, because we do so many online transactions. how to protect these things. It's all technology, right? And you use so many sensors. See, we also have a lot of sensors in our cars, our rooms, buildings have sensors. Here, many of our buildings have sensors. Sensors activate the lights. Sensors activate doors opening. Many of the rooms are like that. Some special rooms have other kind of sensors which can monitor the air, because we need to monitor the particles in the air for doing certain experiments. So we need so many sensors. Each sensor can find out some specific thing. How much carbon dioxide is there? How much oxygen is there? Right? You see dust particles in this air. What is the size of these dust particles? Some sensor can measure 2.5 micron. This is the average size of a dust particle. Sometimes you can see dust particle when light comes. Those are approximately 2 micron dust particle, 2.5 micron. But you can see finer particles also. You know how much your eye can see? Your eye normally can see of that limit. That is why 2.5 micron or 3 micron. Right? That is the size actually the eye can see. Below that, we need microscopes and all that. There's a subject of nanotechnology. So science has gone beyond. We can do surgery today inside the body without doing incision. Means there is a small probe going in. The same probe will see inside and make the pictures come on the computer, and then the doctor will use the same probe. Inside it will go and open up, and 4 blades will come out. And you can control those blades using a computer. This is not today's technology I'm talking. I got surgery, gallbladder surgery several years back using that technology. But there can be much more sophisticated technology, like where are the cancer cells, where you can locate it or not. This is in medicine. So science has to help society. How can science help society? By finding out if you have any medical problem, right? Or there is a virus, like we had COVID virus, how to prevent it, wearing masks, what kind of mask. That is all technology. What kind of mask you can wear. For certain kind of things, you need different masks. For example, the coal miners they need a different mask. They have to inhale, right? So technology today is growing by leaps and bounds, right? Not only your mobile phone. Your mobile phone is one thing which is really reflecting all kinds of technology. It has a technology, how signals are being transmitted between satellites. There is technology, how calculations are being done for global positioning. You can do Google Maps, how fast it tells you, how fast this rapid communication is happening. How does it do that? There's a lot of mathematics in that. All of you study mathematics. There is a lot of mathematics in all that. So technology in all our aspects, whether the clothes we wear, many of our soldiers are wearing clothes which have antibacterial things inbuilt, right? There are clothes which are made for space suits, right? Which can stand for minus 80 degrees, minus 100 degrees. Your clothes and all will all crumble. So technology is everywhere. In audio, video, where the chairs you are sitting, you can make comfortable chairs which will change, which are ergonomically designed. Depending on your body, you can design a chair. The chair will take the shape of your body, of your vertebral column. There are so many kind of technologies, and all of that technology starts at the fundamentals of mathematics, or what we call physics, chemistry, biology. But as you grow older, biology itself will have so many branches, right? From biological sciences, you can have so many things. Evolution is a part of biology. There's something called paleontology. How many of you have heard paleontology? Okay, 2 of you have heard. Biology, which you can see in the fossils, in the stones. I think, I'm not an expert. I think that is called paleobiology or paleontology. What we see, that is, how do we know that 3,000 years back which plant existed, which animal existed? There are certain animals which have gone extinct, right? So they were there. How will we know? We'll study rocks and see the imprint of those things, some imprint of a tooth or imprint of a vertebral column From that, scientists then find out, and then they do carbon 14 dating. From that, they find out the life of that rock. From that, they know that this animal was alive, and I think that is how they work. I am not a paleobiologist. But whatever little bit we learned in biology and all when I was in school and college, that is what we assimilate. And slowly you grow up and you become a specialist in one subject. Okay? But all these fundamentals are required. So whatever you learn in school is very important. If those things are not good, then later on you cannot be a very smart person. Even a doctor needs to know some physics. He needs to know some mathematics, right? It's not only biology. But what level of statistics he will know will help him find out whether his doctor is looking at some test. Okay, he's going to predict that people should take some precaution against some virus. There are a lot of statistics involved, I think. So this is called biostatistics, okay? Lot of things like that. Studying the effect of lung of say 10,000 people, they find out something and then they can predict something. So these statistics, mathematics, as I said, in finding out distance between, by the way, Odisha is well known for whom? One name, very famous. Who? Huh? हाँ नहीं बच्चों को बोलना है. Students have to tell. Patani Samanta. What did he do? All of you know, na? He measured something with a stick. Right? So all of you should know. You are from Odisha. You should know about him. Very famous. Huh? Neat. Patani Samanta was a very famous man in Odisha. Not today, several years ago. And what did he do? Huh? Using a stick, he measured the distance in the sun and many other things like that using shadows. So you must read about him, and I think he's one of the most famous persons of Odisha. So I want to tell you that you are going to hear a lot of things on physics, chemistry, which have something to do in your class, but will be exciting. See, many things we study in class, in books, which are very old, but they have some basis you need to know. But remember another thing when you are studying in class, that even today something new is being found in chemistry, in physics, in biology. So that is what you should remember, that although I am studying something which is 50 years old, 100 years old in my book, but even today something new is happening. That you will come to know when you are going to post-graduation in that subject or doing PhD. But every day something new thing is happening in all subjects. In some lab in the world, some new thing is being created, which you will not know now because you have to read the fundamentals. But if you are exposed to some of these new things once in a while, like these outreach programs, then your mind will be activated that so many new things can be done. You have to look forward to solving some big problems. So that is what, as a young person, you have to find out two things: what interests you, and second, what is a big challenge in this world. And you have next 40 years to work on that, for 50 years. So you should start thinking, what is the area I like, and what is a big challenge in that area that I can do, right? And so there are, today I must tell you, in India there are so many institutions with so many facilities. If you are interested, you can always see the top of the line, what you can see in any American university or any Japanese university, any South Korean university. These are the top countries in the world, say Switzerland, Germany, who are doing technology. But we have similar labs, maybe number is less, but we have similar labs in our country. For the large population that we have, that kind of facilities, the numbers are little less, but there are facilities which are at the state of the art that the government has invested in many institutions of our country. So if you have interest, you can always go and see. Odisha itself, there are so many institutes in near Bhubaneswar. You can go to NICER, you can go to Institute of Physics, right? You have IIT, you have ISER, so many institutions of national importance. Okay? So I wish you all the best. I only want to tell that thanks to all the organizers, Dr. Patra, and all the faculty. He has already given the names, all the faculty members involved, and also our office staff, our registrar, and Mr. Dharmendra and Mr. Swaroop, who have helped in organizing many of these things, Mr. Bikram Sahu, who looks after our computers and all that. So many other staff are involved, apart from the faculty whose names you can see there are there. So I thank all of them for making this meeting possible. You know, it is not possible to get so many highly intellectual people from various institutions, top institutions of our country, right? Indians of Science, all of you know our Indians of Science, right? More than 100 years old. The first institute in Asia to have a department of biochemistry, to have a department of electrical engineering. No country in Asia, not South Korea, not China, not Japan, did not have any department. India had. And that was in Indian Science. I don't know how many of you know it. Before Japan had any department of electrical, India had. Before Japan had any school of biochemistry, India had a school of biochemistry. That was at Indian Institute of Science. ICERs were founded based on Indian Institute of Science. The philosophy is same, that we will be at the world's best in science. Science education, that is teaching science. We have a BSMS program, 5 years, and also doing research at the best level in science. The model after Indian Institute of Science, which was, which is in Bangalore, all of you should see. It's also my alma mater, and it's one of the best institutes of our country. Now, of course, we have ICERs. Also, we have IITs. We have 23 IITs. All IITs also have science departments. The old 5 IITs are very well known, and the young ones are coming up, right? And you should see the kind of students they have produced, right? Worldwide, India is known for our IIT BTech students who have started many of their careers. And they are also known, if you go to US, most universities, you will see PhD students from India, postdoctoral students from India. Any institute you go to Harvard, you go to MIT, you go to Stanford, you will have lots of Indian students as PhD, postdoctoral students. Many faculty, most mathematics department in US, many I have visited, will have Indian faculty, statistics department, electrical engineering department. These are popular departments where Indians are there. Chemistry, it is little less. Biology, it is little less. But you go to any electrical engineering department in United States, there will be several Indian faculty. So India has produced top of the line human resources. That means our brains are very good. All of you can do wonderful work, right? So all of you should aspire to be the best, to go to the best place and learn the best. So ICERs are set up to give the best kind of science education and also do cutting edge research. And you can come to ICERs through a joint entrance examination, which is called IAT. Like IIT, you give joint entrance, JEE, you get main JEE, then you get advanced JEE. In ICERs, you have to give IAT exam to enter. So India has now 7 ICERs. I believe 1 or 2 more are going to open up very soon. So I wish you all the best, and I hope you learn a lot. It will be very fascinating and very interesting. The talks last year, what we had was fabulous. Students did not leave, some teachers till night, 8 o'clock, 9 o'clock, I still remember. They're asking questions. So all the best to you. Thank you very much.
Thank you, sir, for your inspiring words and visionary leadership. It is now my privilege to invite our chief guest, Ms. Madhumita, to share her insight with us. Ms. Madhumita, an IAS officer from 2020 batch, currently serving as Chief Development Officer cum Executive Officer of Jilla Parishad Ganjam. Her inspiring journey from a small town in Haryana to becoming a distinguished public servant is a shining example of resilience and determination. An outstanding academic achiever, she topped her class 10th and 12th board exam, graduated as a university topper in Bachelor of Business Administration from Panipat Institute of Engineering and Technology, and pursued a special course on public administration. Known for her dynamic leadership, Ms. Madhumita has made significant contribution to grassroots development in Ganjam district, with a special focus on women empowerment, rural development, and community engagement. Her work has brought remarkable improvement in education, health, sanitation, livelihood, earning her widespread admiration. Her journey is a beacon of inspiration showing how dedication and perseverance can create meaningful impact. Well, Ms. Madhumita, we are eagerly looking forward to your words of wisdom.
Good morning to all of you. So seeing you all sitting here reminds me of the time I was confused about the choice of academic stream. जब मैं class 10 में थी and I just finished my board, so I was confused. So I was looking forward to tell you the benefits of taking science, but let me tell you, I've been a student of management. I took commerce. So it is an irony, and when people from ISER came to invite me, I was telling them, you are convincing someone, you are asking someone who has taken management as a stream to convince people for science. So before going forward with what I have to say, I would just ask a simple question. How many of you have read the poem Road Not Taken by Robert Frost? Okay. So can any one of you tell me what does it say? Anybody? Yes, please. Yes. So right now, how many of you are from 10th standard who are just going to make that choice? 10th standard students. You already made that choice. All of you are from science. Okay. Even if you are from science, you will be specializing in something because after 12th, you have to specialize. Okay. So how many are from maths? Biology? Okay, you already made the most confounding choices because maths and biology. So two girls here, when sir was asking ki math ka importance and all that, they were saying, okay, we have biology. So road note taken ka hai ki the choices you make right now are going to change the way you're going to lead your lives for the rest of the time you would be here. Some people can be doctors, some people can be researchers, some people can be professors, and there are many more professions you can pursue with the help of science. Science is the foundation of everything. Everything comes thereafter, whether it's arts, humanities, management. As a student, I always used to dread science because we did not have exposure with it like you people have the opportunity to attend today. So at the outset, I'd like to thank ISER for organizing this seminar for popularizing science in Odisha as part of the science outreach program. And I hope that it inspires all of you to pursue career in scientific fields and contribute to the vision of a developed India in the year 2047 with your discoveries and innovations. Thank you.
Thank you, ma'am, for your inspiring words and encouraging students. So we will now proceed with the group photo. I kindly request all of you to please remain seated. Now we are going to have the high tea on 4th floor. You all are requested to please join us.
So we'll start our first session, and in the first session we'll have two talks. One is on quantum computing and another one is on chemistry. So प्रथम अधिवेशन रे हम मान को दीटा टॉक रहइबो. प्रथम टॉक रहइबो क्वांटम कंप्यूटिंग उपरे and द्वितीय टॉक रहइबो chemistry उपरे. I hope you will enjoy this session. So I'd like to invite Professor N.G. Prasad to chair the session and will introduce the speaker. Welcome, Professor Prasad. Yeah.
Good morning. It's a pleasure to be welcoming you to the first session of this wonderful program. In this session, we have two talks. The first talk will be on quantum mania, the power of quantum technologies. The speaker is Dr. Bhaskar Kanseri from Indian Institute of Technology, Delhi. Let me give you a brief introduction to Dr. Bhaskar and his work. Dr. Bhaskar is working as IHFC Chair Professor at the Department of Physics and a joint faculty at Optics and Photonics Center at IIT Delhi. Prior to joining IIT Delhi, he was a postdoctoral fellow at Institut d'Optique in France, and before that, in the Max Planck Institute for the Science of Light in Germany. He received his PhD from the University of Delhi and National Physical Laboratory, New Delhi. His research interests are in optics and photonics, statistical optics, quantum entanglement, and photonic quantum technologies. He has a lot of achievements to his credit, for which he has also been recognized with various awards and fellowships. He has been awarded the Teaching Excellence Award of 2022 and Veena Arora Early Career Research Award of 2022 by IIT Delhi. He has been selected as the member of the National Academy of Sciences, India, and has also been elected as the Associate Fellow of the Indian National Science Academy. It gives me great pleasure to invite Dr. Bhaskar.
Yeah, good morning. So first of all, I would like to thank the chair of this session for introducing me and Professor Ganguly and his team for inviting me in this particular event. And I would also like to congratulate them for successfully organizing this very, very important outreach activity. So I am going to talk about quantum mania. How many of you heard about it? Oh, very nice. Almost every row has 2 or 3 students who have heard about quantum mania. Essentially, it is a science fiction movie you might have seen from Marvels. And you might have seen that in the what we call quantum realm, things behave very, very strangely compared to what they behave in the classical world or in today's world. So this is what I'm going to talk about. Essentially, nowadays, using quantum science and quantum technologies, many, many unreachable areas are being explored. Many, many new technologies, new devices are coming up. So I will give you a brief gist of activities, what are going on in that area. This is a very, very vast area, so it would not be possible to cover everything, but still I will try to start from the basic aspects of quantum physics and try to build up to what are the quantum technologies. Okay, so you all study classical mechanics or classical physics in classes, Newton's laws of motion. Are you studying them? Very good. These all are essentially sufficient to explain whatever you see in this room. All big, big objects, everything follows the classical physics. However, if you go smaller and smaller in size, for example, if you go up to atomic or subatomic scales, then things cannot be explained with classical physics. In fact, classical physics ceases to exist. And you need a very different kind of physics or very different kind of mechanics, which we call quantum mechanics, and which clearly explains and gives you all what you can see. This can be very, very strange. It can be counterintuitive. It can be very, very different than what is visualized in day-to-day life. And this is why this quantum mechanics has been very, very important in science. In fact, if you go back to end of 19th century, all classical physics has been developed significantly, and it was thought that there is no other physics remaining. No problems are remaining which should be answered, because everything has been explored, which is very, very important. But then there were certain problems. For example, there was one problem of black body radiation. I will not go into the detail, but you can note down these keywords and you can later on explore what essentially it means, because these are itself a topic of a complete lecture. So black body radiation was one of the big problems, could not be explained with classical physics. And then the gentleman Max Planck, who has also received a Nobel Award, came and he proposed a completely different way of exchange of light. He said that light is not flowing in a continuous manner, but it is actually flowing in packets. And these packets were named as quantas, which later on were considered as photons. So you must have heard about photons. So photons are the energy packets which are essentially flowing or basically giving you a way to interact light and matter. Later on, Albert Einstein has used the theory of Max Planck, that is the quanta, to explain another very important aspect which is called photoelectric effect. You might have studied photoelectric effect, some of you maybe. And this is all the credit goes to Albert Einstein, who also received a Nobel Award on that. And further, subsequently, Heisenberg, Schrodinger all contributed significantly to develop this new science, which we call quantum science. And in fact, if you look into the behavior of quantum objects, they behave completely different than the classical objects behave. There can be properties, for example, superposition. Classically, you know that any object is localized in a particular place. But when you look into quantum objects, they can be simultaneously in many places before the measurement. And only the measurement collapses them to a particular place. So this is a very interesting aspect, superposition. The other interesting aspect is wave-particle duality, where you can find quantum objects to behave as both waves as Copenhagen interpretation. And this is what we call nowadays also as Copenhagen interpretation, essentially told us what quantum physics is, what are the rules of quantum physics, and they are widely agreed upon even nowadays. Now, as I mentioned earlier, that classically you visualize things. You understand that something is present at a particular position. But if I ask you something is at every place, every possible place, then it cannot be recognized or it cannot be conceived in minds. Similarly, there are many, many aspects which look quite intriguing, quite difficult to understand. And in fact, when I was making those slides, my 5-year-old kid came to me and he asked what I'm doing. I told that I'm making some slides on quantum physics. I thought that this is a very jargon for him. He will not understand what I'm saying. He says, I know everything about quantum physics. I said, come on, you're 5 years old. How can you say so? He said, my cartoons have everything about quantum physics. I know what is superposition. And I'm like, okay, you know superposition. Then he showed me one cartoon, which I would like to play now. And many of you might have seen it. This is a clip from a cartoon called Teen Titans. Yeah, many of you have seen, but I will still try to show you. Please have a look and see that what it says.
Now, prepare to have your minds blown. Quantum physics can be a bit confusing at first, so we'll start with one of the fundamental principles, superposition.
Oh, please. I know all about superposition. Check it out.
That is a superposition.
This is my superposition. What?
Stop that! We're talking about science, not superhero poses!
If superpositions isn't about posing like Batman, we ain't interested.
I promise you will be interested once I explain superposition according to the Copenhagen interpretation.
Copenhagen? We're going to Denmark?
I wanted to see the Little Mermaid statue.
Fish women.
I love the eating of the pickled herring.
Pickled fish.
And they got that good Rosenborg castle, yeah?
Home of the Fish King. The whole city is fish.
We will never, ever go to that dirty fish town!
So, we're not learning about interesting cities or posing like superheroes?
No, just science. Now listen closely to this important information. Superposition is the concept that when we do not know what the state of an object is, it is actually in all possible states simultaneously. Only the act of observation and measurement causes the object to be limited to a single possibility. It truly is an incredible concept.
Wow, I can't believe it.
So, you understand?
Nah, fool. That's some straight up gibberish.
We were impressed because we thought you couldn't get more boring.
And yet you did. You did.
So you could see that it's very difficult to visualize what superposition is or what other quantum phenomena are, but I will try to give you some understanding what superposition is. As I mentioned that unlike classical objects which you see, you measure and you still find them the same, quantum objects before measurement are in a completely different type of state. They are in a state where they can be everywhere, wherever is the possibility, and your act of measurement gives you a particular location where they will be found. So this is what we call measurement dependent outcome. They can act as both wave and particle. I will come to that later. And also they can be not cloned, which we call. So imagine now, like digital electronics, you must have heard about bits. Have you heard about bits? Like 0 and 1. Many of you must have heard. So all your digital information essentially in two states, 0 and 1. 0 may be lower state, upper means higher state, that is 1. And you can assign any information in this 0 and 1, and you can do all your computers or your information technology, everything works with the bits. Now imagine if I have a situation like this, where the switch which I am talking about, 0 and 1, it is somewhere in between. Will it be a possible outcome? What do you think? It's an error because it cannot, neither it is 0 nor it is 1. However, in quantum, this superposition can have all possible values of 0 and 1. That means the switch, which is not only 0 and 1, but it can have infinite states between 0 and 1. And that gives you not only two outcomes, but you have thousands or even millions of outcomes to play with. So at the same time, you can work with all. And that gives you very high computational capability, which doesn't provided by the existing classical bits. So these are the superpositions which are used as quantum bits. Now there is another aspect which is wave-particle duality. You must have heard about waves. Waves are not localized in space. They can be everywhere. Now imagine the first picture left-hand side. You have a laser beam which is passing through two slits. Have you heard about Young's double slit experiment? Anyone? Maybe somebody from 11th, 12th, you might have heard about that. Some hands I see raised. So essentially when you pass these waves through the two slits, they pass through each slit and then they make their own wave fronts. They interfere with itself and you get a pattern something like these lines which you see. These are the maximas and minimas in the screen. On the other hand, if you take particles, for example, you take small maybe some bullets or maybe some stones, pass through two small windows, you will say that they will be localized at the other side. So instead of all these possible fringes which you get in case of waves, you get just two peaks in case of particles. So you see, these are two completely different things. Waves cannot be particles, particles cannot be waves. Now let us look into what happens in quantum domain. Imagine I have a box which gives you some quantum object. It can be an electron, it can be a photon, it can be an atom, it can be even a proton. And when it passes through the double slit, it actually produces a pattern which is the interference of the probabilities passing through these slits. So you get some wave-like property out of a particle-like object, which is basically an electron. At the same time, if you try to observe which the same electron, that which slit out of the two it is passing, it reduces to a particle nature, and what you get is these two peaks which you get in case of a particle property. So you could see that the same electron can show you both wave nature as well as particle nature. So clearly it is not a classical kind of object, but is something completely different. I would also like to show you one experiment with this double slit which we did in case of single photons. So look into this experimental scheme. We have a single photon source. We are throwing one photon at a time. We are putting a two slit arrangement in between, and we are looking what is happening on the screen at some distance away. This screen you could see in the left hand side here, which is basically a camera which can detect single photons. So this is a camera, and there are these small white dots. These are the detection of those photons. So I will run this video and you will see that these photons, which are actually very far from each other, they pass through this double slit and they are detected at certain regions in the screen, which after a long time will make an interference pattern. So clearly particle-like objects which have nothing to interfere finally give you a pattern which is coming as a wave property. So I will run this video. So it will be running very slowly. So I am accumulating the frames with time. You see that these detections are happening on the screen, these white dots. Slowly you will see that you will get some lines there where there is bright region, dark region. Maybe I can run it a bit fast. So after some time you see, can you see some lines now? Maybe after some more time, maybe after a few minutes, you see that you get a very nice pattern, which is an interference pattern coming out of this double slit, which is normally seen classically with a wave. That means these quantum objects like photons behave both as waves as well as particles. And that is something which is clear that they have some strange properties which can be used for many applications. So we'll stop here, this one now. Okay, the other interesting property of quantum objects is what we call no cloning theorem. That means that you cannot clone or duplicate a quantum object. Classically, if I give you a paper of some information and I ask you make its copy, you can easily go to a photocopy machine, you put it, you make thousands of same copies, all identical. It's very easy. Classically, things are very easy to duplicate, but quantum mechanically, if you try to do that, I'm showing an example of a polarized photon. If it is in a vertical direction, since you know it is in vertical direction, you can make its many copies. If it is in horizontal direction, still you know about the exact direction, you can make many copies. But the moment I make it diagonal, you don't know which direction it is. So you cannot make its copy. It is completely unknown object which copy cannot be made. So quantum objects do not allow you to make its duplication. And this property can be used, for example, for cryptography, which Professor Ganguly was mentioning in the morning, that you can send the information through photons, you ask the other party to detect it, but if somebody in between tries to detect it, it is detected wrongly, and the other person easily knows that somebody tried to interest in between. And that way, you can easily catch the person who is eavesdropping the information. Okay, so now whatever I have so far said about it is all quantum science, and this all happened during 20th century, which is called the first quantum revolution. So in first quantum revolution, a new science has developed. New rules of reality have come up which were different from classical physics or classical mechanics, and people understood the interaction of light with matter. and that essentially give rise to many applications which you are now using. For example, everybody of you use computers. Computer is a direct application of the first quantum revolution because it uses many of the optics such as transistors or many other quantum devices which came from the first quantum revolution. You use MRI scanners, you use nuclear energy. You know that India is one of the very well regarded nation in nuclear energy, thanks to the first quantum revolution. We have semiconductors, they are all working with first quantum revolution, with quantum objects, and also you have smartphones. In fact, with time, things are becoming smaller and smaller thanks to new and new innovations in the area of quantum science. Not only that, there are even more objects. For example, you must have seen or used lasers. Lasers are also one of the outcomes of the first quantum revolution, which actually are used in many areas, including defense. And also you use transistors and ICs. Now, this century is more devoted to what we call second quantum revolution, where the idea is to go even beyond. Now you have understood all about quantum sciences. You want to now convert this science into technology. Quantum mechanics to quantum engineering. So this is the goal. Here the goal is to make now disruptive devices, disruptive technologies, which essentially would have our own design and will serve our own purpose. For example, we can make quantum computers, which are a completely disruptive outcome, and it can actually be very powerful. It has orders of magnitude better computational capability compared with a supercomputer which we use nowadays. So quantum computers are one example. In fact, you must have heard that very recently a quantum chip has come up from Google, which is very powerful and which can do calculations very fast. So this is all coming from the quantum 2.0 or second quantum revolution. We have quantum sensing and metrology. We have sensors which are very powerful compared with classical sensors. For example, we have magnetometers which can sense submarines or any magnetic signal very effectively. That's again from quantum physics. We can have clocks which are very accurate, probably like atomic clocks, which can be very accurate even for millions of years. They will not lose even a second up to millions of years. So powerful devices. We have gravimeters and many other kind of sensors. These are all coming from quantum science and technologies. And then we have quantum key distribution, which is about quantum cryptography, which I already mentioned about. So here, you have a sender which we call Alice, you have a receiver which we call Bob. There are some standard names. And then you use the principles of quantum physics like no cloning theorem, like superposition to send information from one to other. And any attempt of catching that information or typing that information essentially changes the quantum state or quantum object, and you easily notice it. Alice and Bob easily notice that somebody has tried to steal the information, and you can that way catch who is doing that. So clearly this is something like, for example, China has come up with satellite-based quantum communication, which has gone up to intercontinental distances like 1500, 2000 kilometers. And most of these technologies are very crucial for strategic applications like defense services, like maybe for army and air force. And this is why these are of denial nature. That means if you want to go to China and ask them for some quantum technology output, they will not give it to you. So it is the national indigenous attempt to develop those technologies so that we need not to ask it for anybody. And this is why they are of national importance. Okay. So I will just spend some more time on quantum cryptography because this is something that we have been doing for a long time. So as you could see that in quantum cryptography, we have Alice, one of the user, Bob, other user. They are the authenticated user. That means they are the actual users who should communicate between them. They use a classical channel through which they talk to each other. And they also use a quantum channel through which they send a quantum object. And you know that the fastest quantum object is a photon, which has a speed of, what is the speed of a photon? Yeah, so you all know what is the speed. It is the speed of light is c, basically we call it. And with this speed, they can communicate the information. Then any EU who is trying to steal the information can be caught because it changes the quantum state. And the beauty of this system is that it is unbreakable. And in fact, even a quantum computer, which is very, very powerful, cannot break any or cannot hack any of this kind of quantum cryptography system. Now, this quantum cryptography is not just between two users. Ultimately, you would like to extend it for all kind of users. So you have to make a network. So this quantum cryptography leads to quantum networks. And finally, you have to make an internet which works with this kind of objects with qubits, not with bits. So that's why with classical internet, you also need a quantum internet to exist, which works with quantum computers, which communicate data with quantum devices, and that quantum computers will communicate using quantum internet. So these are the plans, the way we have to exceed. Now, if you look into how quantum communication is done, you have two possibilities. Either you use a fiber communication. You must have heard about optical fibers. Optical fibers are currently used for all your internet communication. So they are basically underground fibers connecting every city, every user, and you are having all broadband and all kind of communication, light communication. And the same fibers have to be used for quantum communication. You can also use what we call free space or satellite. That means either you connect two buildings with some free space line of sight communication, because photons only travel in a straight line in free space, you know that. Or even satellites. That means you put a satellite somewhere, you have a ground stations, one ground station communicates with the satellite, and then you communicate with the other ground station, and that way two ground stations can set up the key. So these are the ways people do that. This is an example of China's satellite-based QKD, where they connect two ground stations directly with the satellite. In fact, they send two photons from the satellite to the two ground stations, which detect the photon and they set up the key. So they have developed, they have exceeded significantly in this area. With fibers, you can do what we call a QKD network, which is basically connecting different nodes with the fibers, and in between every nodes, you can send up the key or set up the key. So these are the examples of fiber-based quantum networks. In fact, if you look into the satellite-based communication worldwide, this is not just a single satellite which has been tried. Every country is trying its own way to make satellites. Even in India, ISRO is also trying to make its own satellite, which is also a quantum satellite for QKD. If you look into, there are full-fledged satellites like China, that is MISIUS, but you have also some small satellites. They are called nanocube satellites or cube satellites, which are being sent by, for example, Singapore or some European countries, or even they are trying for geostationary satellites, which can be used for this quantum communication. So a lot of activities are happening in all over the world for developing satellite-based quantum communication. In fact, people are also trying to make what we call a backbone network, which can connect all major cities of a country. Like China, they have a network which connects all main cities about 5,000 kilometers in fibers, and this is one of the longest QKD network all over the globe, which is made on fiber. In India also, we are trying to set up a 2,000 kilometer long network, again connecting major cities, including Delhi to Chennai, through this kind of backbone network. In fact, 2 years back, we have made one of the first 100-kilometer fiber-based quantum communication in India. We together with DRDO worked on this, and it was between Prayagraj, which we earlier called Allahabad, to Vindhyachal, which was separated by 100-kilometer underground fiber. So our Alice was at Prayagraj, our Bob was at Vindhyachal, and we had a link of 100 kilometer where we have got a key rate which is more than 10 kilobits per second. So this is the first indigenous attempt to make quantum communication in India for connecting two cities, or what we call intercity. And then we ask the question, can we do it better? Can we go for longer distances? And with state-of-art technologies, actually, you can go for longer. For example, nowadays, very, very efficient devices are available, like what we call superconducting devices or superconducting detectors, which are a very, very complex system, but which can detect photons very, very efficiently. Maybe 10 times or 15 times better than which you normally find with solid state devices. So these kind of detectors, if you use and you use more optimization of the systems, you can actually go for even longer distances. For example, in IIT Delhi, we could go up to 380 kilometers with a fiber spool without any nodes in between for quantum communication, and that can actually connect even longer distances or even farther cities with quantum communication. And the goal is to reduce the dependence of intermediate nodes, because these nodes are very, very prone to any kind of attacks. The other aspect which is very, very intriguing is what we call quantum entanglement. Anybody heard about entanglement? Many of you must have heard about, it is all very, very fancy nowadays. So quantum entanglement is something which has been proposed maybe 30, 40 years back in experimental way by John Bell, but it was considered as a thought experiment way back in 1935, where Einstein was the most refuter, or we can say he had never agreed with quantum entanglement. He said that it is just a spooky action at a distance. I don't consider it to be a realistic outcome, but nowadays it has been actually a very, very realistic and very, very powerful building block for quantum technologies. So what quantum entanglement is, you have quantum objects which interact in past, and then you separate them and put them any distance away. But they always contain quantum correlations, and these quantum correlations actually make them in such a way that individually, if you try to measure one photon, you can get any output, but the moment you measure one, you immediately know about the other. Whatever be the distance, you can put one in this galaxy, other in the other galaxy. If you make a measurement on this one, you immediately know about the other. So this cannot be provided with a classical means. And this is why this kind of thing has been more in myths or in science fictions, but later on it came to the reality. And the people who actually before that, maybe I will also tell you how it actually works. So in the lab, you can actually generate quantum entanglement. What you do, you use a laser, you use some crystal, which is basically what we call non-linear crystals. You can note down and you can get the details later what it means. And their interaction essentially gives to a pair of photons which are entangled in a quantum mechanical way. That means if you use this kind of a scheme and you generate these photons, they have a particular polarization property. If signal or one of the output has horizontal polarization, the other one will always be in the opposite polarization, that is the vertical polarization. And if you pass it through a polarization splitter, one of them will be transmitted, the other one will always be reflected. So whatever be the distance between them. Remember that they are non-local correlations. Non-local means they can exist at any distance. Let me give you an example. Imagine that you have this entangled source. You put a photon A to one direction, photon B to other direction. Let's say one photon in India, other photon in US. Now you put these polarization splitters and you try to see the A photon when transmits, which means it is horizontal polarization, the other one is automatically reflects. They are not talking to each other. Remember, they are very far from each other. They don't know. One photon doesn't know what is happening to the other. But they are prepared in such a way that if one is measured in horizontal, the other one automatically comes in the vertical. And by chance, if the first one is measured in vertical, it reflects. The other one automatically comes in the horizontal. So they are always having anti-correlations. Always they are orthogonal polarization. And this is something which is very, very useful. And the people who have actually contributed to make it happen are these three gentlemen who have actually received the Nobel Award in 2022 on their work, their research on quantum entanglement. Their names are Alan Espé, John Closer, and Anton Zalinger. They not only first time observed entanglement in the lab, they proposed theories how to measure it, and then they looked into their experiments. With their experiments, very, very long distance entanglement can propagate, and it still can be measured probably in hundreds of kilometers away. So that was the groundbreaking activity they have done, for which they have been awarded the Nobel Prize. And these quantum entanglement based technologies are not just one, there are many. If you read it, you see that you can do what we call quantum teleportation. You must have heard about teleportation. Star Trek movies, maybe many of you are stressed. You can do quantum internet, which I told. You can do QKD, which is the cryptography. You can do clock synchronization, because your both photons are coming exactly at the same time. So the kind of precision they provide, you cannot get it from anywhere else. They can do what we call quantum randomness. So randomness is something which is essentially an innate property of quantum objects. Quantum measurements are purely random. And this entanglement provides you this randomness, and in fact, you can make a random number generator which can be used in many applications. Where you use random numbers? Can anyone tell me where you use random numbers? Passwords, for example. OTPs, for example. Or even when you are playing a game, you are throwing a dice. You don't know in a priori what will come out. And it can be anything random. So in casinos where people play, they all use these random numbers there. So random numbers are very, very useful. And entanglement can give you an opportunity to make very, very true random number generators. Now the other area is quantum computing, as you might have already known about. So we have already superposition. We are using qubits. We have interferences, where we can interfere those possibilities and get maxima. Maximum means maximum probabilities, and minima means lowest probabilities. And we can also make entanglement. So these all three recipes together come up and make what we call quantum computer. And this computer, this is an example of how the computer from IBM looks like. So these computers are being built in every country. Every country wants to make their own first quantum computer and try to show that these are really useful for the society. In India also, there are attempts which are being made to make quantum computers, and the use of quantum computers is significant. Where we are going to use them? You know that the weather is very, very unpredictable. And with quantum computers, actually, you can predict weather very, very accurately. You can, for example, make new devices, new drugs. You can model the protein, you can model molecules, and make new kind of drugs which are not even existing. The kind of resources they are required with current computational powers would take thousands or even more years to make some useful drug, which quantum computer probably can do in just a few minutes or few seconds. So they are really very powerful expected outputs of quantum computers. You can also do cryptography. As I mentioned, we have been doing cryptography. With entanglement, with quantum computer, you can actually break the codes which are existing. Currently, whatever codes we have, for example, classically you have these OTPs. Somebody said that we use OTP. Now if you have a powerful computer which can guess very fast, your 6-digit OTP can be guessed in a fraction of a second. So rather than you, somebody else will take the money, because he knows what is the OTP. So in that situation, you need ways by which you can actually protect your digital information, your passwords, your online transaction details, and that all can be done by quantum cryptography. And similarly, you can do many, many new things like financial modeling and many other things. And quantum computer is, that's why, one of the main resource which people are actually trying to make. And if you look into quantum computers, there are different ways people are making these qubits. I told you about the qubit. These qubits can be made, for example, using superconductors. So this is one way which in India also people are trying to make qubits. You have spin qubits which use spin of ions plus minus, and they can use, you can use topological qubits, you can use semiconductor qubits, even you can use photonic qubits, you can use photons, and that is also a very, very important technology, because photons can be used in room temperature, whereas most of them require cryogenic temperatures, which are a lot resource intensive approach for making qubits. So many kind of outcomes with quantum qubits are being done, and nobody knows that which one is the most powerful, because in some month some approach is very nicely working, but in the next month somebody else comes with a new idea and says that this qubit is better than the previous qubit. So there is always a fight between different qubits, that which one will actually make the final quantum computer. And I was talking about entanglement, so we had also worked with entanglement based QKD, and as you could see that we could generate entanglement, polarization entanglement, we can separate them up to 50 kilometers. In fact, not only that, in IIT Delhi campus, we put a fiber, underground fiber, which was about 8 kilometer length, and we have shown that in a field deployment case also, you can deploy in deployed fiber, you can send these photons with entanglement, and you can detect them after certain distance, and they still find the entanglement property to be retaining there, which means that you can do QKD, you can do many things with quantum, with these kind of deployed fibers. Now, what is the final road ahead? Now, how people are proceeding in quantum technologies? So I will give you some timelines how people have actually come up with. If you look into computers, roughly 80 years back, 70 years back, there were what we call electromechanical computers. Computers of the size of this hall probably. Then there were developments in transistors and ICs. New ICs came in 1960s and 1970s. New protocols for internet came. And by 80s, you have the Mac systems which were developed. And by 90s, you have the internet, which we now use as well. So this internet has actually gone through these particular ways. And if the same you look into the quantum domain, these are the forecasts. In 2010s, we had some initial computer which we call D-Wave or annealing computer which came up. In 20, we are talking about quantum hardware and quantum supremacy. That means we are saying our computers are better than classical computers or supercomputers. Maybe after certain years, we expect to have multi-node QKD networks. We are already developing some, and we believe that by the end of this decade, we will have such networks, such will be there within India. Then we will have full stack quantum computers probably in next 10 years. And finally, once they are developed, what we expect that by 2047, when we are expecting a Viksit Bharat, we will have quantum internet also in place, which can actually connect all these quantum processors, and you could have a safe communication all over the world with quantum technology. Now, another interesting aspect which I believe that you must have heard about is teleportation. As I mentioned that Star Trek movies, you might recall this dialogue, "Beam me up, Scotty." Have you heard about this? Many of you must have seen. So they have a teleporter which essentially teleports a human object from one place to another. And this was in scientific fiction movies. Now the same kind of concept is being used with the help of quantum technologies. And what people are trying to do is what we call quantum teleportation. So quantum teleportation, in quantum teleportation, we do not teleport an object or a human being, but we teleport a quantum state. The nature of the quantum state is teleported. And how it is done? It is done with the help of entanglement again. You have an entangled photon source, one photon which is with you, and the other photon is sent to where you want to teleport the information. Now the interaction of any unknown photon with that entangled photons gives you some outcome, which you actually translate to the other object. And if you make the measurement based on that outcome there, the photon disappears from the first place and it appears on the other place where you want to teleport it. So you can easily teleport photons from one place to another. In fact, very recently in US, people have teleported electrons as well. which is also a quantum particle. So the moment you can teleport electrons, protons, neutrons, essentially you can teleport molecules later on, and you can build up with airs, probably you can teleport even classical objects as well. And in fact, very recently people have also shown that this teleportation works with a fiber which actually have the standard internet traffic. That means with internet, with live signals, you can also do teleportation, which is one of the greatest achievements, because with this you would be able to reach nearer to what you have seen in science fiction movies about teleportation. Okay, one other example of quantum sensors is what we call LIGO, Laser Interferometer Gravitational Wave Observatory. Anybody heard about LIGO? Not many. Okay, so LIGO is a very, very sensitive detector. In fact, there are 2 such detectors in US which actually detect gravitational waves. And in 2014, for the first time, these detectors have detected gravitational waves. This is how they look like. You have an interferometer where each arm has a length of 4 kilometers. So they are very, very big experiments. And they have shown that by using quantum light, which I have written in the top, you can actually enhance its sensitivity by 2 to 3 times. So if you use quantum physics, you can actually make it more sensitive. That means you can observe many, many smaller black holes, smaller objects, celestial objects, by using these kind of interferometers. And you'd be happy to know that in India also one such LIGO is being set up in Maharashtra. And hopefully by 2030 it will come up in its shape. So it will be an opportunity for you all to be a part of this LIGO kind of interferometers or experiments. These are very, very big experiments. Many, many countries have different type of interferometers. Like in US, they have 2 LIGOs. In Japan, they have a different kind of interferometer. In Europe, they have even smaller but more efficient interferometers. So they all are working in such a way that you do not miss any of those astrophysical events. You can detect all of them. So this is a very, very challenging area, and this is exploration for different astrophysical objects. Now, another question or another thing which you would like to know is where we are going to use this quantum technology. So one of the very, very, what we can say, effective area for which there is a huge race in quantum science and technology is the warfare. In defense, in strategic areas, everybody wants to make quantum devices because they are more efficient. For example, there are radars. Current radars work with microwaves, but now people have made quantum radars. For example, China has made a quantum radar by which they can detect any stealth aircraft, any aircraft which is not detectable by microwaves can be detected by this quantum radar. In fact, they have detected a US aircraft for the first time, which even US doesn't believe that they could make it, but it was in news that they have come up with a quantum radar, and nowadays many countries are again trying to make those radars to be more powerful. Then you have sensors like magnetometer sensors. You have underwater warfares where you want to detect the magnetic fields. I told already about submarines, but you can have even more sensors. You can make a distributed sensor system where you can detect all these kind of small variations, and that way the warfares can be designed. You have, for example, chemical detectors. People are trying to make chemical sensors which can be more powerful thanks to the quantum physics. You can do underground mapping. People are making quantum gravimeters, which detects the gravitational field. And if you can make them more powerful than the classical ones, you can actually use them for detection of mines or detection of many those kind of underground objects which cannot be approached by the classical sensors. And I already talked about quantum internet, which is a very important tool for warfare, because if you block any strategic communication, or you basically steal any strategic communication, you already paralyze the enemy by doing that. The quantum efforts are not only in some specific countries, but they are actually in every country. If you look into this map, every country is trying to have its indigenous attempt to make quantum technologies. US, China, they are the leaders. They have actually pumped a lot of money to make their indigenous devices. And in fact, India, as I mentioned, that India has also started its own mission, which we call National Quantum Mission, which has rolled just last year. And currently that is expected to be started with a full swing. And in National Quantum Mission, the goal is to develop all these technologies indigenously to make an ecosystem where you can actually come up with all subsidiary technologies. Like for example, I mentioned about QKD or quantum communication. So you just not only need all this communication, but you need detectors, you need sensors, you need cryogenic devices. So all this ecosystem needs to be developed. And this is the area where there are tremendous avenues for all the students who are completing their maybe 12th or 10th. They have opportunities to be a part of these initiatives, to explore more about that, and to actually work on those areas, because by the time this will be in its middle, you all will be the main workforce to work on these particular frontier areas. In National Quantum Mission, which is actually being operated by Department of Science and Technologies, there are 4 different verticals, what we call hubs nowadays, which are going to focus on developing these technologies. These are quantum computing, quantum communication, quantum sensing and metrologies, and also quantum material and devices. In fact, this quantum material and devices is a very, very important area where you need to finally, once everything is shown as a proof of concept, you need to make finally the devices. You need new materials for that. And this is the area where, again, there is a huge impetus by the government to come up with new materials and to develop new devices. So, as I mentioned, I would like to welcome you all to be a part of this national initiative. And probably I will now close by saying, by using the words of Niels Bohr. What he said is that if quantum mechanics hasn't profoundly shocked you, you haven't understood it yet. So I would like to thank all. Some of the work which has been done here has been contributed by my group at IIT Delhi. So I would like to thank all these smiling faces who have actually worked in the lab for achieving these results. So thank you very much. If you have any questions, you can email me in case I am not here. Otherwise, you can interact me today. Thank you.
Thank you, Dr. Bhaskar. That was a very fascinating introduction to Quantumania. Students will get a chance to ask their questions and interact with Dr. Bhaskar after the next talk. The next talk of this session is From Discovering the Fun in Chemistry to Applications in Everyday Life. It's an interactive session by Professor Pramit Kumar Chowdhury. Professor Chowdhury is a professor in the Department of Chemistry at IIT Delhi. He specializes in physical and biophysical chemistry. His research focuses on understanding protein folding, misfolding, and dynamics in crowded environments. Professor Chowdhury got his BSc from Presidency College, Masters from IIT Kanpur, and earned a PhD from Iowa State University in the US. He then went on to do a postdoctoral tenure at the University of Pennsylvania. And at IIT Delhi, he has been a professor since 2009. He has numerous very high-profile publications to his name and is recognized as one of the leaders in the field. Professor Chowdhury.
Please do. Otherwise, I just run amok. Sir, नहीं ऑडियो कहाँ इधर ना? अच्छा और ये HDMI सर ये ठीक है मेरे लिए सर ये वाला हाँ ओके Okay, good afternoon, everybody. Can you hear me properly? Good, that means you're not sleeping. So, I would definitely like to thank Professor Ganguly and all the other organizers to have some of us over here to share with you our thoughts about what we work on. And many thanks to Professor Prasad for that very kind introduction of his. So I, as Professor Prasad pointed out, I'm in the Department of Chemistry in IIT Delhi. I've been there from 2009, okay? So I hopefully you're not already quantum mechanically teleported. If you are, Professor Bhaskar can get you back. I cannot. But what we'll do today is we'll try to have a different kind of look at chemistry. A chemistry which we understand is there. We understand that we have to go through and memorize a lot of reactions. But then there are many fun aspects, very important aspects of chemistry in everyday life that we encounter, but we do not realize how much chemistry has helped us in. Okay? So we'll try to keep it a very interactive session. I can get back to you. I can ask you, questions. Hopefully, those questions are not too bad. So as I said, let's try to explore the fun in chemistry. Just let me get the pointer right. Right. So, how many of you have RO-based filters in your houses? Reverse osmosis, right? Okay. Name some of the filter companies. Okay. EcoGuard, Kent, correct. Okay. And there are a few others also. So there are also some filters which are not based on reverse osmosis, correct? Okay. Now, I don't know whether you have noticed ever, the first time a salesperson or a technical person from that company came to your house to make you believe or to impress upon you that this is the thing you need to have. Okay, what did he do? What did he do? If you would remember, I don't blame you if you do not, right? But if you would remember, he would take out a very small instrument, like a stick, right? He will take the water from your tap and show a reading for you, okay? That reading is referred to as TDS. You know what the meaning of TDS is? Totally dissolved solids, that is correct. Totally dissolved solids. So he's telling you that in your water, the concentration of solids is, say, so high that it is not good for you, right? And you would rather have a reverse osmosis based filter which would throw out a lot of those and keep some in, right? So he gives you the TDS concentration, the totally dissolved solids concentration, as was rightly pointed out. Guys, how did he do it? Any ideas? Was it magic? Okay, like David Copperfield or PC Shortcut, did he do a magic? No. He's not a magician. But, well, he is a clever technical person who used science. Have you heard of conductivity? Correct? So what did he do? He measured what? The conductivity or the conductance of the solution. Right? Now, if the concentration of solids is high, what is going to happen? The conductivity would be high. And that conductivity was converted to what? A number which corresponds to the totally dissolved solids. Right? He gave you that number and showed you that indeed this is pretty high and you need to have an RO-based filter. Right? So this is the first step that you realize that unknowingly, I've used the principle of conductivity, right? Or not you, they have used the principle of conductivity to lure you yourself into buying a reverse osmosis based filter. Now the next question is, do you think as per reverse osmosis, I should be throwing out all the minerals? Should I? Why not? Because many of these are essential ones, right? So, there is a certain limit, there is a certain range between 200 to 300, correct? Is a range, or say 150 to 300 is a range that we should be having a TDS at. If it is very low, it is not good for you. So be very careful. Nowadays, if I would draw your attention to this one, and even Kent, so this is from Eureka Forbes, we happen to have that in our house. You will see there are two buttons out here. This button, you know what it does? Huh? Correct, thank you. It is a mineralizer. So what it is telling you, that my reverse osmosis based filter is throwing out a lot of my essential minerals, right? Which unknowingly will leach out minerals from our body also. Okay? So if you drink that, and it is not suitable for many people, let me tell you that. It has been proven. So what they do is, because they cannot control that, they go ahead and add minerals from their filter cartridge, so as to maintain that correct TDS, and hence that water is suitable for drinking. Is that clear, guys? Right? This is the first thing where chemistry comes into effect and comes to help you out in terms of deciding whether you really should have an RO-based filter or not. See, not all places, regions would be having a very high TDS. And there is absolutely no reason for you to go for an RO-based filter out there, because it is obviously more expensive, and more so it is not necessary out there. But there are many places where RO-based filters are of need. Next question, guys. Based on conductivity, because since we are already on this, right? Which ion happens to have the highest conductivity? I have ions, right? Sodium, potassium, magnesium, hydrogen, or sodium? Any other guesses? Silver. Wow, okay. Copper. You know what conductivity is, right? How fast it can diffuse, mobility, right? But I'm afraid none of those answers are right. Lithium? No. It is actually H+. It is actually H+. Why is it H+? Why is it H+? Because of the size, isn't it? The size is small. But there is one more interesting aspect to it. But let me ask you this. How many of you guys have read conductivity? Have you guys read conductivity as yet? No, covered? No? Okay. But still, let me tell you this. You see, this is a water molecule, right? There is a water molecule and you have H3O+. That means an H+ has come in. Okay? Now, water is unique. Why is water unique? Because it is a network of what? Hydrogen bonds, right? It is too many hydrogen bonds throughout. Okay? Now, what happens is, if you have an H+ coming in, if you look at this, there is H2O, 1 O, 2 H's, and H+ comes in, it becomes an hydroxonium ion. Correct? Now, because of this network means the water molecules are small and the water concentration typically is very high. Does somebody know what the water concentration is? You can calculate from the density. You know, from the top of it, you know? It is about 55 molar. Okay, it is indeed very high at obviously room temperature. It is indeed very high. So in that respect, you will be having a lot of water molecules. Now the question was, which I started with was, right? Why does H plus have the highest mobility or the highest conductivity, right? So if you look at this line, what is happening is the H plus from here, because of the high network or the high concentration, the detailed network, this H plus jumps to the second water molecule. Then the second water molecule becomes protonated. Then this H plus jumps to the other water molecule, which is also which then becomes protonated, and so on. So what is happening? The water molecule is not moving, but the H plus is doing what? Hopping from one molecule to the other. And because it hops, and because you have so many water molecules, that network makes sure that its mobility is very high. It indeed has the highest mobility. Which comes next? Do you know? It is based on what? If it is H plus, what is its counterpart in water? If it is H plus, OH minus, OH minus. So OH minus comes next actually. Because of a similar mechanism, but OH minus is not as high as H plus. This is a little more involved, but if you guys are up to it, you can look it up. It is still an ongoing research, and people have proposed certain reasons for that. Okay, everybody okay with this? Okay, good. Now let's look at something where we use chemistry every day, probably without realizing it that much. What do you see? Smog. Okay, you guys are fortunate. It's a beautiful weather out, right? Some of us from Delhi, and as Bhaskar would say, that many a times during the winter season, we end up facing this kind of situation, right? It's a photochemical smog. What is smog? Smoke plus fog, correct. Smoke plus fog. What is photochemical? Right? So chemical is chemistry or any chemical process that is initiated or brought about by photons is called a photochemical process, correct? Okay. Now if you look at this pie chart, what you will realize is the road transport, that means the vehicles, right? Cars, SUVs, trucks and all these buses, they contribute to about 40% of this photochemical smog. Now this is not good at all, right? Because wherever you have this smog prevailing, especially people who have respiratory problems, right? They face a very difficult situation, right? They have to wear masks so that those particles don't get in and so on. The gases are not affecting them for breathing troubles. So then, overall, whether it's in China, whether it's in US, whether it's in India, whether it's in UK, people have to devise ways in cars to reduce the smog, right? Okay. So what is this smog, right? Or what is this photochemical smog? So what happens is, let's talk about cars which run on petrols and diesels, right? So nowadays it's the era of electric vehicles, where obviously we do not have to worry about this, and that's why electric vehicles are becoming so popular. But let's worry about the cars running on petrol. So what happens? The petrol burns, right? The engine burns the petrol, okay? Because the engine burns the petrol, what are the gases that are produced which are harmful? Carbon monoxide, okay? Also nitrogen oxides. Now if you look at this, at a very high temperature, because the engine is running, the temperature is very high, nitrogen can combine with oxygen to give nitrogen dioxide. Now those things can break up. So nitrogen dioxide can break up under sunlight to give oxygen. This is what? Atomic oxygen. This is not molecular oxygen. This is atomic oxygen. Now being atomic oxygen, what do you immediately make out of it? It is very reactive. It will react with the atmospheric oxygen to give rise to what? ozone. The ozone itself will react with many unburnt hydrocarbons, correct? And to give rise to many other substituents of the photochemical smog. And because of this, what happens is all these contribute to your respiratory distress. You might be having respiratory problems. Okay? Hence, governments had to step in to figure out, is there a way to reduce the causes of respiratory distress, which is your gases, the toxic gases, as you said. That is why they developed something referred to as catalytic converter. Okay? Now, having said this, what do you think would the catalytic converter do? Obviously, it will convert. Because it is the catalytic converter, it will be having a catalyst. That's where I'm going to. But before that, what does it do? What does it convert? What to? You said carbon monoxide, which is toxic. Correct? Okay. So carbon monoxide would be converted to what? Carbon dioxide. You would also be getting water vapor. What will happen to the to the oxides of nitrogen? NO, NO2 and others? Now they have to be reduced. So you have, in one case you have an oxidation, in one case you have a reduction, correct? So realize your catalyst should be so designed that it not only oxidizes carbon monoxide to carbon dioxide or soot or hydrocarbons to carbon dioxide and water, but it also reduces what? The poisonous oxides of nitrogen to nitrogen only, correct? So how do they do it? The catalytic converter now has two major parts. One is an oxidation catalyst, one is a reduction catalyst. So if you look at this, this is where it reduces what? The oxides of nitrogen. What is the catalyst you have out there? It's rhodium. It's rhodium, right? What about this side, where you're doing the oxidation? You have platinum and palladium. Okay? So every car in its catalytic converter would be having, right, a certain combination of these to ensure that the gases you breathe or the gases that are sent out from the exhaust of the car are not as poisonous. And the better you're able to do it, the better is the nature of gases coming out and less toxic is your environment, right? Have you seen, you must have read in newspapers or governments coming up with these protocols of doing these pollution certificates of cars? You know, what do? They measure the amount of carbon monoxide that is being spit out of your car, right? They measure those extent of poisonous gases and then they tell you whether you need to replace your catalytic converter or you need to go for your car servicing and so on. So it is extremely important to understand that these three metals, platinum group metals, help in maintaining a safer environment, a safer air. Okay? Now also let me share with you this. Having said that these are the three main metals out there catalyzing your stuff, just a moment. The catalytic converters have been one of those components in the car which has been stolen. Why is it so? Because the metals they are using are quite precious. They are expensive. Now do not think that the thieves who are stealing the cars are going to steal the catalytic converters and do some chemistry in the labs. No. Right? They are going to sell those metals for some quick monies for whatever purpose they are doing. Okay? So one odd day, you might find, if you have a car, you might find your car is not, your catalytic converter is not there. That means you go to your pollution check. The pollution person says that it's too high a pollution and you see your catalytic converter is not there. Then you might realize that I might have come over there and taken the catalytic converter away. Okay, but this time it was for a noble cause to do some experiments. But anyway. So the catalytic converters are very, very expensive. Very expensive. They are about 50,000 a piece depending upon what car you have, what extent of those catalysts you have inside. And so on. So this was something that probably you would know that it is there, but it is every day it is helping you in maintaining a cleaner environment, at least trying to. Now let's talk about something in terms of chemical kinetics. Okay, how many of you have gone through chemical kinetics? Have you gone through you know what chemical kinetics is? How fast or how slow a process happens? Okay, what are the different orders of reactions that you can get? Zero order, first order, second order, and so on. Correct? Have you guys done that or no? Not yet. Okay. So let me skip this then. Let me go to this part. So one was chemistry as a catalyst. Now this is chemistry for your safety. Now that was environmental safety. Now this is a little bit different. Along with the catalytic converters, nowadays you will see it is becoming mandatory for all the cars to have what? Airbags. To have what? Airbags. Now what are airbags supposed to do? Airbags are supposed to prevent you from serious injury if a collision happens, correct? So let me try to play a video for you. So let's look at this, okay?
It is a big engineering challenge to bring the human body to rest from a high speed in a time duration of 100 milliseconds without causing much harm to the body. Let's learn about this life-saving technology by understanding the mechanism of airbag inflation, which interestingly happens thanks to a chemical explosion. Seatbelts are supposed to hinder the movement of a human body. However, during accidents, such seatbelts exert huge force on your chest area and can cause internal organ injury. To avoid this huge force on the chest, modern seatbelts slightly release the seatbelt with the help of a torsion bar. This action makes the upper body slightly move forward, but once the torsion bar is done with the belt release, the upper body's movement is arrested here. Let's pause here and analyze the physics of the accident in detail. Please note that the seatbelt arrests the motion of your upper body, excluding your neck and head. When only your upper body is arrested and the neck and head are not arrested, you can guess what will happen. The head goes in a perfect pendulum movement in a high-speed accident. The devastation can be horrific, even with the seatbelt. This is why engineers came up with the idea of airbags. Airbags have a cushioning effect and at the same time prevent you from hitting the dashboard. The very first attempt to inflate the airbag using a compressed air arrangement was a failure.
So I'll stop here. So you understand the principle, you understand basically how the airbag is working, right? What it is doing. I've not told you the chemistry behind it as yet, right? Now let's think about the chemistry. See, what is the airbag doing? The airbag is getting inflated, right? After a collision. So what are you going to have? You're going to have, so after the collision happens, how would the airbag get inflated? The car has to understand that there has been a collision. So there has to be a sensor, correct? Now the sensor senses that and sends the information to something. There is a certain chemical compound, I'll share with you very shortly. That chemical compound, because of that sensing information, by the mechanism that is in place, gets ignited, right? On ignition, you see, the airbag has to inflate. What does it mean? There has to be some gas inside, okay? So in this case, the compound dissociates, the gas comes out, the airbag gets inflated, right? And prevents you from having a serious injury. Now, having said that, does anybody know what compound is used generally? Okay, so the gas is nitrogen. Let me give you that. The gas is nitrogen. There is about 70 liters of nitrogen, give and take a few, for any given airbag. And the compound that is used is sodium azide, mostly which has been used, but it has been done away with for certain reasons. So let's quickly look at that. So this is the compound. Can you guys see the compound? So the compound is sodium azide. What happens when sodium azide breaks? Decomposes, It goes into sodium and nitrogen, correct? So nitrogen is the one which is inflating your airbag. Now realize, guys, I cannot have any discriminate amount of sodium nitrite out there. I have to have a measured amount. Why is that so? Because the nitrogen that is going to get released and inflate my airbag also has to be measured because of that, so that because of that inflation, I do not get hurt myself. Number two, if you would realize from the video, when the person hit the airbag, that person got cushioned. Cushion means the airbag got inflated and then it started deflating again. Now, if it remains inflated, then what is going to happen is, because it's inflated, right? So it is pretty solid. You can get hurt. So the moment you impact, then that gas that was released starts getting out through certain vents. So all these mechanisms are put in. Now, this is how an airbag is working. You have nitrogen, you have a certain amount of nitrogen. That's why you start with a certain amount of sodium azide. This is a very easy chemical problem. You can figure out, to get 70 liters of nitrogen, how much of sodium azide should I be starting with, okay? But there is a problem with this. Can anybody say what the problem is? Look at the first reaction. What is the problem? Sodium. Why is sodium a problem? Good. It is highly reactive. So what is going to happen is, if I do not have anything else, you forget the other reactions right now. If I do not have anything else in the mixture, what is going to happen? The sodium is going to react with, correct, atmosphere. It is going to explode, burn, and you're going to get hurt because of the airbag. So what people have done is, people have put in other compounds, like you can see, potassium nitrate, so which gives rise to silicates, glass type substances. Now these silicates reduce the impact of sodium exploding and just make sure that you do not get hurt from the explosiveness of sodium, okay? But just nowadays, to avoid this, what people have started using is a material which is more benign. That material is gonadium nitrate. It is less expensive. It is not that toxic, right? And when it decomposes, you see, you do not have any of those elements that you have to worry about. Now, listen, when you're looking at this, a lot of research has already gone into this, correct? This has been researched from 1940, 50, and so on. So a lot of other compounds have been used. You know, one of the compounds which was used in between was ammonium nitrate. Have you heard of ammonium nitrate? What is it used for? Explosive? It is actually also used as a fertilizer, right? Because of the high nitrogen content, correct? Okay. Now, ammonium nitrate, as somebody pointed out, is also a part of explosives. So a certain company actually used ammonium nitrate. Now, what happened? Let me share with you what happened. You see this? I'm not sure whether you guys remember, this is a very recent phenomenon. In 2020, in the year 2020, August, in Beirut, there was a huge explosion, right? And the explosion happened because in a warehouse, they were storing about 3,000 tons of ammonium nitrate. 3,000 tons of ammonium nitrate, okay? That ammonium nitrate, it was sitting there for a long time, probably because of some sparks from a neighboring unit or company or whatever, factory, they burnt fully. Now, what was the impact for this? Impact was not only in terms of the number of people who got injured or killed. Impact was, next to this was a grain silo. Grain silo means where they would store food grains. They lost about 90 to 95% of the food grains. There was a huge mess. Now, the reason that I was going to discuss this with you was, one of the car companies, without realizing this, actually used ammonium nitrate. Why? Because they thought that per molecule of ammonium nitrate, I'm going to have more nitrogens coming out because it is rich in nitrogen. But then what happened was, later they saw that this ammonium nitrate started exploding because it was getting exposed to the atmosphere and so on. And that company actually got bankrupt. They could not proceed with that, and the company just fell out of the window. Okay, guys. Baby diapers, have you seen? What do baby diapers do? They absorb the water. They absorb the water. Do you know typically how many times the weight of the compound there is that the diaper can absorb water? 10? Arey nahi. 10 is too small. No, you have to send 1,000 times, 2,000 times, tabhi kuch milega na. Well, it is about 300 to 500 times, about 300 times. Right? It absorbs. Do you know what compound is used? Oh, this is chemistry, guys. This is simple chemistry. Nothing high-fun about it. So the compound that is used is a compound called sodium polyacrylate. Is a compound called sodium polyacrylate. It is a polymer. It has many negative charges coming from carboxyl groups. Each of those negative charges are associated with sodium ions. It is obtained as a powder. You take a certain amount of it in the baby diaper, and then obviously you have other layers, right? So that the baby diaper does not soak through fully and touch the skin of the baby. Correct? Now let's try to look at this video. Okay, so look at this carefully. This is actually fun.
So what happened to the water? Was it magic? No, there is no magic. Magic's not real. Turns out what you saw was thanks to a magnificent chemical invention called sodium polyacrylate. All right, let's try that again, except with a little bit more truth. Here's my magic trick. I've got about a gram of sodium polyacrylate. It's a polymer which can absorb water. Keeping track, it's about 50 grams of water. So far it's absorbed about 50 times its weight. There's a little bit over 100 milliliters or 100 grams of water. Let's keep going. Take a look at that. 200 times its weight. Starting to become kind of liquidy, but we give it a little bit of time. So let's talk about the structure.
So you understood what happened. You started with this very small amount of sodium polyacrylate, right? How much water did it absorb? Huge, yeah, huge. Huge. Imagine a compound which is so small in quantity, right? Because you cannot use a huge quantity, otherwise the diaper itself will be very heavy, right? You use a small quantity, and that quantity is able to absorb so much of water, right? Okay. Now, this is something, the structure you can look up. I'll not discuss the structure out here, but it is essentially what is happening is the sodium ions were solvating your carboxylate anions, okay? Now when water comes in, you have many waters, water molecules are better hydrogen bonders, then what do? The hydrogen bond with what? The carboxylate anions, and they displace the sodium ions out, okay? Now let's reverse it. What if I have to release the water from the gel-like sodium polyacrylate which has already absorbed 300 times more water as compared to its weight? What should I do? See what it does. You see some salt out there? That's just salt, sodium chloride.
Polyacrylate, which by the way, now that I've let it sit for a while, I can turn this thing, despite it being mostly water, I can turn that thing straight upside down for a while. Now let's talk about what happens. And by the way, you can probably don't want to touch it too much. Anyhow, let's see what happens. This is pretty gelatinous. Now I'm going to go ahead and I'm going to introduce more sodium ions with just some old table salt. And after a while, this thing goes back.
What did you see happening? The water got released. So if you add more sodium chloride, more water will be coming out. Why so? Now because you're putting in more sodium ions, it will start replacing the water molecules. So the water molecules are coming out. So it is not only a good example of how much it can absorb, but you can also release the water which was absorbed, isn't it? Okay. Let's see what we have next in the bag. So this is acrylic acid and this is the sodium polyacrylate. Okay, if you want to look it up, please do. Right, let's talk about this. Have you thought about chemistry being used in forensics? How? Okay, let's take a look at this. You see, on the left side, this is a criminal scene. Okay, some crime has happened. Possibly blood is spattered. Okay. On the left side, the leftmost picture, you see the carpet where somebody comes in, say the forensic analysis, the analysts, they come in and they look at almost a clean carpet. That means to us novice people, it would seem that, there are no blood stains, nothing has happened out there, we cannot get anything from there. But then they take a magic potion out of their bag. And what do? They spray that potion. Once they spray that magic potion, what happens? You start seeing pattern, you start seeing footmarks. There is a fluorescent light that is coming out. Does anybody know what compound is used out there? Well, hydrogen peroxide is already there, but there has to be some compound which gives this light. Anybody? So it is called luminol. It is called luminol. You know what happens to luminol? If you see the side, the bottom reaction, what is happening out here? The luminol comes in contact with the blood. What does blood have? Why is blood red? Hemoglobin. Okay. What is the metal you have in hemoglobin? Iron. Correct. Metals act as catalysts, right? So this iron will also act as catalyst. Now, as somebody said, you already have in that magic mixture, along with luminol, you have an oxidizing agent, which is H2O2. So what is the iron going to do? Iron is going to decompose H2O2, release oxygen. The oxygen is going to go and oxidize luminol. Now what happens is, once this oxidation happens, let's not worry about the reaction, but once this oxidation happens, the luminol goes to a very high excited state. So it goes to a certain intermediate, like a transition state, which is of very high energy. Because that energy is very high, now what happens is it has to lose that energy. So how will it lose that energy? It loses the energy by giving out photons, right? And this is why it is called chemiluminescence. A luminescence which is happening because of a chemical reaction, not because you're supplying photons from outside. Okay, so this is the principle of chemiluminescence. That is essentially your first step towards detecting whether I have any trace amounts of blood present in a crime scene. This is just one example. Okay, now let me show you a video with regards to this, and then I'll discuss with you. Or let me this one. Okay, so she will be having 3 small vials. One vial will be having only water. One vial will be having a little amount of blood, and one vial will be having more amount of blood, right? She is going to add luminol. She is going to add luminol, which is here. She is going to add luminol, and you see what happens.
We're going to see if that works now. So I'm going to add some luminol to some tubes here. Now I have this one, which has about 50 microliters of blood. I have one that has less. We can compare. And so we have this one has 20 microliters, so it's significantly less. And I also have some water, so we can compare, so we can see how it all works out. We'll use that as our control. And so I'm going to add, I'll open them all up at once, just easier that way. Hold them like this so you guys can see what I'm doing. And I'm going to use a pipette to add my luminol. There we go. So I'm going to collect some luminol. Give it a little shake first. There we go. All right, so I'm going to add the first one, which I believe is the control. Add it to my second one. I'm going to add it to my third one. Okay. Close them. All right. The middle one is the one with a little bit more blood. Do you mind? It's a little bit, tiny bit brighter.
Do you see the light? So this light which is coming out is called luminescence. Luminescence means what? It is giving out photons, light. It is giving out photons. Do you realize that, it's difficult though, but do you realize that both of these have a little different shades, intensities? Why? Because one had more blood, one had less blood. And obviously the one which had more blood would be giving rise to more intensity. Is everybody clear about this? Here the application of a chemical compound in doing chemical luminescence. Do understand, this is a cold process. Cold process means you're not hitting with anything outside. You're just putting a a mixture in. That mixture generates something which is a very high energy intermediate, and that energy, when it comes down to the ground state, that energy, excess energy, is being given out in terms of photons. Okay. Now, what does this mean? It means that in nature we have a process which is known as luminescence by itself. Has anybody heard about phosphorescence by any chance? Has anybody heard about fluorescence by any chance? Okay, have heard about fluorescence? So what happens? So this is a typical process. In the process, what is happening is, if I just introduce you to this, this is a very important process which is one of the most widely used techniques in terms of sensing throughout the world. Okay, so keep this in mind. So what I have is, I have my molecule in its ground state. Okay, so in the ground state, it has, this is its ground state, S0. Don't worry about S, it's called singlet. This is the ground state, 0. Okay, now what happens is, if it absorbs photons, it goes to higher states. This excess energy, if you look at this S1, the excited state 1, this excess energy which the molecule has can be given out in many ways. One is in terms of photons, which is luminescence or fluorescence or phosphorescence, and the other one is in terms of no photons, which is just heat or thermal. Okay, so the one you saw was an example of this excited state losing its excess energy in terms of giving out photons. Okay, but realize though, here the difference is, I'm seeing an absorption, but there I do not need any photons. I am not using any photons. I'm just essentially using the chemical reaction to give rise to this excited state, after which the photons are being emitted. So this is where the beauty of chemiluminescence, the beauty of chemistry comes in, to help you sense or detect something which are not visible to the naked eyes, because our naked eyes do have certain limits. Okay, so all of you have used glues, right? Gums and all these things, right? Ever wondered how does it work? Okay, let's see. What are the typical types of bonds that you know? Typical types of bonds. Hydrogen bond, okay. Ionic bond, covalent bond, anything else? Van der Waals, right? Van der Waals forces. So, do you remember what is, how does the Van der Waals, what are the Van der Waals forces, the distance dependence? So, if I have two molecules or two species exhibiting Van der Waals forces, how close or how far they should be? Any ideas? Okay, let's not go there, fine. So let's move on and see. You have used Fevikwik, right? All of you have used Fevikwik. Ever care to look up what is there inside Fevikwik? It makes it a very good glue. See, Fevikwik is a problem. If I have it on my hand, it is very difficult to knock it off. Very difficult to knock it off, okay? So see, how does the super glue work? This is a special class of compounds called cyanoacrylates. Special class of compounds. What happens is when you put this glue, even a little bit of water can give rise to this nucleophilic reaction, and then it ends up polymerizing. Polymerizing ka matlab kya? What do you mean by polymerization? You have this glue, you take it out, in the glue, what you have is you have just monomers of this cyanoacrylate. The moment you add, what happens? It gets exposed to water. Once it gets exposed to water, what is going to happen? You're going to have a chain polymerization. And because you have a chain polymerization, you will immediately see that liquid you have has become cured. Cured means gel-like, right? And that curing helps you bring about a huge adhesive strength. So this is how, again, a simple chemical species, right, exhibits an adhesive type action just by exposure to water. Your Fevicol, which is the previous version of Fevikwik, also has a similar, but it is not cyanoacrylate. Otherwise, it would have been Fevikwik by itself. It is something else. You can look it up. And I'll end with this. This is one of the fascinating stuffs which is still ongoing. This is, people are doing more and more research on this. Our own Professor Ganguly also does something in that direction. Not exactly though, but something in that direction. So, you know what OLEDs are? You know what LED is? Light emitting diode. What are OLEDs? Organic light emitting diodes. Now, what does organic mean? Yeah, I'm not talking about organic food or anything. I'm talking about organic molecules. Yes, I'm talking about organic molecules with all its, sigma bonds, pi bonds, whatever, double, triple, and so on, right? Now, these OLEDs, there are television displays nowadays which are built on not LEDs but organic LEDs. What does it mean? That in the LEDs, you have put in organic molecules. Okay, so let's see the construction. Again, without going into the details, this is what you have. So you have a cathode, you have an anode, because you have to have an electrical circuit maintained. So this is called electroluminescence. By given an electric field, I'm getting photons out, right? Then I have an electron injection layer and a hole injection layer. So if you take an electron out, what is going to happen? The electron will go out and you'll be having a vacancy, which is what? Positive, electron is negative. So this is hole, this is negative, right? This is electron. Then you have an electron transport layer and a hole transport layer. At the junction of these, you have an emissive layer. This emissive layer, in this emissive layer, you have all your organic molecules, okay, out there, okay? This emissive layer is made of all the different types of organic molecules. So essentially what happens is, in the emissive layer, this electron and hole, they recombine. When they recombine, then they give out light, color, and that's exactly what you see through the organic molecules. So what are the different organic molecules? So these are the different, see, look at these organic molecules. Have you come across these complicated organic molecules? No? I'm sure you have not. But then these molecules are being designed, and more such molecules, more and more research groups are working on design of better molecules. But the question is, how does it work? So realize, without going into the details, once I send an electrical circuit, the electrons that you see are injected into the excited states or the higher excited states of these organic molecules. Now what happens? This is a very important thing, a very innovative thing. This is my ground state, as I told you. This is my excited state. First excited state, second excited state, right? Now what happens is, because of that electron injection, my first excited state gains an electron. Now that first excited state then undergoes something referred to as a spin inversion or spin conversion, okay, to something referred to as a triplet state. S stands for singlet, T stands for triplet, okay. So if I have two paired spins, what is the spin on one electron? Plus of, what is the spin on the other electron? Minus of, what is plus of minus of? Plus of plus minus of is 0. There is something referred to as spin multiplicity, which is 2s plus 1. So what is the spin multiplicity? S is 0, it is 1. That is why it is called singlet. What about triplet? If I have plus of, what is the total spin S? 1. Then what is 2s plus 1? 3. That is why it is called triplet. You understand? So singlet comes from 1 state, triplet comes from 3, because you have that spin multiplicity. Now what happens is, you know how phosphorescence happens? Your fluorescence, that means from here, the system shifts to the triplet state, and the triplet state then relaxes to the ground state, and when it relaxes to the ground state, it gives out photons in terms of phosphorescence. But what is happening out here? This is something referred to as a very advanced thing. It is called thermally activated delayed fluorescence, TADF. So T stands for thermal, A stands for activation, D stands for delayed, and F stands for fluorescence. Now just let me end with this. Fluorescence always happens between a singlet state, that means S1 to S0 mostly. Phosphorescence happens between triplet to singlet, okay? Now when you have a delayed fluorescence, what it means is the electron that was out here, it goes and spends some time in the triplet state. This is called inter-system crossing. Why is it called inter-system crossing? Because you have crossed from one system, which is a singlet, to another system, which is a triplet. Now what happens is the same system comes back to the singlet state, from the triplet to the singlet. Once you are there, then it gives out light, and because it has gone to a certain place and come back, it is taking some time to give out the photons, and that is called delayed fluorescence, because the fluorescence is delayed as the system spends some time in the triplet state also before it comes back to the fluorescent state. So this, with time, you will see a lot of these LCD screens, these LEDs will be replaced by these organic LEDs. Why? Because these organic LEDs, you know, what makes these organic LEDs so, these organic molecules so preferred? What do you think? You saw the structures of the organic molecules. What do you think? What is the special thing out there you see? No, not exactly. I have to synthesize them. But in the structure, what do you see? Branching and conjugation. We have a lot of what? We have a lot of pi electrons. So you have no scarcity of electrons. Those electrons can make transitions from back and forth. And this is why it is so easy to have those organic molecules which can conduct these electrons. So the concept is not new, The concept was given. So these are like organic molecules or molecules which are conducting. In the year 2000, 3 scientists, one was Alan Heeger. They got a Nobel Prize because of figuring out or working on, conducting molecules. And this is the development of that. This thermally activated delayed fluorescence. As you will see, when the next time when you go to buy a TV, or your friend goes to buy a TV, or somebody else, just ask what the screen is, what the display is made up of. It just might happen that it will be organic LEDs. Okay. So I think I've run out of time. I'll end here. Having said this, I'll just, want to share with you that chemistry is not about writing reactions. Chemistry is not about, pushing arrows back and forth. Chemistry is all about realizing what those molecules can do for you. The molecules are there for a certain reason. We have gone through some examples. There are many other examples which we have not gone through. For example, just to give you another sense, you have heard of fireflies, right? The fireflies which when they fly around, they glow, correct? So like this, you have seen this? Okay, because I've run out of time, I'll not go into it. But have you ever wondered what makes these fireflies glow? Ever wondered? Again, there's a beautiful piece of chemistry. Only in this case, there is not chemiluminescence, but this is bioluminescence, because it is being brought about by a biological molecule, which is an enzyme. Okay, so guys, be excited about chemistry, have fun with chemistry. It's not about rote learning, but it's about understanding how to go ahead with chemistry. It is full of fun and full of excitement. Okay, thank you guys for your attention.
Thank you, Professor Ramit. Now, I thank both the speakers for keeping to time so that now we have a lot of time for interaction with the students. We'll open up the interactive session. I request Professor Bhaskar to also come up on the stage.
Bhaskar, आप वो वाला mic ले लो. I'll speak from here. तो नहीं सुनिए. अरे ओके कर ले.
Okay, so now we'll have the interactive session. If you have questions, please feel free to raise your hands, and there are volunteers who will come around, give you a mic. Please specify who you have question for, and our colleagues will be very happy to answer. Okay?
यहाँ से कैसे बोलें?
Oh, you want to stand?
I was going to stand here. That's easy.
Okay, we can start. There are questions here. Yeah, okay. Please tell us your name, your school, and then ask the question, okay? Yeah, okay.
Excuse me, sir. So my name is Gyanesh Ranjan Behra. I'm from class 11 Science Maths from Army Public School, Gopalpur. I have a doubt from Bhaskar sir from IIT Delhi. So my doubt is, how can we consider all the particles as one particle in superposition, sir?
Sorry, can you repeat what is the question?
So how can we consider all the particles as a single particle in superposition in quantum mechanics?
No, all particles are not single particles.
No, so
what we are saying is that every quantum object before measurement is actually everywhere. And only the measurement which tells you that where exactly it is. So it is not localized in space. It's like wave, you can say. It's everywhere. The moment you make a measurement, it collapses to that particular position with a certain probability. So it's not that all particles are everywhere. Particle, the quantum object, we don't call it particle. It's a quantum object. It's both particle as well as the wave. It is showing both the properties depending on the measurement. So as I mentioned, you cannot visualize it because our visualization is inspired by the classical thinking, you know. Yes. You cannot think in terms of those that something is everywhere.
Exactly. Yeah? Okay, thank you so much, sir.
Okay, so I would request all the students to limit at least in the first round to one question so that we can give chance to as many people as possible, okay? If there is more time, then we'll come back to second rounds of questions.
Good afternoon, sir. My name is Vidyashri Sahu and I am from OAV Karapalli. My question is that if in near future there will be a World War III, by using the quantum warfare, how destructive it will be in the comparison of previous warfare?
So can you locate where you are?
Right here.
Oh, I see. Okay. So what was your question? If there is World War III?
In the near future, by using the quantum warfare, how destructive it will be in the comparison of previous World War?
How it will be in the comparison of previous World War? See, what we say. See, first of all, world wars are something which should be stopped because nowadays we have so deadly weapons. You know about atomic bombs, we have hydrogen bombs, we have everything to destroy the whole world. So everything is nowadays controlled with information. You know, we talked about informations. Everything is controlled with information. So what people predict is that if there is a world war, it's based on the information age. So you are essentially hacking the information. If somebody hacks the information, you cannot communicate with. For example, these nuclear bombs, they also use some nuclear codes. You must have seen some movies, especially MI, Mission Impossible or many other movies. They talk about nuclear codes. You know, these are the passwords by which you can actually activate any nuclear bomb. So if that code is taken by somebody else, you can understand that the results would be devastating. So everything is now associated with information. That's why what we believe is that the World War III will be with an information age where everybody will try to hack the information, and hacking the information will lead to hacking the resources, like any of those destroying weapons basically.
Thank you, sir.
Just information to our own volunteers, there are some hands up at the very last rows. Yeah, please go ahead.
Good morning, sir. So I'm Saloni Patnaik from DAV Barampur. So, sir, I have a question that how does quantum computing help in producing new drugs?
New drugs. See, when we talk about new drugs, we need to basically handle molecules. You know, there are long chain molecules, polymers, everything we talked about in the chemistry lecture recently. So now you have to simulate first using those resources, your computational resources like computers. You have supercomputers nowadays. So you simulate first that what kind of drug would be made and what will be its outcome. That simulation requires handling proteins, handling molecules, which are very complicated and long time taking simulations. So when we talk about computers, quantum computers, these time taken by these simulations would be very, very small. Probably you can do more complex simulations with very shorter time. Then your results, you can actually try many, and whatever is successful, you can make finally products out on that particular outcome. So quantum computer is not making any product. Remember that when we say that it will produce something, it doesn't mean that it will go into the lab and make a drug for you. No, it will give you the outcome which essentially a person or a machine has to make in the lab. Okay?
Okay.
Yeah.
Sir, one more question. Can you explain about quantum correlation again?
So I don't have slides now. So I talked about generation of photons. If you remember, there is an experiment where with a laser beam, a crystal was shined and then you are generating those photons.
Yes.
So essentially what is happening that a particular laser photon coming from a laser beam divides into two photons. The laser beam has a high energy. It converts into two low energy photons which are generating exactly at the same time. So wherever they go, since they are generated at the same time, they are always correlated. So these kind of correlations which are because of the generation are not possible classically. Now whenever you take these two photons, you take them any distance, since they are always correlated by their birth, they will always show these quantum properties. So that we talked about entanglement and other things which are the next stage of that. But at the beginning, you need quantum correlations, and the process by which they are generated is the process which I showed you. It's a quantum process.
Okay,
Okay?
Thank you, sir. Sir, I have a question for Pramit, sir.
Too many questions.
Sir, why can't we use nitrogen gas for instead? Can't we use any other gas instead of nitrogen gas for that airbags?
No, you can. But then the air is a mixture of gases, right?
Yes.
So
sir.
where will you get that air from? It has to be very fast. So I did not, okay. I did not show one thing. You see, I'll tell you the response time. So the response time is about 10 to 30 milliseconds. Within that, the car has to sense, right? The sodium azide has to decompose and the nitrogen has to come out, right?
Okay.
What compound will give you that time? Because simple air, even if you have a compressed gas, it will be taking some time to come out. Nothing else. Right? But it is just the time scale that you need. Otherwise, you're already hurt by the time it is still
Yes, sir.
figuring out when to come out, when to inflate.
Thank you, sir.
Okay.
Good afternoon, sir. Good afternoon, sir. I'm Amrita from PM Shri Kendra Vidyalaya Gopalpur Military Station. So my question is for Pramit, sir. Sir, what difference would it create if I'm using an OLED instead of an LED?
Oh, okay. See, OLEDs, it's very easy for you to control because you know exactly what type of organic compounds are going in, right? And remember, the organic compounds are very rich in electrons. So now let me take a step back and think about this. All of you have cell phones, right? Now in your cameras, what do you see? These cell phones like, 13 megapixel, 64 megapixel, 128 megapixel. How does this help? Tell me, how does this help? The more pixels you have, what do you have? You have better resolution, no? Because the same information, the same picture, you are being able to grab using much smaller detectors. These pixels are small detectors, nothing else, right? So those small detectors, the more the number you have, the better you can capture or resolve the different colors. The same thing for the organic compounds. When you're using organic compounds, you see they're highly electron rich, pi electrons. So all those pi electrons will be available for you to do the processes off and on, off and on, off and on. So many repeat times, the simple LEDs will not be able to do that. They have their own discharge recharge process. And that is why the OLEDs give you much crisper pictures as compared to the normal LEDs.
So, but won't that be expensive?
OLEDs, well, today, as of now, they are becoming, see, anything to start with will be expensive. But with more and more research devoted onto it, it is becoming less expensive. It is much less expensive than it was before. But I'm sure with more advancement, it will be even cheaper than LEDs. Once people have a good way of figuring out how to process or synthesize these organic molecules in large scale. That's it.
Thank you, sir.
It is still a very huge research field, let me tell you that.
Good morning, sir. I'm Kartik Pradhan from PMC Kendriya Vidyalaya, Barampur. I have a question for Professor Kanseri. So in one of the slides that you have shown, it was written that unbreakable encryption it relies on physical principles rather than computational complexity. So what are the physical principles that it relies on?
Okay. So I think I explained physical. Maybe I can tell you what computational complexity means, and then it will be clear to you. So currently there are two kind of encryptions which are happening. One is the one which you use for example to make a transaction like OTP. This is called symmetric encryption. Essentially you get a password. The same password is used to encode and decode the information. The other kind of encryption is called asymmetric encryption, which is essentially used in your all internet-based communication. So what you do that since it's not, see, the problem in encryption is, suppose you want to communicate with me safely, you want a key, I want a key. A message you will encrypt with the key, you will send to me, I have the same key, I will decrypt. So the question is how to safely communicate the key to you and me. You have a key, how you will give it to me? Either I have to physically come to you or you have to send by some ways. And if you send it by some ways, anybody can in between take the key. So this is the problem. To solve that problem, there is something called computational complexity based algorithms, where they use something called RSA or many other kind of algorithms, where you take some computational problem as a key. For example, you know that factoring the product of large prime numbers is very difficult. If I take a very long digit prime number, multiply with other prime number and give you the final solution and ask, can you factorize it? A current supercomputer may also take hundreds of years to solve it. So what people do, people use these kind of computationally complex problems as the passwords basically, and they can be only solved if you know one of the solutions. So if you have a solution, you can easily decrypt it. For me, if I don't know the solution, I will take years or maybe hundreds of years to solve it. A quantum computer, since it is computationally very advanced, it can solve this problem in a fraction of a second. So all your internet-based communication is at risk once you have a quantum computer. And this is why we are using the basis of quantum computation, quantum cryptography, where we are not at all relying on any computational assumption. We are saying that no, there is no computational problem. We are using the same OTP, but we are using those quantum principles such as no cloning theorem or superposition to exchange the keys between us. And in quantum cryptography, when we communicate, after communication, we come up with a key. You will have a key, I will have a key, which will be identical and which will be distributed between us also. So we need not to send it to me. I will always get a key, you will get a key. So this is the solution basically. Okay?
Thank you, sir. I'm extremely sorry for the inconvenience caused, but I have another question for Professor Pramit. Sir, how does radium emit photons?
How does?
Radium emit photons. Radium, at the element radium.
Radium? Okay. So So you're talking about radium emitting photons?
It produces fluorescence. So how does it do?
So every atom has its own energy levels, right? So like the energy levels that you saw out here, right? Given the proper perturbation, what is going to happen is it is going to go to one of those energy levels, and then when it comes down, it will emit the photons within whatever wavelength it has. Any compound will do that. It doesn't have to be a huge compound. It can be a small compound, or it can be something which is just an atom or something. But the fluorescence or the luminescence is a key intrinsic property, right? It doesn't matter what you have, right? See, the question we ask ourselves is, like radium, would I be having many other atoms which will also give fluorescence? No. Why? The reason is, for radium, that is unique. The other ones, it can give photons, but then the other process, which is a non-radiative, that means does not give out protons, predominates. And hence, you do not see any light or very weak light. But in this case, it dominates. And that's why it glows.
Thank you, sir.
Good afternoon, sir. My name is Aniket Singh and I am from APS Gopalpur. Sir, my question is how a quantum computer will be so efficient in catching up random numbers if it's only known to you and me?
Can you repeat again? What was your last line?
Sir, my last line was how a quantum computer would be so efficient in catching up random numbers if it's only known to you and me.
No. So when we say about quantum computer, I think you are asking about cryptography, eh?
Yes,
that
sir.
how it will break the key or something like that.
Yes, sir.
which
How
we
it will break the key of the code between you and us if it's so safe to the internet, sir?
See, first of all, there are two ways to answer this. One answer I already gave to somebody where he was asking that how it is solving the computational problems. And I told you that since it's very fast, it's order of magnitude faster than any classical computer. It has some specific algorithms which only operate on a quantum computer. For example, there are Shor's algorithm, which is called a factorization algorithm, and there is Grover's algorithm, which is called a search algorithm. So quantum computer has a specific way to search out of a database. Suppose you have a random number, you say that, okay, I have a 5-digit random number. Classically, it will be searched line by line by a classical computer. But quantum computer has this Grover's algorithm which can solve or search this, which is exponentially lesser time than a classical computer. Similarly, this problem of breaking the codes, which I told and I answered him, there is the Shor's factorization algorithm where it again solves the problem with exponentially less time. So there are different algorithms for quantum computer, and both these search problems, which is basically about the OTP. Like OTP is a problem of searching, you try different ways and something, you guess different things and one of the guess fits. So that can also be done by one of the algorithms, and this factorization can also be done by the Shor's algorithm. So both can be solved. Yeah.
Okay, I know that there are a large number of hands up, but I have been requested that it is time to bring the session to a close. So we'll take one more question from a region where there have not been any questions. Your speakers are available over lunch. After that also, please feel free to talk to them after the session is over. Okay, so one last question.
Good afternoon, sir. My name is Bhavesh Panigrai and I am from Delhi Public Senior Secondary School. My question is to Pramit, sir. So we know that there are many exceptions, and if we see the case of diapers, then the sodium acrylate absorbs the water, and when we add NaCl, then it also regains its state. So that is only in the case of water, na sir. If we see urine, then there are also some amount of NaCl in it, and it is also kind of acidic. So how is it possible for the diaper to absorb it?
Oh, but it is not that high, you understand. So you have the sodium polyacrylate, right? Now think about the percentage of water you have in urine. It's huge, right? As compared to the concentration of sodium. If you do urine analysis, you will exactly know what concentration of sodium ions you have, right? So the water is too high. It's 70% body by weight. So even urine has a huge amount of water. So no matter that you have other elements which can coordinate with those, right? But still water is going to predominate and play its role. And obviously there it's going to increase in volume.
So, but we can also have exceptions, na sir.
Exceptions where?
In the urine case.
Well,
if the salt amount is more.
But it cannot be more than water. That's what I'm saying. So urine is what? The salt has to be dissolved in urine to come out, no? So your water is still a solvent. The solvent is a solvent, right? Yes, exceptions can be there, but then the problem is if you're starting to have exceptions, then you're starting to have something else. That means some ailments or diseases coming in. But water will always be there. So if you do not have that much of salt coming out, then by how much it increases in volume would be less, obviously. Okay, but water will still predominate because it's just the solvent. It is the one which is carrying all the things out.
Thank you, sir.
Okay, thank you everyone. We now have the pleasant task of bringing this session to a close with two little things that we still need to do, two little but very important things. First is a little token of thanks to both our speakers. I request Professor Bhaskar and Professor Pramit to join us. We now have some gifts for some of the students that the committee has chosen. There's a book and some chocolates. The names will be announced. I request you to come up on stage and receive them.
एक नंबर World War 3 era second टा कोटे हो ना Okay, so here are the 5 selected students who will get a small gift from our side. So the first name.
Okay, so before we announce name, so let me tell you, I mean, when you raise your hand, you are already a winner. Okay, when you ask question, this is already a very big thing. Okay, so all those, I mean, 5 we have selected, but don't think that you didn't get it. You have done your job. You have done very good by asking questions. Okay.
So first one, Ganesh. And second student, Saloni Patnaik. So Saloni Patnaik from DAB Public School, Ganesh from APS Gopalpur. Third one, Ankit Singh, I believe Singh. Fourth one, Amrita Patra. And fifth one, Bhavesh Panigrahi.
Thank you all. And we would like to give special thanks to our session chair, Professor Prasad. And also we would like to thank all the speakers who made this session successful. And thank you all for your attention. We are going to have lunch now. And see you after the lunch at 2:30. Okay, please try to be here before 2:30. We are going to distribute you some sheets which will be useful in the next session. So please try to come a bit early. Okay, I hope you all are enjoying. Okay, thank you.
Which kind mania? Quantum mania, right? Okay. So good. So now we have two speakers. Professor Rajesh Prasad is going to talk to you exploring symmetry of periodic structures in phrases, wallpapers, and crystals. Symmetry, you know, you have seen petals, leaves, they have all symmetry. In nature, there is a lot of symmetry. So what is that science or mathematics of symmetry, and how many things you can discuss, which is very fascinating. So Professor Rajesh Prasad, he has 30 years of experience teaching material science at BHU, IIT Kanpur and IIT Delhi. He has been there for a long time at IIT Delhi. And he did his PhD from University of Cambridge, then his master's from ISC Bangalore. And his current research interest is on plastic deformation and anisotropic elasticity of crystalline solids. He enjoys teaching, and he is a very outstanding teacher of IIT Delhi and a very good friend. I know him from my student days at ISC Bangalore. He was junior to me, right? Okay, so welcome Rajesh.
वो जमीन पर सोने वाला तो बतला दो.
He has a lot of stories of sleeping on the floor in the hostel and all that.
No. बहुत तेज हो रही. Okay.
He will tell the story. So welcome Rajesh to this meeting.
थैंक यू. ज्यादा गूंज रहा है क्या? हेलो, ठीक है, आवाज ठीक है? Okay, thank you Ashok for a very nice introduction, for this invitation, and also to Dr. Patra for giving this opportunity to talk about a topic which is very close to my heart, that is symmetry. But let me first tell you a story of how Professor Ganguly said only that we know each other for a very long time. It's a long time friend. But the long time friendship, the initiation you should know. The initiation was that when I joined ISC as for MTech student, he had joined for PhD student, as a PhD student. Both of us did not get the hostel for a week or so. So both of us were sleeping on the floor of common room. That is what was provided. And the classes and everything is started. So from the trunk, we will take the books, go to the class, then again keep it in the trunk. So that is the first introduction with Professor Ganguly. So thank you for that nice opportunity God provided. If I was knowing that he is going to be director sometime, I would have taken more care of him that time, but that time I used to think as a common friend. So symmetry, one famous mathematics professor, Weil, he towards the end of his life gave a series of lectures which was converted into a very famous book, and the title is only Symmetry. And it's a very, very nice book, highly recommended. That's why I'm starting with that. And I'm starting with a quote from that. Symmetry is the central thing to comprehend and create order, beauty, and perfection. So very nice quote, very nice book. If you get time, please do look at this book. Then this lecture will be successful. Now, let me start with crystal. And if I ask crystal, what is the crystal structure of copper, a very common metal? Copper. You have studied crystal structure? No? Not yet? Anybody knows? Solid state is in? अच्छा हटा दिया, ठीक है. Very good. So now I will teach you solid state. So see, any metal which is actually is crystalline. By crystalline we mean atoms are periodically repeating in space. So if you look at copper, you can't look at the copper atom, but if you do X-ray and electron diffraction, you will find that it's a structure, we call it cubic close pack. By cubic close pack, we mean that it has a lattice, face-centered lattice. By face-centered lattice, we mean that if you think of a cube, face-centered cubic is missing there, face-centered cubic lattice, FCC. So face-centered cubic lattice, you have a cube, and at the corners of the cube and at the face centers, you have lattice points. And then you place atoms. And where you place atoms, you place one atom at each lattice point. You have a choice. More complicated crystals, you can place 2 atoms at each lattice point, n atoms at each lattice point. In Buckminster fullerene has the same cubic structure, but at each lattice point 60 atom football will be sitting. So it will be a much more complicated structure, but will still have face-centered cubic lattice. So the simplest face-centered cubic structure is the lattice with 1 atom motif, 1 atom at each lattice point. That is the structure. But in this lecture, we are interested in symmetry. So let me ask, what is the symmetry of the crystal structure? Symmetry of the crystal structure of copper. Now, this can be answered in a variety of ways. The simplest and the most simple answer can be there, symmetry is cubic. But by cubic, we mean only the crystal system, which is a partial information, a very, very partial information of symmetry. I told you it's face-centered cubic. So if you say face-centered cubic, that's also description of symmetry. And it is a little bit more detailed. It gives you the Bravais lattice and you have more information about the structure. That is, if I know face-centered cubic, I also know cubic. So, but I don't know further. And the further is more detailed, and the correct and the exact answer to this question is that symmetry of copper crystal is Fm3 bar m. Fm3 bar m. What is this beast? This is a space group. This is called a space group. So for any crystal, the final ultimate symmetry answer is what is its space group. So that's what gives you the complete information. But then how do I find what this space group Fm3 bar m means? Well, for that, there is a society called International Union of Crystallography, and they publish 7 or 8 volumes. Each volume is this thick and this big, too heavy, 3-4 kilos each volume. And the very first volume is titled Space Group Symmetry. So this whole book is devoted only to describing space group symmetry of the crystals. So I can look up this book to find out the meaning of Fm3 bar m. And you will see this confusing projection diagram. All symmetries are represented by projections. And this cubic symmetry Fm3 bar m has such a complicated and very scary projection. So to understand, to make meaning out of such symbols and such projections, one needs a little bit of patience, little bit of training, and little bit of thinking. Otherwise, it's only a geometric description of the symmetry of crystal. So, and there are 230 such space groups. So any crystal can fit into one of these 230 symmetries. So crystallographer's job using X-ray diffraction is to find out which of these 230 space group belongs to a particular crystal. So copper shows Fm3 bar m. Other crystals will show other space groups. And for each space group, there are details like that, which I showed you for Fm3 bar m. That's really, really mind-boggling. And is something which cannot be handled in a short lecture now. So let us come down. Let us come down from 3D to 2D. the central thing for the crystal and the 230 space group is that the structure is periodic. It is repeating. It is repeating in 3 dimensions. That's why you have a unit cell. That is the cubic unit cell. That cubic unit cell is supposed to repeat in all 3 directions to give you the crystal. So that is 3 dimensions. If we come down from 3 dimensions to 2 dimensions and talk of wallpapers and tilings, the essential thing here also is periodicity. Tilings, unfortunately, there is no I had imagined that I will show the tiling of my hall, but there is no, no tiling on the floor. So it's an amorphous floor, but crystalline patterns, tilings will have, yeah. So 1D, freeze, that will come in the freeze. So wallpapers and tilings, I have already given you one interesting example. And this example is from a very famous Dutch artist, Dutch graphic artist, M.C. Escher. What are you seeing in this pattern? Pattern is made up of what? Lizard, fish, and bats. Lizard, fish, and bat. Earth, air, and water. So, but the interesting thing from our point of view is the periodic repetition. A lizard pointing down is repeated here, pointing down. And hopefully, if the pattern continues, it will repeat again here. This is part of the pattern. In your mind's eye, you have to expand it both x and y direction to have an infinite pattern. So there is a repeating structure and you are seeing the repeat pattern. And whatever is the repeat pattern for this downward pointing lizard is true also for the downward pointing fish. And not only downward pointing fish, for this diagonal lizard also repeats by the same vector. So whatever translation you have for one component, one element in the pattern, that translation is not for lizard, not for fish, or not for bat, but for everything in the pattern. So this is the horizontal repeat distance in this pattern. Similarly, there will be repeat distance in other directions also, and you can find that. So there is a translational symmetry. That is the essential thing for a periodic pattern, and that is essential thing for a wallpaper or tiling. But then, apart from translational symmetry, do you see other symmetries? Do you see any other symmetry? Translational I showed you. Do you see any other symmetry in this? Symmetry you are familiar. We will define symmetry. Don't worry, but if you are already familiar, you can share. हाँ जोर से बोलो बेटे. हाँ triangular. What sort of triangle? Where are you seeing the triangle? Very good. Triangular symmetry. Maybe here, here, and here. A triangle is forming. So very good. Triangular symmetry. So we will see. So every pattern, suppose you had a simple square tiling. Will that show triangular? That will not show triangular. That will show squares. Square pattern. So one pattern differs from other in terms of symmetry. Now, if I am Escher, you should Google Escher actually, and you will find beautiful patterns like this. This is also downloaded from net. So Escher was master artist in doing periodic pattern. So much so that some crystallographer, Caroline McGillivray, wrote a whole book on teaching crystallographic symmetry using only Escher's patterns. So that's the kind of fascination Escher had for mathematicians and crystallographers. And another periodic pattern made of circular arcs, looks like Deepak. That's why it was created in Diwali. Yet another pattern. Now, the question is, are these patterns different symmetry or same symmetry? And how many different kinds of symmetry I can create? So if I am Escher, I can play not only with bat, fish and lizard, so many different creatures I can use. Flowers I can use, different motifs I can use, geometric motifs I can use. So you can have infinitely many different patterns, two-dimensional periodic patterns. But how many different kinds of symmetry they generate? Is that also infinitely many symmetry? The answer is no. The number is very, very finite. And number is finiter than the 230 for the crystals. It's only 17 plane groups, only 17 types. And I have, so for 230 space group, you require that international tables volume, 5 kilo volume, volume A. For this, all you require is one slide. And I have given you a copy for that. So these are the only 17 possible periodic patterns. Only you can make it of bats, fishes and lizards or with your imagination. But in terms of symmetry, it will be reduced to one of these. And the exercise I give you in this class for you, that which of these 17 fits the bat, lizard and fish pattern which you already have. So you have to explore the symmetry of the pattern and match with one of them. It's just simple matching. Anybody can do. Sorry? Oh, you have already solved it, I think. Very good. Very good. Very good. He deserves some chocolate or whatever. Yeah. So, so 3 dimensions से 2 dimensions में आए. अब 2 dimension में भी थोड़ा एक और reduction करते हैं. 2-dimensional wallpaper is repeating in 2 directions. What if I take a 2-dimensional figure but repeat only in one direction? अगर एक ही दिशा में उसको shift करते हैं, then what I get is called freeze. So 1-dimensional periodicity. Pattern is 2-dimensional. Letter A is 2-dimensional. It's drawn on a plane of paper. Okay, but I'm repeating it only horizontally. सिर्फ x axis की दिशा में इसको आगे बढ़ा रहे हैं. A. I am getting a pattern, and this already is a freeze pattern, and it should have one of the freeze group symmetry. Instead of A, if my choice is B, I get another freeze group symmetry by repeating B. The question is, if I keep repeating A to Z, do I get 26 different types of symmetries or limited number of symmetries? The answer again is limited. There are only 7. So 230 space groups, 3-dimensional crystal, 3-dimensional periodicity, 17 plane groups, and now only 7 freeze groups. And they have some standard international tables name, the volumes which I showed you. They're named like this. Conway, a mathematician, has given some interesting nicknames to all of them: hop, sidle, jump, we will see. And I have created an example list for you. And so this is a sort of answer also to what you have in the worksheet. What about freeze group? You are all familiar. 1-dimensional periodic pattern, you are all familiar, the sine wave. ये तो बचपन से पढ़ते आ रहे हैं. Sine wave, y is equal to sine x. So the very fact that y is equal to sine x is a periodic function. This itself is a periodic pattern in space, periodic pattern in 2D. So it should also have one of those seven freeze group, which I just showed you in the previous slide. So तुम्हारा काम अब फिर ये बना कि उन 7 फ्रीज ग्रुप में से साइन वेव कौन सा है, इसमें तो कोई साइन वेव है नहीं, बट द साइन वेव ऑल्सो शुड फिट into one of the 7 symmetries.
Excuse me, sir. Sir, here.
हाथ रेज करो.
Sir, the fifth one, P11G.
अच्छा हाँ उधर से बोल रही है.
Sir, the fifth one, P11G.
P11G. Very good, very good. We will come to it. So summary till now. 230 space groups, 17 plane groups, 7 freeze groups. So 7 is obviously the simplest, and 7 probably can be done in this 1 hour or 1.5 hour lecture. So we will focus on the 7 freeze groups. The other thing, if you understand well how the symmetry mechanics or symmetry mathematics is working for these 7 freeze group, it is easier to graduate to 17 plane group and then to graduate to 230 space group. So the beginning should be made with these freeze groups. But beginning can be reduced to even lower level. All these three-dimensional periodic pattern, wallpapers, crystals, wallpapers, and the freezes, all of them have translational symmetry. What about finite body? Isn't a square having a symmetry? A square doesn't have translation. If you translate a square, it will shift. So translation is not part of a square symmetry, but a square we know is a highly symmetric object. So for finite object, the symmetry is considered, and that is called point groups. So we will begin our exercise by the point groups. Now for symmetry, now we are defining symmetry. So alert, we are talking of symmetry, and vaguely, and we have identified translation symmetry and some sort of a triangular symmetry and things like that. But what exactly is symmetry? So first, to understand symmetry, there is a mathematical concept called isometry. In any symmetry operation, translation, I am moving from one point to the other point. I am thinking that points are moved. There was an initial point, and then I mapped it to some final point. So it's kind of a function. It's a point-to-point function or a mapping. And you can have all sorts of mapping, but there is a very special kind of mapping, isometry, which does not change distance. I have a square. I rotate the square. It's a mapping. Corner of the square which was here now has gone there. But will distance between any 2 points of the square change on rotation? No. So rotation is an isometry. So the question is, how many different kinds of isometries we can have? We will come to that. But isometry is not symmetry, but if the isometry maps the object to itself. Next level. First level, there should be a function, there should be a mapping which does not change distance, and if such a mapping maps the object to itself, then that mapping is symmetry of the object. We will see the example. So first of all, in 2D life is very, very simple. So in 2D, only 4 kinds of isometry are possible, and they are listed here for you: rotation, reflection, translation, and glide. Rotation, you know. So P is rotated about this center, which I have unfortunately not labeled. Imagine an O there. So P is rotated about O by an angle theta, so goes to P prime. Rotation does not change distance. P is mapped to P prime by a mirror line. So by mirror line, I drop a perpendicular from P, the distance D to the mirror line. Then I go to the other side, the distance D, to find the image. So all these are mappings which will not change distances. Translation, very simple, just shift by a vector T. P to P prime. Glide you may not be familiar, so pay attention to the glide. Glide is interesting symmetry that is a combination of reflection and translation. That you reflect first, but on reflection I am not putting an image point there. I am waiting. That is only half the journey. Reflection is half the journey. Then I translate further by some distance to get my image point. So reflection followed by translation parallel to the mirror line is glide. I have written the translation here T by 2. Why? Because if I simply translate by T by 2 P, I don't get a point there. So that's not, so T by 2 is not translation of the whole pattern. T by 2 is the translation inherent in the glide operation. The real translation of the pattern is T, because if I apply the glide again to P prime, I go to P double prime, again I T by 2 translate. So the total translation from P to P double prime is T. So capital T is the translation of the structure. T by 2 is the translation of the glide operation. Something about fixed point. Rotation leaves the center of the rotation fixed. So that's a fixed point. Mirror leaves, if I map a point on the mirror itself and reflect, I try to reflect a point on the mirror, in the mirror, what will I get? I'll get the same point. So that is a fixed point. So or the mirror line is fixed point. In translation, what will be the fixed point? Is there any fixed point in translation? I'm moving everything. I apply this vector T to all the points. Here only an example point is shown, but the translation, transformation or translation operation will act on all the points. And since it acts on all the points, there will be no fixed points. So no fixed point, and since glide also involves translation, there will be no fixed point. And there is an interesting thing about change of handedness. Rotation, if you have a left-handed and a right-handed object, rotation, left shoe and a right shoe. Rotation of left shoe will keep it left. Okay, but a reflection of left shoe will make it right shoe. So reflection changes handedness, rotation does not change handedness, translation again shift, so no change in handedness. Glide, since reflection is involved, again there will be a change in handedness. So these are with points. You can take much more interesting thing, for example the peacock, and apply the operations. So in the first figure, peacock is rotated by 90 degree. I am calling that image of, it's not really a left-handed peacock in the sense that we are left-handed or right-handed, but I am considering that image of peacock to be left-handed. On rotation, it remains left-handed. Reflection, left-handed becomes right-handed. Translation is just shifted, and the glide operation you can see. So these four isometries are all you have. This is the ingredient, this is the masala of your symmetry kitchen, with which you have to cook all sorts of symmetry. So let us start with the simplest. Let us start our education with A. What is the symmetry of A? Which isometry will leave A to itself? Reflection. Which reflection? Where? In which mirror line? Vertical mirror line dividing the A into two halves. So reflection symmetry, we also, so sort of synonyms, reflection symmetry and mirror symmetry, and it's about a vertical line, but there is a little bit of emphasis difference if you go into a little bit more careful thinking of symmetry. When you say reflection symmetry, reflection is the operation. When you say mirror symmetry, mirror is the line about which the operation is acting. So mapping and the line of the mapping, or mirror is the fixed point of the mapping. So reflection is symmetry operation, mirror line is geometric symmetry element. Now we come to the, so how do I describe the complete symmetry of A? Shall I give it a name? So since this is a point symmetry, since it's no translation is involved, so obviously its symmetry will be a point symmetry. I give it a name. Since it has a reflection, a mirror line, so for mirror M is a nice letter, I say letter A has point group M, has a single mirror. Letter F. Letter F has what? Yeah? Glide, I have to reflect it and translate it. But then I generate a new F here. At the moment it is not there. If I was having a pattern of F, I could have applied glide. But for a single one, I cannot apply glide. Translation also for a single F, I cannot apply. Translate, if I translate, I should create a new copy of F here. Where is that? It's not there. It's a single standing F. F grade. A grade, everybody was getting A grade. Now F, everybody is getting an F grade. Yeah? No symmetry. No symmetry is the answer. It's not necessary that everything will have a symmetry. It has no symmetry. But mathematician, just like if you have no money, that's a negative way of saying it. You can still say that you have zero money. So mathematicians have a name for no symmetry also. Instead of saying no symmetry, they say it has an identity symmetry. Identity. And they give a name, point group 1. So any object which has no symmetry, I'll say has a point group 1. Any object which has one mirror line, I'll say it has a point group M. H. Which reflection? Vertical, horizontal, both. Both. So you can see, already you are seeing that H is, I can now little bit more confidently claim that H is more symmetric than A. Okay. A is more symmetric than F, because I have now the tool to characterize the quantity of symmetry, because I am seeing how many different symmetry operations the object has. Is that all it has? Yeah? Rotation, yeah? Rotation by 180. If I totally turn it upside down, imagine A. If you rotate A by 180 degree, it will become an ulta A. उलट जाएगा ना. A ऐसे था, 180 डिग्री से घुमाया ऐसे हो जाएगा. तो क्या बन जाएगा? So 180 डिग्री रोटेशन भी है. 180 डिग्री रोटेशन को कहते हैं टू फोल्ड रोटेशन. ये नॉमेनक्लेचर है. जो भी डिग्री से घूम रहा है, 360 डिवाइडेड बाय दैट नंबर, 360 बाय 182. अनदर वे ऑफ थिंकिंग कि अगर H को रोटेट किया 180, सेल्फ कोइंसिडेंस, another 180, again self coincidence. So in complete one rotation, it will become self coincident 2 times. 2 बार ये अपने स्वरूप में आ जाएगा, H का जो असली स्वरूप है. अगर 45 घुमाएंगे तो 45 डिग्री टिल्टेड H है, वो सही नहीं है. 90 घुमाएंगे तो हॉरिजॉन्टल H हो जाएगा, वो भी सही नहीं है. 180 घुमाने से पता ही नहीं चलता है कि घुमा कि नहीं घुमा. अगर आंख पर पट्टी बांध दूं और उसके बाद 180 घुमा दूं, फिर पट्टी खोलूं, बोलो घुमाया कि नहीं घुमाया, क्या जवाब दोगे? बोल ही नहीं सकते. तो वही सिमेट्री का मतलब है. कैसे बोलोगे नहीं घुमाया? मैं घुमा दिया हूं. घुमाने के बाद भी तुम्हें पता नहीं चलेगा. मुश्किल ये है. तो वही सिमेट्री है. जब हमें ये मुश्किल हो, अगर आंख बंद करने के बाद वो ऑपरेशन दिया गया है और आंख खोलने के बाद मैं कह नहीं सकता कि ऑपरेशन दिया गया कि नहीं दिया गया, रिफ्लेक्शन दिया गया कि नहीं दिया गया, रोटेशन दिया गया कि नहीं दिया गया, तब वो रिफ्लेक्शन, तब वो रोटेशन ऑब्जेक्ट की सिमेट्री है। तो टू फोल्ड का भी एक नोटेशन है, इसको याद कर लो। एक छोटा सा लेंस बना देते हैं, जहां पर टू फोल्ड है, जहां पर 180 डिग्री रोटेशन का सेंटर है, वहां पर एक छोटा सा लेंस बना दो, तो वो टू फोल्ड हो गया बस। और इसकी अब इसके पास क्या क्या है, तो इसके पास टू फोल्ड भी है, एक हॉरिजॉन्टल मिरर है, एक वर्टिकल मिरर है, तो पॉइंट ग्रुप का नाम दे दिया 2mm। एक मिरर पॉइंट ग्रुप m, कुछ नहीं पॉइंट ग्रुप 1, दो मिरर 2mm। ओके, one more letter. Now this 2 which came is very, very interesting. In fact, this is not property of H. Any object, think of a rectangle, any object which has two perpendicular mirrors will also have this two-fold symmetry. This is the symmetry theorem. This is the symmetry magic. आप बना ही नहीं सकते हो, आप you can't have one variety of symmetry. I have only two perpendicular mirrors without two-fold. Give me a symmetry, give me an object which has two horizontal mirror, vertical mirror, but not the two-fold. Sorry, नहीं दे सकता. So दो mirror आया, तो दो mirror का combination, the horizontal mirror and the vertical mirror का combination अपने आप two-fold बन रहा है, इसलिए वो two-fold यहाँ पर है. अब इसको कौन बतलाएगा? n, दिस इज द लास्ट वन. n की सिमेट्री क्या है? रोटेशनल, 180 डिग्री रोटेशन, इसको भी 180 डिग्री रोटेशन. इसके सो A had mirror, H had two mirrors and two fold. Now n is different, it has only two fold. You can have just one two fold, that you can have, but you can't have two mirrors without two fold. Or if I try to put one two fold and a mirror, another mirror will also generate. So two fold does not require like one mirror, it always comes with two mirrors. तो चलो वो जो एक्सरसाइज है ये वर्कशीट में उसको कर दो. नाउ यू हैव एवरीथिंग. सो लेटर्स ऑफ अल्फाबेट पढ़ो, ABCD. फिर से प्राइमरी स्कूल में ले गया हूँ, अच्छा बात है ना. ABCDEFG HIJK LMNOP. क्या रिफ्लेक्ट करो, रिफ्लेक्ट करो. हाँ हाँ, तो इस डायगोनल में अगर रिफ्लेक्ट करोगी तो ये पॉइंट कहाँ जाएगा? यहाँ पर जाएगा. ठीक है, ये पॉइंट कहाँ पर जाएगा? यहाँ पर जाएगा. पॉइंट है, ये 45 डिग्री है, तो ये रिफ्लेक्शन में 45 डिग्री पर ही आएगा ना, तो यहाँ पर लाइन आएगा. सो रिफ्लेक्शन विल नॉट वर्क. यू कैन चेक दैट. बनाओ, इसमें सिमेट्री लगाओ सब में फटाफट. देखो किसका पहले कंप्लीट होता है. इसमें वर्टिकल मिरर बनाओ, वर्टिकल मिरर बनाओ, वर्टिकल मिरर बनाओ. यहाँ पर वर्टिकल मिरर बनाओ. हाँ, वेरी गुड, वेरी गुड. हाँ, वेरी गुड. ये तो तुम्हारा कंप्लीट हो गया लगभग. एस में वर्टिकल मिरर नहीं है, टू फोल्ड है. ठीक है, वर्टिकल मिरर में करोगे तो उल्टा एस हो जाएगा ना. दिस विल बिकम लाइक दिस, विच इज नॉट राइट. हाँ, टू फोल्ड, तो n को दिखलाया ना कि टू फोल्ड है n के पास, तो n इज टू फोल्ड। तो इस तरह से टू फोल्ड वाले कौन कौन से हैं? और हाँ, s भी है, वेरी गुड। बना रहे हो? हाँ, किसी को भी अगर कोई कंफ्यूजन हो पूछो। हाँ, सिमेट्री ऑपरेशन बाद में बतलाऊं। सिमेट्री ऑपरेशन वाला कॉलम छोड़ दो, वो कुछ ज़्यादा पूछ लिया। अभी सिर्फ लेटर्स, पॉइंट ग्रुप और लेटर्स कंप्लीट करो। बीच का कॉलम छोड़ दो, सिमेट्री ऑपरेशन। हाँ, इसमें बनाओ, मिरर बनाओ, तो ये लाइन बनाओ। आई वॉन्ट यू टू राइट द लाइन। तो मिरर का लाइन है वो दिखलाओ, कंटिन्यूअस लाइन दिखलाओ। यू यूज कंटिन्यूअस लाइन फॉर मिरर, डैश्ड लाइन फॉर ग्लाइड, क्योंकि ये तो पॉइंट ग्रुप है, इसमें तो डैश लाइन आएगा नहीं, सारे कंटिन्यूअस लाइन। हाँ, n अगर इसको इस मिरर में रिफ्लेक्ट करोगे, ओके, तो ये इस लाइन का सोचो, इस लाइन का ये पॉइंट यहाँ पर जाएगा और ये पॉइंट यहाँ पर आएगा, तो ये पूरा लाइन ऐसे आ जाएगा, तो वो उल्टा n हो जाएगा ना, दिस n विल बिकम ऐसा, so that is not symmetry. So this line is not a symmetry line for n. So n को 180 से घुमाना होगा, n को 180 से घुमाना होगा, तब वो 2/4 सिमेट्री बनेगी। हाँ, तो वो 1 में आएगा, वो 1 में आएगा, इसलिए f लिखा है ना 1। p1 में नहीं, वो जस्ट 1। p1 जब ट्रांसलेशन है, हाँ, p1 जब ट्रांसलेशन है वो फ्रीज ग्रुप में आएगा। आ रहा है? हाँ, करते चलो। n नहीं, n के साथ o मत लगाओ, o को तो तुमने दो मिरर दिया ना, और n के पास तो कोई भी नहीं, n को भी 2 मिरर डाल दिया। नहीं, n को तो मिरर है नहीं, ध्यान दो तुम, n के पास 2 फोल्ड है, so n, that's why n is a different type, and o will go into with h, o will go with h because it has 2 mirrors. हाँ, नहीं वही दोनों, ये h वाला है, जैसा h है वैसा ही आई है। h को पतला करते चलो, पतला करते चलो, और फाइनली दोनों मिल गया तो i बन गया, लेकिन सिमेट्री उसकी प्रिजर्व्ड है। हाँ, कौन सा दिखला रही हो? अच्छा नहीं, ये तो यहाँ पर लिखना था, लेटर्स ऑफ अल्फ़ाबेट यहाँ पर लिखो, सिमेट्री ऑपरेशन बाद में लिखेंगे। लेटर्स ऑफ अल्फ़ाबेट लिखो, P, L, Q, R सब ठीक लग रहा है, Z ठीक है, S भी आएगा इसमें, लेटर्स तो ठीक हैं तुम्हारे। ठीक है, अभी आंसर दिखला रहा हूँ, यहाँ पर आंसर दिखला रहा हूँ। देखो, सिमेट्री ऑपरेशन बिना बतलाए पूछ लिया। सिमेट्री ऑपरेशन, अब पॉइंट ग्रुप 1 वी सेड नो सिमेट्री, so no symmetry, it has only identity operation. Identity operation means doing nothing, so the only symmetry operation which point group 1 has is 1. 2 has 180-degree rotation, so it has 2, but 1 is always there. For all point groups, 1 will always be there, because doing nothing is symmetry of everything. Anything, if you don't rotate, don't reflect, don't do anything, will remain as it is. So 1 is a common symmetry operation for all of them. So for m, we have 1 and m. For 2 mm, we have 4. 1 is there, then 2 was there, and mx and my. So these are the symmetry operation column. And letters with no symmetry, letters with two-fold symmetry, letters with single mirror symmetry, That's the longest list. And letters with two mirror and a two-fold symmetry. So अगली बार जब मैम पढ़ाए कि दो इंग्लिश लेटर्स आर ऑफ टू टाइप्स, कॉन्सोनेंट एंड वॉवल्स, हाथ उठा के बोलना नो मैम, देयर आर 4 टाइप्स, 1, 2, M and 2M. Now when we talk of groups, we were using group without actually defining it. So here is the official definition. I don't want to worry too much about this, but any group requires these properties. That combination of two operations should also be another operation, closer. Identity you saw, all of them were having identity. So identity will always be there. So doing nothing is always a symmetry. And that is being represented by 1. Inverse, if I rotate by 90 degree square, I rotate by 90 degree and it comes into self-coincidence. Minus 90 degree, which is the inverse of 90 degree, it will also come into self-coincidence. So inverse will always be there, and the associative property, which you know from your number line. So that is also be there. So symmetry satisfies all these properties. So that makes symmetry group. But who in mathematics gave the concept of groups? All our point groups, space group, freeze group, starts with group. And the person who started group was Evariste Galois. Date of birth and date of death is written correctly. There is no mistake. So calculate his age at the time of death. 21. If you look at the month also, 21 he did not complete. So 20 plus. He died at 20 plus. He is the founder of group theory, on the basis of which we are talking about point group, space group, and freeze group. He wrote his papers at the age of 17. He started working on theory of equations. The group theory, surprisingly, group theory came from equations. Linear equation you can solve, quadratic equation you can solve, cubic equation you cannot solve, but if you Google, you will find a formula for cubic also. Equation of 4th degree you cannot solve because nobody taught you, nobody taught me also, I can also not solve. But if you Google, you will find formula for 4th degree. But there is no formula for 5th degree. And this young man set out that why there is no formula and proved once for all that there cannot be any formula for 5th degree and higher. So you can have equations only up to formulas only up to 4th degree. And that proof required group theory. But how did he die so young? Not because of an illness, but because of a murder. Duel. Duel क्या होता है? I need 2 volunteers. एक जो ड्यूल कराऊंगा, एक जो मरने के लिए तैयार है और एक जो मारने के लिए तैयार है. 2 आदमी चाहिए और बतलाना होगा कि मरने वाले हो कि मारने वाले हो. जल्दी आ जाओ, टाइम नहीं है. हाँ, मरना चाहते हो कि मारना चाहते हो? हाँ, मारना चाहते हो तो तुम गैलवा के दुश्मन हो गए. अच्छा, गैलवा के दुश्मन हो गए, जिंदा तो रहोगे लेकिन जिंदगी भर अपमान में रहोगे. और तुम गैलवा बने, तुम मर तो जाओगे लेकिन तुम्हारा चित्र यहाँ पर दिखलाऊंगा स्लाइड में. ठीक है, तो ये गैलवा हुआ. अब तुम ऐसे, तुम लोग दोनों को एक एक पिस्तौल देता हूँ. पिस्तौल ले लो, ले लो, तुम भी पिस्तौल ले लो एक. हाँ, रख लो, पॉकेट में रख लो. हाँ, रख लिया सर. पिस्तौल पॉकेट में रख लो. हाँ, अब इधर ऐसे उल्टा खड़ा हो, उल्टा खड़ा हो, तुम भी उल्टा खड़ा हो. बैक टू बैक, बैक टू बैक. अब मैं काउंट करूंगा, हर काउंट के साथ एक स्टेप लेना है. ठीक है, और जब मैं रुक जाऊंगा तो रुक जाना, और जब क्लैप करूंगा तो तुमको घूमकर गोली चलाना है. अब इतिहास साक्षी है कि घूम के गोली चलाने में गोली गैलवा को लगी. तुम गैलवा हो इसलिए तुम्हें मरना पड़ेगा, ठीक है? मरने का एक्टिंग जानते हो? हाँ, गिर के अच्छा से मैं, ठीक है, और तुम हंसते हुए निकल जाना, ठीक है? लेकिन तुम बहुत ही बदनामी वाला काम कर रहे हो, ठीक है? हाँ, 1 2 3 4 5. Wait for my clap. As soon as the clap you hear, you have to turn and shoot. Imagine for a young, bright mathematician to die like this. Khel mein. Die like this. Duel. He was also very politically active. There are a lot of theories. You Google that, you will get confused. Who actually killed it and how and why the duel was set up. But it is a fact that he was killed in a duel. He kept lying in the pool of blood in a field. The duel was conducted in a field outside Paris. He kept, after being shot, he kept lying in the pool of blood. Some farmer came, took him to a hospital. Hospital was named for some reason, Cochin Hospital. So Cochin Hospital in Paris, where he was taken. I don't know whether it's a French word or it's actually the Cochin of our Cochin. So where he finally died next day. So duel, very bad game, now banned, but in those days people used to play. So now let us come to the freeze group. So in freeze we will have repetition. So letters you have already, the point group you have done. Now you do the letters. So to create freeze group, many of you are saying for F and G individual letters itself the translation. No, unless and until it is repeated, the translation will not come. So now I am repeating. Now I am repeating A to create the freeze group. So repeat, repeat, repeat. So forward repetition, you have to continue in this direction, but the pattern has to be infinite in both the directions. You have to repeat in the opposite direction also. Remember the group property inverse. If any operation is there, the inverse should also be there. What will be the inverse of vector t? Minus t in this case. Okay, so you will go in the opposite direction as well. So now letter A had what symmetry? Reflection symmetry, the vertical symmetry. So that symmetry will be there for the whole pattern also, not only for the letter, now for the whole pattern. Because not only this letter is coming into coincidence, if I reflect this A into this mirror, I get this A. If I reflect this A into this mirror, I get this A. But exactly in the position where already A was there. So the whole pattern remains self-coincident by reflection in all these mirrors. Are you seeing any other new symmetry? That is the magic. If I am asking, you should see. Hint. Translation is there, that's not new. New, not yet drawn here, but is present in this freeze group. कौन बतलाएगा? जो बतलाएगा उसके चॉकलेट है ना पात्रा जी? हाँ चॉकलेट है, जो बतलाएगा पहले चॉकलेट मिलेगा. Glide in which plane? Glide in which plane? Plane बतलाओ, glide का एक plane होना चाहिए और line. Which line? Horizontal or vertical? Horizontal. Horizontal, if I reflect A, I will get ulta A. After that, whatever I translate. Vertical, if I reflect and then translate. You have to translate. After reflection, you have to translate parallel to the mirror. So if I reflect and then translate, I should start getting A somewhere else. Not there. So, yeah? Yeah? Where? Mirror is already there. New. between उसको chocolate between the two A's. So although, see, this is again, this is a symmetry game. This is a game of symmetry. I started with the letter A. I didn't ask for this green mirrors. I asked for give me a letter which has a vertical mirror. And then I decided happily to translate it by T. But now, I can't do that. I can't do that without creating a mirror at half the displacement, half the translation vectors. So, T by 2 mirrors are Swambhu. Swambhu Bhagwan bante hain na? So, again, it's the same thing. A translation combined with mirror at 0 position creates a translation at T by 2. Can't avoid it. The closure property of the group. If two operations are there, translation is there, mirror at position 0 is there, mirror at T by 2, the combination should also be present, and that is mirror at T by 2. वाह, खुशी नहीं हुआ? ताली तो बजा दो यार. हाँ? रोटेशन तो नहीं है, पीछे नहीं जा रहा. यहाँ पर देखते हैं रोटेशन क्यों. Like अगर 180, any rotation of 180 to A will give me an ulta A. अच्छा, very good. Yeah, very good. Very good point. See, nobody raised, but directors are raised. You should have raised it. That instead of mirror, I can rotate it about this line. I can think of this as a rotation axis and rotate by 180 degree. But in terms of mapping, that rotation will take this point to this point. The reflection also takes that point to that point. Okay. So in terms of mapping, from point to point mapping, this reflection in this mirror line and 180 degree rotation about an axis lying in the plane is exactly the same. So these are just two different words for the same thing, and conventionally for 2D we use the mirror and do not describe it as rotation. So rotation for 2D is always about a perpendicular axis. But you can, so if you want, it's not a new thing. If you want to describe it as a twofold lying in this, then you don't call the mirror. You remove the mirror, you call it a twofold. But usually that is non-conventional. Yeah, now how do I name it? That P1M1, that is a very strange name for this group, but very, very simple. Just one by one. Four things are there. 4 positions are there. Each position has a meaning. First position is the simplest, just put P. Nothing else is there in first position. For all freeze group, P is there. So first position is solved. Always P, that stands for primitive. We will not explain at the moment. Next position always tells whether there is a twofold rotation or not. If a twofold rotation is there, put 2. If it's not there, put 1. 1 for no rotation, 2 for twofold rotation. Third position, you have a translation. Look perpendicular to the translation line. You have a translation. Look perpendicular to the translation line. And perpendicular translation line, I am having mirror. Both the red and green mirror are perpendicular to the translation line. So third position M. If this perpendicular mirror was not there, third position would also have been 1. The last one is parallel to the translation line. So this one sees whether parallel to the translation line I have any mirror or glide or not. In this case, parallel to the translation line, nothing is there. So P1M1. जब गैलवा वाला ये शो कर रहे थे तो कोई एक दो लड़के मिस हो गए थे यहाँ पर आने के बाद, वो फिर से आ जाएं, उनके भी चांस मिलेगा। क्योंकि अब कॉनवे ने उसका नाम साइडल कैसे रखा ये समझाने के लिए मुझे एक डेमोन्स्ट्रेटर चाहिए। अब क्या नाम? के सिद्धि रंजन। And which school? Yeah. So now you sidle and show how to sidle. 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 Yeah. So sidle, I will show you. You stand like this with your foot. Okay. And side bhago. Side bhagna is sidle. Side. So हाँ ठीक है, तुमको भी करना है, बैठ जाओ यहाँ पे, बैठ जाओ, अभी बुलाता हूँ नेक्स्ट वॉक पर। ओके, थैंक यू सिद्धि रंजन फॉर शोइंग साइडल। Yeah, so these names sidle, very colorful name. Sidle, walk, jump, spin, hop. These 7 names were given and concocted by this famous mathematician, Conway, John Horton Conway. He was very much deep into symmetry and deep into patterns and deep into group theory. Has several books. He was a Princeton mathematician, and you can see his office. Office looks like some sort of demonstration of various models which he is having. In one, for few days in Princeton, he decided that his room is too claustrophobic, does not encourage discussions. So he shifted his table in the corridor so that students, people coming, going can have a discussion. So he was having more freer discussion in the corridor rather than in his office. And in one of his book, again on symmetry, the symmetries of things, with 2 other, actually one of them is not a mathematician but an artist. So very nice symmetry pictures you will find in this book, the symmetry of patterns. So ये साइडल नाम जो दिया सिद्धि रंजन ने, वो किस बेसिस पर? So remember, we were sidling this way. So left pair, right pair, sidle mara, left right, sidle mara, left right. If then the footprints have what symmetry? Exactly the same symmetry as A. If you are sidling, your footprint is having vertical mirrors between the footprints and vertical mirror in between also. Okay, so that's why sidling. Of course, you can all sari, ma'am, your sari border, you have to find out which 7 frieze group it is. Oh, everyone wearing sari. This homework. That which of the 7 frieze group, because it's a single border. Any border, sari border, dupatta border, temple, kanguras, wherever you see repetition in one direction, you will have the frieze group and you can find frieze pattern. So you can see this sari border, it has many friezes, but this central big frieze, you can see is again having the same M's. M through the leaves and M in between. I have not drawn M in between. So it's the same group, same P1, M1 or sidle. Now the sine wave exercise. With this we will complete the frieze group and we'll go to the plane group in the last 5-10 minutes. Batlao, sine wave ki symmetry batlao, now you have seen. Does it have translation? What is it called in the common bhasha? Translational symmetry has a name. Sine wave का क्या? Lambda wavelength. So जो wavelength बोलते हो यहाँ से यहाँ, that's what is its translational symmetry. Wavelength is translational symmetry of the sine wave. But what other symmetries? What other symmetries? Horizontal glide. Very good. सबसे ज़्यादा difficult था उसको पहले देख लिए. So if I reflect this crest, then I will get a trough. But there is no trough there, so I will shift the trough to match here. By how much? Lambda by 2, t by 2, remember? So if t is the periodicity of the pattern, the glide will always have t by 2 as its operation. So lambda and lambda by 2. So we do have a glide, but other operations are also there. Sine wave. रोटेशन by 180 डिग्री कौन बोला? कहां पर? Where is the center for rotation? Where is the center for rotation? नहीं, सेंटर फॉर रोटेशन पहले देख लें. रोटेशन कहां पर है? सही बोल रहे हो सर. कहां पर?
T/4. Sir, T/4.
Okay, let me draw an x-axis. With respect to that, you say.
Okay, sir.
Is it lying on the x-axis?
Yes, sir.
And where?
Yes, sir.
Wherever the x-axis intersects the curve is actually a two-fold rotation center. Very good.
Sir.
Very good. But no.
Sir, here. Sir.
कहाँ?
Sir.
Sir,
it has a rotational symmetry at a distance of 3t/2.
T/2 from where?
From left or right?
Yeah, very good, very good. Right, that's the right answer. From here, t/2 here. So actually, that's what I said. If you draw the x-axis, the x-axis is the glide line, and intersection of x-axis with the curve is the two-fold. But you are all missing mirror. Mirror to dekho, vertical mirror. Vertical mirrors are there. And as you know, if mirrors are there at the wavelength, there will be mirror at half wavelength, the green mirrors. Don't forget the green mirror. So one passing through the crests, another passing through the trough, and the two-fold. And finally, which you all of you found for the first, I am very impressed, is the glide. So the x-axis is the sine wave को इस तरह से देखा क्या कभी? कि sine wave also is a Friese group, but now name this Friese group for me. First letter P, second letter, whether rotation is there or not, it is there, so P2. Third letter, perpendicular to the translation, mirror is there, so P2M. And the last one, parallel to the translation, so it's not M. Parallel to the translation is glide, G. तो निकल गया P2MG. अब इसको P2MG, कॉन्वे साहब ने बोला स्पिन साइडल. अब कौन करेगा? थोड़ा नशे वाला काम है. एक कोई आया तो था, मैं बोला था कि रुक जाओ. स्पिन साइडल ये कर लेगी, आ जाओ. नहीं, दूसरे को मत भेजो, अपने आओ, फोर्स मत करो. हाँ, यस. स्पिन साइडल लेकिन नशा आ जाएगा तो समझ लेना. अब पहले साइडल करके दिखलाओ. पहले साइडल सीखी कि नहीं? हाँ. अब साइडल में स्पिन कर जाना है, तो पहला पैर यहाँ है. हाँ, पहला पैर यहाँ है, दूसरा यहाँ आएगा. हाँ, फिर यहाँ आएगा. अब वहां से यहाँ तक स्पिन करते हुए आओ, स्पिन साइडल करते हुए. वीडियो बनाओ भाई इसका. ठीक है, थैंक यू. सो स्पिन साइडल, कॉन्वेज नेम स्पिन साइडल. अब देखो, अब साइन वेव का तो कोई साड़ी का बॉर्डर नहीं बनाएगा. साड़ी का बॉर्डर के लिए कुछ अच्छी इंटरेस्टिंग मोटिव चाहिए. मैंने तुम्हें पीकॉक दिखलाया था. अब पीकॉक से एक साड़ी का बॉर्डर बनाता हूं यूजिंग P2MG. अब this is a nice, I think designers are using any given motif. So now I have taken peacock motif. You can generate 7 different periodic patterns for all the 7 groups. I am making now the same one, P2MG, for the sine wave. So पहले मिरर लगा, पहले एक उससे स्टार्ट किया, मिरर लगाया, हमें वर्टिकल मिरर चाहिए तो मोर रिफ्लेक्ट हुआ, फिर हमें 2 फोल्ड भी चाहिए λ/2 पर, तो इसको रोटेट कर दिया 2 फोल्ड से 180 डिग्री, दोनों मोर उलट गए, फिर मिरर लगाया, फिर 2 फोल्ड लगाया, ऐसे करने लगा तो मेरी साड़ी की बॉर्डर बन चली. अब ये बिकेगा कि नहीं मेरा साड़ी, ये डिफरेंट बात है, लेकिन the designer can make different kinds, or you can try in your home, take different motif and try different frieze patterns. Now finally coming to the 2-dimensional periodic pattern, the wallpapers. फ्रीज ग्रुप में कोई 4 फोल्ड रोटेशन नहीं मिला, फ्रीज ग्रुप में कोई 4 फोल्ड रोटेशन नहीं मिला, क्यों? 4 फोल्ड की क्या गलती थी? 4 फोल्ड ने बेचारा क्या करे, आरटीआई करेगा 4 फोल्ड, 2 फोल्ड को जगह मिली, मुझे नहीं मिला फ्रीज ग्रुप में, तो आरटीआई का क्या जवाब दोगे? देखो, जब फ्रीज ग्रुप था तो ट्रांसलेशन वाज ओनली इन वन डायरेक्शन. Any rotation other than 180 degree will generate a translation in a different direction. 4 fold is 90 degree, इधर translation है और 4 fold भी है उसके पास, so you will have a perpendicular translation. So then you will not have a freeze, you will have a plane group. So in plane group you can have more symmetry. So, but in freeze group you can only have 2 fold rotation, but plane group you can have, and the definition of the fold I gave you orally, but it's written here 360 by theta, where theta is the smallest non-zero rotation angle. Different folds for different pattern. Letter Z we have already seen 2 fold, then that symbol 3 fold, swastik 4 fold, 5 petal flower 5 fold, hexagonal snowflake 6 fold, and some computer graphics 8 fold. However, now just like freeze group with single translation put a restriction that nothing other than 2 fold can be there, even the plane group puts a restriction that only certain rotations can be there, and interestingly only these rotations are possible. 1 no rotation, 2 180 degree, 3 120, 4 90, 5 no, 5 fold not there, and 6 yes, 6 fold, 7 8 9 not there. So this is called the crystallographic restriction. Crystallographic symmetry or periodic symmetry in 2D and 3D are restricted to only 1 fold, 2 fold, 3 fold, 4 fold, and 6 fold rotations. Ab last exercise with which we will finish is, अरे ये तो solution ही दिखला दिया, no, जल्दी हटाओ. So you have the pattern, try to find the symmetry of the pattern, match it with the 17 plane groups, and tell me, or tell Dr. Patra if you want chocolate. क्यों? जो जस्टिफिकेशन देना होगा, P3M1 का जस्टिफिकेशन देना होगा. P3M1 क्यों? वो एक साथ में एक और है P31M. Why not P31M? जो भी P3M1 बोल रहा है उसको जवाब देना होगा why not P31M? There are two closely related. यही तो खेल है, P3M1 की P31M. हाँ बोलो. हाँ, very good, very good.
Sir, each fish and lizard के around mirror है sir,
हाँ.
vertical mirror.
हाँ.
That is why P3M1 not P3 1M.
हाँ, P3 1M में क्या होगा?
Sir, P3 1M होता तो यहाँ पर reflection नहीं होता, मतलब mirror नहीं होता.
Very good, very good. So threefold, those points which you are talking about, you should.
So 3 is for that यहाँ पर बीच में 3 lines से वो हो रहा है 3 folds.
Yeah,
That
very
is why
good,
P3.
very good. Is the correct answer है. Patra ji, he deserves the chocolate. हाँ, ताली बजा दो, ताली बजा दो. So देखो, ट्रांसलेशनल सिमेट्री तो हमने पहले ही देख लिया था स्टार्ट ऑफ द लेक्चर में. उसके बाद ट्रांसलेशन के अलावा क्या है? So all these lines are mirrors. You see, Escher has very nicely used. उसके lizard और bats और fish arbitrary नहीं हैं. They are drawn nicely such that a mirror line passes straight through their bisectors. So each animal's bisector, bodily bisector, is actually a mirror line. And wherever 3 mirrors intersect, you have a threefold rotation also. Take this lizard, 120 degree rotation यहाँ आ गया, 120 degree rotation इधर आ गया, ठीक है ना? So, and same with all other animals. So, mirrors are there, intersection of mirrors are threefold, and there is no other symmetry. So, now the exercise becomes very simple. Exercise becomes very simple. 17 plane groups, P1 out, P1 says no symmetry other than translation. P2 out, only twofold. PM out, only mirrors. PG out, only glides. CM out, only mirror and glide. P2MM, only two folds and mirrors. All these out. Fourfold not there. This is also out. So only things which have threefold are on the corner there. So these. Last these two also out because we have threefold but not sixfold. This has threefold along with sixfold. So these two also out. So the final candidates are the top 3. Top 3, P3 is a poor fellow, has threefold but no mirrors. My lizards have threefold as well as mirrors. So P3 is out. So only candidates were P3M1 and P3-1M. Now, very rightly, क्या नाम तुम्हारा? बादल सेठी. So rightly pointed out by Badal Sethi that just see the orientation, relationship between the mirror and threefold. In P3M1, all three folds have mirrors passing through them. In P3-1M, some three folds at the corners have mirrors passing through them, but other three folds अंदर वाले के पास मिरर नहीं है. आंसर मिल गया, आंसर मिल गया. सो थोड़ी सी एशर की 2 मिनट की कहानी बतलाकर बंद करूंगा, वाणी को विराम. सो एशर, I told you, very famous Dutch artist, graphic artist, whose pattern we solved, one of the patterns. Solve other patterns also, go and look at that. He became very, very famous. He actually, mathematicians and 17 plane group, I told you, na? 17 plane group. He was not a mathematician. He was very poor at mathematics. He says he was even poor at drawing in his school. I'll come to that slide. So, but through his intuition, he generated not only this P3M1 which we saw, all the 17 plane groups. And he had his own classification scheme by which he had 17 names. So not the crystallographer's name or the mathematician's name, he had his own names, but 17 types he showed. And then he actually had a real discussion with a real mathematician, George Polya, very famous mathematician. Polya was the one who proved that there are 17 plane groups mathematically. The proof, see, I just gave you the list. Proof is not that easy. Got to work hard for that. And George Polya was the one who proved it. And the mathematician George Polya discussed with MC Escher, and then they came to know about each other's work. Of course, he must not have understood the mathematics, but he understood that this person is intuitively, through art, is getting into mathematics. And that's why he became very famous. He gave actually invited talks at International Union of Crystallography in Cambridge. And as I told you, a crystallography textbook by International Union of Crystallography is written to teach symmetry and space group simply based on Escher's pattern. So another, what do you, yeah, ye bhi chocolate question. Last chocolate question. What do you see in this? Birds, कौन बोला bird? हाँ, bird वाले को chocolate दीजिए. There is no background. There is no background. There is fish and bird flying in the other direction.
Sir, it's a bird. मैं बोला.
Yeah, but it's also fish. Both are there. So backgroundless, regular division of planes. He was born in a very wealthy family. His father was a wealthy civil engineer. You can see his house. But his father wanted him, and he drew his father when he was 18 years old. And then he drew his father again when he was 37 years old. You can see how his art is developing. The father himself is at 92 years old now. So, a little bit of his biography. At secondary school in Arnhem, just quotes from him. Drawing was absolutely my favorite subject. The passion. The passion is important. The favorite subject is important. What is your favorite subject? And find that favorite subject and follow that. Drawing was my favorite subject. But look what he is going to say next. Next sentence will surprise you. I hated school, but the drawing lessons was always a great relief. So only one subject, like Ramanujan, who only liked mathematics. But although I wasn't particularly brilliant pupil at drawing, जो पैशन का सब्जेक्ट है उसमें भी टॉपर नहीं था. Don't have to be topper to follow your passion. Okay, and you don't have to be topper to do well. The school grading, school topping is a different game. The live performance and life game is a different game. So even if you are following like particular subject, but in terms of exams and all you are not able to do so well, don't drop it. Carry on. I wasn't bad, but certainly wasn't exceptional. So then he went to, father was a civil engineer and he liked art and all. So father probably thought of a compromise. Ki art plus civil is equal to architect. So he asked him to be trained as architect. He sent him to a architecture school. But there he showed his drawings and he showed his artwork to one of the teachers, one of the sympathetic teachers. So his school time lino cuts to his teacher, well-known graphic artist. The teacher said, wouldn't you be graphic artist instead of an architect? One sentence, transform Escher from architecture course to graphics arts course. So teachers' influence can be there. Teachers have to be careful in making comments, and teachers have to appreciate students' abilities and skills. And don't be hesitant. Teachers also have powerful position. Teachers, professors, director. It's very not easy to approach, but don't be hesitant. Don't be hesitant to sometimes take your ideas, take your views and talk to them, because however daunting they may appear, they have one plus point, that they have the experience which you don't have. So sometimes you can get guidance and good views even for people who appear not to be very friendly. Of course, father was not initially, as usual, father was not agreeing to this change from architecture to art, but finally gave his consent. Thank you very much.
Okay, so we have a very exciting talk, and I hope we have a lot of questions. So how much time is there for questions? 15 minutes. Okay, any question? Last page.
क्वेश्चन का जवाब देना है,
ऊपर जाओ.
तो ये लेना चाहिए, ये
Good afternoon, everyone. I am Prince from Iron Public School. Sir, I have a question. Sir, here in my paper, B is not symmetrical. The top part and the bottom part is slightly bigger than each other. Yes, sir. Sir, in next.
where most of it was symmetrical, but you were very right. Your observation. I did find that in B, the top circle and the bottom semicircle are not the same, slightly different. So well observed. Hello.
Yes.
So we are imagining that they are equal for having that horizontal symmetry. But if it is not, we will have to put it in point group 1. Very good. Very good.
Thank you, sir.
Chocolate mila ki nahi? We'll give them. Yeah.
You have to be fast. Raise your hand. We will
Good
take
afternoon,
only
everyone.
2-3 questions more. Okay.
Sir,
Then
what
let-
is Sir, what is isometry?
That he explained.
Isometry.
This is not a good question. This is a repeat of what he has already explained. You have to ask something which he has not. This is a question which he has already answered. It is a straightforward. Anything because we have very little time. Isometry has already explained. He has defined in the slide something which you think new creatively. Don't ask something which he has already. That means you are not thinking. If he has taught you isometry and you are asking what is isometry.
Good afternoon, sir. Sir, I am Akshobhya Yadav from Army Public School. I have a generalized question that how is this study of symmetries like shaping the future, and if someone wants to like opt for this career, what is the most prominent institute one must choose?
Symmetry.
Yeah. So I will give the mic to director, sir.
So symmetry has a lot of applications in physics. Of course, mathematics it is there. It has come from mathematics. But there are lots of applications in physics and in physics, then engineering. For example, just by knowing symmetry of a crystal, I can tell that if I pass a laser light of frequency omega, it will give me frequency of 2 omega. I can tell that some crystals will do it, some crystals will not do it. I don't have to do the experiment. I can tell by symmetry. So symmetry, if you know, there are a lot of properties. There are properties like ferroelectricity. If you know symmetry, you can tell which materials will have ferroelectricity. Yes. So there are a lot of applications in physics and of course in engineering. Yes.
Thank you, sir.
Next question.
आपका नाम क्या है?
Good evening, sir. My name is Abhishek Pradhan. I am from PM Sri Kendriya Vidyalaya, Berhampur. Sir, we see that if there are two folds, then we place a symbol of oval, and if there are four folds,
Then we place a symbol of square. Then what about O, which have infinite symmetrical lines? Yes, sir.
I will suggest you can use a circle, because finally it's all polygons, and the limit of polygon tending to infinity, infinite side, is a circle. Although something which I have not seen.
You're saying infinite symmetry elements, okay? In crystallography, it is probably given by a circle, but in chemistry, it is given by infinity, the symbol infinity. Symmetry can also be taught through chemistry language. There are two types of notations. He is using one notation. This is used in crystallography. Okay, you can give him a chocolate. His question was given. Yeah, any other question? Yeah. Speak loudly. Any other interesting question which nobody has asked, and not from what he has taught, but what you have thought?
Sir, what must be the viewpoint of a normal person to understand the beauty of the symmetry? Like person like John Horton Conway and you look into like. What must be the viewpoint of a normal people to understand its beauty?
No,
To understand its meaning?
I think
See, not the viewpoint, but the application, diligence, passion, learn. Okay, there is no special talent required. There is no. If you start thinking about it, you start working on it, you will become expert tomorrow.
I think your question, you have to phrase it properly, what you want to know. Okay?
Yeah.
That's one very important thing in life, even in your classes. It is important to ask questions, and those students who ask good questions, they are better students than those who get 100 marks. To me, if you can frame a good question, you are a better student than the student who gets 100 out of 100. So learn to ask good questions. Okay, what is a good question?
Thank you, sir.
Good evening, sir. I was Aishwarya from DA Public School. Sir, I wanted to ask, is there any scope for finding new freezes group or plane groups? We are limited with a number. So can we find more if we try?
She's asking, can you
The,
more than
the
7?
freeze group cannot be changed under the constraints which is given, but then other things are going on, even in tiling. Mathematicians are doing tiling research, and few years back some research came on so-called quasi-periodic tiling. Okay, we are talking about periodic. What if you not have periodic but quasi-periodic? Professor is going to talk on Fibonacci series. Yeah.
Basically, in 3 dimensions, you can have certain symmetry. If you increase the dimensions, you will have more symmetry. It's abstract. That's why mathematics has symmetry. It's abstract. In physics, it is real life. Real life is 3 dimension. So if you want to go into higher symmetry, you can increase many quasi-periodicity, you can get more symmetry elements. But in real life, we work with 3 dimensions. You can only have 230 space groups. You have fixed. That means you cannot have any more symmetry. That's the maximum symmetry.
Sir, I am Snehal Mudali from OAV Karapalli. Sir,
This is the last question. Okay.
Okay, sir. Sir, using symmetry, could we guess the point of breaking of any object? Sir, using chemistry, could we guess the point of breaking of any object? Yes, sir, in plane figures. 2-dimensional.
I don't think you got your question right. So there's no logic in the question. I can give you once again. Repeat your question.
Sir, using that symmetry, all the formulas we learned in this seminar, can we use these formulas to get the point of breaking of that 2-dimensional object?
Point of breaking.
Yes, sir.
Doesn't make
Sir, like we have a two-dimensional object which is sir solid, but it is like translucent or transparent. So using this, like sir, we will take a random space and we will try to break it. Then the thing is that it will break from a single point.
There's no logic in your question, by the way. So what is not clear, but you may be having something in your mind. I don't want to say, but think it through what you are trying to ask.
Sir,
What you are
actually,
asking right now is not having any logic to follow. See,
sir,
to answer a
actually,
question has to have a logic. What are you getting at? Then only we can answer.
sir, the point of breaking is a concept of physics, but can we use symmetry in it?
Point of breaking means what? What are you breaking? You're breaking a wall, you're breaking a structure. Are you talking of symmetry breaking? That's a different concept. It's a very
Yes,
high
sir.
level concept.
Symmetry breaking like that.
Symmetry breaking. It is taught at the level of physics, advanced physics courses in master's level. I don't know where you have heard. Symmetry breaking is a different concept. I don't think anybody, even at undergraduate college, will understand. You will study, if you take physics, advanced physics courses at master's level, then some teacher may teach you symmetry breaking. So symmetry breaking is there, okay?
Yes,
But
sir.
it's not breaking a wall. Symmetry breaking is there, a phenomena in physics, in particle physics and all. There is something called symmetry breaking.
Okay, sir. Thank you.
Am I okay, Anil? What I answered? Okay, we close now. Yeah.
Yeah. Uh, Thank you, Professor Prasad, for the nice, engaging presentation. And I would like to invite Professor Ganguly to felicitate Professor Prasad on behalf of this outreach program. Thank you. ହ୍ୟାଲୋ ୟା ଏଥିସହିତ ଆମ୍ଭେମାନେ ଚା ବିରତି ପାଇଁ ଚତୁର୍ଥ ୟା ଆମେ 4:25 ସୁଦ୍ଧା ପୁଣି ଏହି ରୁମ୍କୁ ଫେରିବୁ ତ ଏଥିସହିତ ଆପଣମାନେ ଚା ପାନ ପାଇଁ 4th ଫ୍ଲୋରକୁ ଯାଇପାରିବେ ଓକେ So, just ଏଇ ଫ୍ଲୋରରେ ହିଁ ଚାର ବ୍ୟବସ୍ଥା କରାଯାଇଛି ଆପଣମାନେ ଚା ପାଇଁ ଯାଇପାରିବେ ବାହାରକୁ
is Professor P.S. Anil Kumar. Professor Anil Kumar did his PhD from the University of Pune. He was a Dutch Technology Foundation postdoctoral fellow at University of Twente in the Netherlands. Then he moved to Max Planck Institute of Microstructural Physics in Germany. And later on, he joined the Department of Physics, Indian Institute of Science in 2004. He is currently a professor of physics. His research interests are in experimental condensed matter physics, applied physics, material science, covering topics like spintronics, magnetic nanostructures, transport in multilayers, magnetic properties of ultra-thin ferromagnets, quantum materials and technology. And he is currently the president, I just learned, he has become the president of the International Union of Materials Research Society. He is the first Indian to be the president of the International Union of Materials Research Society. Professor Anil Kumar is going to speak to us on the wonders of magnetism. Professor Anil Kumar, please.
Thank you, Professor Ganguly. Am I audible there? Am I audible? Yeah. Okay. Okay. This is fine. This is fine. This is fine. Okay. First of all, let me thank Professor Ganguly and the team for inviting me here. So I have come to this place last year also for a similar workshop. So today I'll be speaking about wonders of magnetism. So how many of you have used magnetism in your life? Everybody. So let us see a little bit further about the wonders of magnetism, right? So within magnetism, I'm going to talk about a subtopic which is called spintronics. Spintronics means spin-based electronics. So how many of you are using spintronics? How many of you know about spintronics? Okay. So let me rephrase my question. How many of you are using a computer which is made after 1998? So the good news is that all of you are using spintronics. So today we will see where you are using spintronics. So we are all using spintronics. Today's lecture you will learn where you are using spintronics. Spintronics means spin-based electronics. If I consider an electron, you all studied that the electron has got a charge as well as a spin. If you look at the transistor, diode and all those kind of things, you make use of the charge of the electron. We don't worry about the spin of the electron when you talk about the transistor characteristics or diode characteristics. But now we started using the spin of the electron along with this charge. That's why it is called spin-based electronics. So the electron has got its own intrinsic property like charge and spin. Conventionally, for all electronics, we use only the charge of the electron. We forget about the spin of the electron. But now we started worrying about the spin of the electrons along with its charge. That's why it is called spin-based electronics or spintronics. So we will see today how we are using spintronics, etc. So if I look at the spintronics, so this is the spintronics material technology. This may not be that visible to you, I'll explain. There are a large number of people who are contributing the spintronic material technology. You need electrical engineers, you need computer scientists, you need physicists, you need chemists, you need material scientists. All these people come together and develop this field called spintronics technology. And what is coming out of the spintronic technology is fascinating. One of the thing is speed, location and angle sensor. So I'm going to talk about a magnetic field sensor. Imagine that I have a magnet with me, and if I have a magnetic field sensor. So magnetic field sensor means if I bring this magnet close to the magnetic field sensor, sensor will say, yeah, there is a magnet here. the quality of the sensor is decided by the fact that how small you can make this sensor and how small you can make this magnet and how far I can detect this magnetic field. So that is a very good sensor. So if I have a tiny sensor and a tiny magnet and far away distance if I can measure, then I say that I have a wonderful magnetic field sensor. The spintronics technology allow you to make wonderful magnetic field sensors. So where can I use it? Imagine that you are all bicycling, right? And you keep a small magnetic field sensor on the fork of your bicycle and a tiny magnet on the cycle rim, the tire, near the tire. And then what happens? You are bicycling. So when you bicycle, this magnet takes one round and comes back to the sensor. Sensor gives a signal. Fine. Then you are going for the next rotation. Again, the sensor gives a signal. Now the time duration between these two signals is, if it is delta t, if r is the radius of this tire, so 2 pi r by delta t, what is it? Speed of your bicycle. So now with a simple magnetic field sensor and a magnet, you can find out the speed of your bicycle. Each time it rotates, it takes 2 pi r distance, and delta t is the time taken. 2 pi r by delta t gives you the speed of your bicycle, right? Imagine those who are having bikes, there is a cable that is running, many a times the cable breaks, etc. Here there's no contact, a contactless way of looking at the speed of a bicycle. Or imagine that I want to open that door and I don't want to open the door all the time. I wanted to have a remote button and I connect a motor to the door, and when I press the button, the door opens because the motor rotates and the door opens. Now, if I'm not very careful, this door will go and open and bang onto the wall, right? So now imagine that I have kept a tiny magnetic field sensor on the wall and a small magnet on the door. Then what happens? This magnet comes very close to the sensor. Sensor senses it, send a signal back to the motor, stop. Now this door will not go and bang on the wall. Similarly, so this is like a position sensor. The first one was a speed sensor. Now imagine that on this travel, in every 10 degree I kept a magnet. Then what happens? For every 10-degree rotation I get a signal. So that will become an angle sensor. If you consider a modern car, there are around 35 different magnetic field sensors inside for various purposes, including the fuel injection, so many things. Imagine that I am going to make a car where the steering wheel is connected with an array of magnets at the bottom and a magnetic field at the below that. Then when I rotate the steering, the signal will be such a way that I know how many degrees I have rotated. Now without any contact with my single finger, that's not good for a car, but I can rotate my steering wheel. Accordingly, the motor on the tire will random access memory. You are all aware of random access memory. I will tell you a little bit about magnetic random access memory. And the next generation applications, quantum computing, spin memory, field effect transistor, those kind of things. Now let us take one by one and understand. Actually, initially I prepared this lecture for standard 8th and 9th, then I realized, so that's why I changed my lecture. So if I have a magnet, there are magnetic lines of force. So I have brought some demonstration thing also after the lecture in the evening. If you have time, you can just sit with me for some time and see those demonstrations. So you have magnetic lines of force, right? Now in this room, suppose if I want to find out which is the north of this room, how will you find out? I want to find out which is the south and north, east and west. You will use a compass, and then the compass, what the compass will do? This is a compass which I brought. Needle will show where the direction is. Now I know that this is the north of this room, right? A magnetic compass will tell you. So why this compass is giving you that north-south alignment? Earth's magnetic field. So is the Earth's magnetic field looking like this? Yes, that's what you feel, right? But actually, the Earth's magnetic field is not that symmetric as you think, because there is a compass here, and if I bring this magnet close to this compass, it distorts. Similarly, from the solar wind that is coming from the sun, the solar flare will distort our magnetic field. So our magnetic field look something like this. This earth magnetic field is a protector for us from the solar wind because it takes out all this unwanted plasma particles because of this magnetic field. But if you look at tiny here, you see from the pole there is a hole from where the particles can enter, right? So that's why, at all other places we are safe, but at the pole we should be more careful. That's why nowadays all the flights which are taking through a North Pole and South Pole is prone to this kind of disturbances that's coming from the wind. So I thought I will just explain to you because this is what you believe, but in reality this is distorted slightly. But we won't feel that because in the local scale we don't see that. In the global scale, thousands of kilometers out, you see there is a difference between the field lines on the right side and the field lines on the left side. So why did I bring these field lines in this thing? So I'm going to use something called magnetic information data storage for this purpose. Okay. See, there are two magnets like this, right? So if I say that this red color is the North Pole and the blue color is the South Pole, and I keep the red color towards you, right? I say that, okay, this is the zero state of this magnet. I'm just arbitrarily telling you, zero state. When this red is towards me, I call it as a one state. So I can, with a magnet, I can define a zero state and I can define a state one. Now when I have two such magnets, so when I put both the red towards you, this is 0 and this is 0. And what is this? What is this? So with the two magnets, now what I have created is 2 bits of memory. Right? Now let me make it a little bit more complicated for you. Imagine I have 8 pencils here. Each of this pencil is sharpened on one side. And when the pencil is pointed towards you, I say it's a zero state of this magnet. So this is the North Pole of this magnet, this is the South Pole. Now I bring all these 8 pencils, and if it's all with the pointing towards you, what is the state? 0, right? So there are 8 bits here. You must have studied in computers, when you learn computers, 8 bits form 1 byte. Now suppose if I take this magnet like this, what is the state? What is the state? Now with this 8 magnets, I can have 8 bits with the zeros and ones the way you want. Right? This is precisely happening in your computer hard disk. You have magnets inside your hard disk where information is stored like this, zeros and ones. Right? Now let us study a little bit more in detail. So these are the magnets. When the North Pole is towards this, I call it as a 0 state. When the North Pole is on this side, 0, 1, 1. So I have 0, 0, 1, 1. Exactly same as what you define zeros and ones here. Now what happens in a computer, when I take 8 such magnets together, and if I put the magnets such a way that it is 0, 1, 0, 0, 0, 0, 1. I represent the character capital A. So there are other systems in the computer that converts to a monitor, it is capital A. So when I read all these 8 bits together, if it is with a configuration 0, 1, 0, 0, 0, 0, 0, 1. So let us create that thing. This is 0, 1, 0, 0, 0. The last one is 1. So I put it back here. So now what I have is 0, 1, 0, 0, 0, 0, 0, 1. It is capital A. Now imagine that I am changing this thing to this direction and this one to that direction. What is it? B. Right? So now similarly small a. If I change it like this, if I change it like that, And if I change it like this, it is small a. So now every character can be represented by this 8 magnets, 8 bits. This is how precisely you store information in your computer hard disk, right? So how many such magnets are there in your computer? What is a hard disk space in your computer? A typical hard disk space? 1 TB. 1 TB means 1 terabyte. 1 into 8 into 10 power 12. So that means 1 terabyte computer contains 10 power 13 such magnets. See how many magnets you are handling? 10 power 13 magnets. But, okay, then let us. Now, let me ask another question. Suppose if I bring 2 magnets, see, I'm bringing 2 magnets close to each other. What will happen to this magnet? If I bring 2 close, repel. Any other thing? Imagine I am bringing like this 2 red, repel. I am bringing 1 blue and red, attract. Now if I bring them like this, I'll bring it, it goes like this. So when I bring them close to each other, it goes like that. If I bring them like this, it will repel, it's repelling. If I bring them like this, it is attracting. But if I bring them like this, it changes. So what does that mean? That means if I take 8 bits, if I take this 8 bits, if I bring them close to each other, what happens? The alternate ones will be that way, this way, that way, this way. Then I have no information. Information is washed out. The moment I bring the second magnet, the information kept on the first magnet is gone. So what is the way to do? Keep the magnets far away. If the magnets are kept far away, the field lines which we saw there will not influence the second magnet. So now I have to keep these magnets at far away distances. Now in order to keep 8 bits, I need this much area. This room may take around 1000 bits. If I want to put 10 power 13 bits, you need the entire Odisha state to keep my magnets, right? But your computer is having a small entity where 10 power 13 such magnets are there. So what is the trick? Make the magnet small. How small? Make it smaller and smaller and smaller and put more and more magnets in a given area. So that is what exactly was happening. If you look at the size of a magnet somewhere in 2000, the length of the magnet is 380 nanometer and the width of the magnet is 45 nanometer. So this length of this magnet in 2000 was 380 nanometer and the width was 45 nanometer. How small is 45 nanometer? How small is 45 nanometer? 45 into 10 power minus 9. How small it is? How small? What is the diameter of your hair? Approximate. Everyone's hair diameter will vary. Approximately. Diameter of your hair. Approximately. Micron. 1 micron is also micron. 10,000 micron is also micron. A prefactor. Say around 50 to 100 micrometer depending upon the person. Imagine that my hair is 90 micron in diameter, right? Now, how small is 45 nanometer compared to 90 micron? I take my hair, vertically split 2000 times, and one piece out of it is 45 nanometer. So that means in my hair diameter, 2000 magnets can sit in 2000, right? So today the story is different, that I will come, evolution I will come. So that is why in 1980, when the magnet size was around more than 10 micrometer, that means in my hair only 9 magnets. By 2000, in my hair it's almost 2000 magnets. Today in my hair dimension 20,000 magnets. That's why you get terabytes. Now if you look at the size of the bit as a function of time, you see that somewhere here there is a change. It was coming at a smaller rate, slower rate, reducing the dimension. Suddenly it started changing. I asked a question, how many of you are using a computer? Then I modified the question, how many of you are using a computer which is made after 1998? 1998 is a time when this changed its, because that is the point where spintronic based magnetic field sensors were introduced in our computer hard disk. So until that time, what we were using is something called permalloy. Permalloy is an alloy between iron and nickel. The permalloy has a property, it changes its resistance when you apply a magnetic field. Now if I bring a permalloy piece close to this magnet, there are magnetic lines of force outside, and this magnetic lines of force will interact with this permalloy and change its resistance. The change in resistance is 4% per oersted. So if I have a magnetic field outside, if I apply 1 oersted of magnetic field, permalloy whose resistance, if it is 100 ohms, it will change to 96 ohms. So that's why 100 minus 96 divided by 100, 4%. Now if I make this magnet smaller, what happens? The magnetic field outside also will become smaller. When the magnetic field outside becomes smaller, the change in resistance of the permalloy also will go down. So now imagine if I make this magnet half the size, my magnetic field also will go down. My change in resistance of the permalloy will go from 100 to 98. Now if I make it quarter, it will go from 100 to 99. If I keep making it smaller and smaller and smaller, the change in resistance becomes smaller and smaller. And you know, when you do measurements, sometimes that change in resistance you are not able to measure. So one of the thing was bring the permalloy close to the, that's what was happening here. Bringing the permalloy close to your magnet, but here you threw away permalloy and used something called giant magnetoresistance. I'll come to that. Permalloy has magnetoresistance, change in resistance with applied magnetic field. The word giant itself is clear. Giant magnetoresistance, huge change in the magnet resistance when you apply small magnetic field. So now comes the next issue. Don't look at the slide now. Look at me for the time being. What is the state? What is the state? This is. How do you know it is 0? But inside your computer, who will say? You can't go and check if everything is north pole towards you or towards me. So there should be a mechanism of finding out whether it is 0 or 1. So if you remember the magnetic lines of force which I said, the magnetic lines of force will be like this, or if it is like this, it will go like this. Now when I bring the permalloy resistance change or the GMR resistance change will tell me whether it is towards you or towards me. Now imagine my sense, this bit itself is 1 by 20,000 smaller. Now if I bring a sensor, if I bring a sensor like this, it will see all the magnets together, he won't know what to do. Now I have to bring a sensor which is now smaller than this magnet. Otherwise, the sensor will get the information from the next magnet. Right? So what you do, you have a reed head whose dimension is much smaller. Probably we can use it here. A small thing. So you bring that sensor on top of this magnet and see whether it is 0 or 1. Then go to the next one, see whether it's 0 or 1. That's why when you try to read your computer, you hear a sound. Shh. One sound comes, right? What is happening is there is a disk which is rotating at a speed of 10,000 RPM inside your computer. And imagine that this is a circle and you are in one track. Next level is next track. Next level is next track. Like that, there is a circle. So when this thing rotates, I can bring my sensor here and I can, when I make a rotation, I can see what is his state, what is his state, what is his state, like that I can see. Then I know in that track, which is 0, 1, 0, 1, so 8 such blocks gives me 1 byte, then I know what it is. Now what I do, I extend my arm to the second row. Again in the rotation, I will see the people who are in that row. Then I extend my arm further, the third row. Like that, the read head only moves back and forth, whereas the disk rotates at 10,000 RPM at a distance of nanometers separation. Imagine the kind of mechanical engineering that is needed. Something rotates with a space of, few nanometers and rotating as 10,000. That's why when you use a computer, don't shake it. Right? So this is how you read the information. Now, what is the state? What is the state? What is the state? How did I make it? I just took it and put it like this. Inside my computer, if I want to make 0 to 1, I cannot go and take a magnet out and then put it in the opposite direction. So there should be a method called writing head. So I have, you must have studied, you might have done this experiment. I also brought that experiment. If you take a screwdriver, wind a wire around it and connect a battery, what will happen to the screwdriver? It becomes magnetic. And if I change the direction of the current, if North Pole was here, the North Pole will come this side. Similarly, I have a yoke, simple principle, I have a yoke in which I have a wire wound around it, and I pass a current, and then that creates a magnetic field in this opening. And if the magnetic field is sufficient, a ferromagnetic material has got something called coercivity. That means you can switch the magnetization of a material from that state to this state if I apply a magnetic field higher than the coercivity of this material. Now, if I apply a magnetic field which is higher than the coercivity of the material, the magnetization reverses. So again, while writing, same principle. The write head and the read head are side by side. I want to read the information. Again, when you try to read the information in your computer hard disk, again you hear the sound. That sound is what? This disk is rotating. Now the write head is going to this person, apply plus I current, he is made to 0, come to this person. This is how the areal density, gigabyte per square inch, was happening in our computer hard disk. And this is the place where we have brought somewhere in 1998 the giant magnetoresistive read head. And it is keep on increasing. But you see in the last few years, you are not seeing any improvement in your computer hard disk. It is stuck at few terabytes, right? So this is what has happened. In 1950s, the first IBM computer was having a capacity of 5 megabytes. And the information is stored on a 25-inch hard disk, like that 50 of them. So 24-inch hard disk, like this way, 50 of them was giving you a capacity of 5 megabytes. And speed and density, everything. And this computer was almost like in a hall like this. One computer with a 5 MB hard disk in this entire room. But today what you have? A palm-held hard disk. It can take you 500 GB. And 2 such disks give you 1 TB. 4 such disks give you 2 TB, like that. So why it is not improving for quite some time, we should understand. So what was happening? Suppose if I take a ferromagnetic material and I make the size smaller and smaller and smaller, this loses its ferromagnetic property. It becomes something called a paramagnet, a super paramagnet. Means if I look at it, its magnetization north is towards you. If I blink my eye, it comes here. It goes back and forth. Because the thermal energy that is available at room temperature is sufficient to switch the magnetization. So that's why we cannot make the bits any further smaller. We have reached the limit. And in the last 10 years, some more things happened. People went to perpendicular magnetic recording. So this is 0 and this is 1. Now what happens? We put it like this. See, if you go to Bhubaneswar, you see flats. Whereas if you come to this place, mostly houses. Because real estate is less expensive here. Similarly, the computer real estate is also very expensive. That's why from in plane, it goes to perpendicular to the plane. That means in this much area which was taking, Now this is taking like a flat, vertically going up. One bit is taking only this much space. The next bit can be nearby. Next bit can be nearby. So with this, that we have reached now 2 TB, 1 TB computer hard drives. So this to give you a feel about, this magnetic dots. Fine. Now let me just tell you. So I told you that, spintronic device is a giant magnetoresistive device. And this was first shown in 1986-87 time scale by two different groups. One is Professor Peter Grunberg from Germany. The other person was Professor Albert Fert from France. They found out giant magnetoresistance. Suppose if I take iron, Fe, if I measure its resistance change when you apply a magnetic field, resistance change is negligible. Now if I take another material like chromium and I measure the resistance change, it is negligible. But these people had a thinking, look, let me take a bilayer, Fe 30 angstroms, chromium 9 angstroms, and then they made a multi-layer out of it. When they made a multi-layer out of it, they started getting a change in resistance 50%. See, I would not have thought about it. I will check the resistance of iron, it's only meager. I will look at the resistance of chromium, it is meager. But these people thought that let me put this iron, chromium, multi-layer, and they suddenly found 50% change in the resistance. So this discovery was in 1986, and in 1998, this technology came to our computer hard disk. That's why I asked you the question, how many of you are using a computer which is made after 1998? So in 1986, they discovered this, 86-87. 1998, this got into the computer hard disk. In 2007, they received the Nobel Prize in Physics for this discovery. See, imagine two different materials with the two different properties they combined. Now it's an opportunity for all of us. 100 plus elements are there in the periodic table. You can combine them the way you want. Now if you make a compound, again you can make the multi-layers you want. Nowadays, I take one insulating layer and I take another insulating layer. I keep on top of each other. Then I see at the interface it is becoming superconducting. Two insulating layers, you bring them together at the interface, it is superconducting. Two non-ferromagnetic material, different compounds, bring them together at the interface, you see ferromagnetism. So whatever was there with the nature, see, iron, cobalt, nickel was the only three elements in the periodic table that showed you ferromagnetism at room temperature. Now you have infinite possibilities open. Make your own compound, make your own multi-layer, think much more, then you will get into this. See, this is what this gentleman did, Nobel Prize in Physics. So what is needed is thinking, right? See, sometimes students ask the question, is there anything in science left to do? Many people think, oh, everything is there, right? So it's a wrong feeling. In 1899, one of the American patent officer, it apparently said that all what is needed for the mankind has been invented. Because he looked around, electricity was there, bulb was there, motor car was there. He said everything is done. So he said all what is needed for the mankind has been invented. Today, if you look at that, such a foolish statement, right? If today somebody says all what is needed in science is done, it won't take even 100 years. In 20 years, you will see that it's a wrong statement. Let me ask a question. How many of you know about photoelectric effect? Raise your hand. Okay. When photons shine on a material, when is the electron ejected? When is the electron ejected? Threshold as far as energy is concerned. Time-wise, photon is falling. When is the electron ejected? Time-wise. No time. No time means what? Instantaneous. What is instantaneous? What is instantaneous? So people had this question. So after Einstein explained the photoelectric effect, people started doing the experiment. They shine with light, looked for an electron in 1 millisecond. Electron is already there. Then improved, shined with light in 1 microsecond, looked at it, electron is already there. shine with light and looked at in 1 nanosecond, electron is already there. Then it went to picosecond spectroscopy. That means 10 power minus 12. They shine with light, look for an electron, 1 picosecond, electron is already there. So instantaneous, right? Then no, people will not leave there. Every 10 years, by 3 orders of magnitude, the spectroscopy improves. Then people made to femtosecond spectroscopy, 10 power minus 15. They shined with light, looked for an electron, electron is already there. So it's instantaneous. Then now it is a attosecond spectroscopy. So people shine with light, looked for an electron that is coming in an attosecond, 1 attosecond, electron is not there. 2, no. 5, no. 10, no. 15, no. Around 20 attosecond, that first experiment, slowly the electron is coming out. Now the people worry, why it was so slow? It took 20, into 10 power minus 18 seconds to come out. So now people are curious about that, right? So we all thought that we understood photoelectric effect. Now how much more we have to now reveal, right? So in that sense, please don't think that everything is done. Many more things need to be done, right? Okay, then I'll skip this. Actually, in this metallic multilayers, why there is improvement always possible? When you say iron, chromium, iron, chromium, iron, chromium, it's like a burger. You take the burger bun and you see some sauce there, right? In metallic multilayers also it's like that. You make a multilayer of A and B. Sometimes part of A gets into B, sometimes part of B gets into A. So the property gets deteriorated if that happens. So it's like iron, chromium, iron layer, right? And you don't want any chromium coming to iron or any iron going to chromium in this multilayer structure. So that is what the whole world is now perfecting. Make a perfect burger where the sauce will not get into the bun. Okay, let me just give you one more example. Something called tunnel magnetoresistance. So here, the electrons, 2 metallic, in the previous case I said 2 iron layers and a chromium layer in between. Chromium is a metallic layer. So the electron from iron will go through chromium and come to the other side. Now if I make an insulating layer in between, the insulating layer cannot accept electrons. This is like, if I go to that wall, I will be stopped at that wall, right? I can't go further. But you have seen this movie, a man is running towards a wall and he diffuses through the wall and running to the other side. Electrons can do this. Provided the wall thickness is very small, it is called tunneling. Now electrons can tunnel from one ferromagnetic layer to the next ferromagnetic layer through an insulating barrier. So then the resistance of this thing changes depending upon the orientation of the magnetization. So again, there is a resistance change when you apply magnetic field. So then you get something called magnetoresistance. In the earlier case, I said giant magnetoresistance. Now magnetoresistance, but through a tunneling phenomena. So it's called tunnel magnetoresistance. Is anybody using tunnel magnetoresistance here? Should I rephrase my question? Anybody is using a computer which is made after 2005? Good news, all of you are using. So that is used, our current hard disk is using tunnel magnetoresistance because the change in resistance is into hundreds of percentage. So look at here, TMR above 500% is observed. That means even when my bit becomes even so small, the tiny magnetic field coming out of it I can now measure. See, that is why the spintronics technology has revolutionized our life, right? And now with this tunnel magnetoresistance, one more thing that we can do is random access memory. So now what is random access memory? I have 2 ferromagnetic layers and an insulating layer in between. When the magnetizations of the 2 ferromagnetic layer is oriented in the same direction, it has got a low resistance state. I call it as a 0 state. Now when the magnetizations are anti-parallel, if I measure the resistance is high, I call it as a one state. Now just by looking at whether I have a low resistance or a high resistance, now I can define something called a memory. 0 state, 1 state, 0 state, 1 state. Now what I do, I'm going to make a structure. See, if imagine this room was a flat room and all of you are sitting here. At time t equal to 0, I deposited all, I crafted you. I deposited all your legs. And then with a different material, I deposited your body. And then I deposited your head. And you were one unit to start with. Now as a carpenter, I come and remove material around this person. And I created him with the head, body and leg. I came here and removed the material around and I made a structure here. Like that, imagine I made you. Similarly, this tri-layer structure, I removed material around it and I made an independent standing tri-layer structure. Right? Now, what I do, I'm also making a copper wire which is going in this direction and all of you are stepping onto that copper wire. Next row, again a copper wire, you are stepping onto that copper wire. Next row, again you are stepping onto the copper wire. So that means the bottom, all of you are connected in each row by a copper wire. Now I am going to make another copper wire that is connecting all your heads. Right? So now each of you are sitting, stepping onto a copper wire, your head is connected to another copper wire in the cross thing. Now suppose if I pass current, see imagine I take this line and if I pass current through this wire, what happens? Don't worry, nothing will happen to you. So imagine when I pass a current, it creates a magnetic field. Now if this magnetic field is more than the coercivity of this material or coercivity of your head, all of you will turn your head to the back. Now you are facing towards me. If I pass current, all of you will turn to that side. So that means if I measure the resistance, initially it was 0 state, but everybody in this row has become 1 state. Now I can't do that. What I do, I pass 50% of the current through your bottom line. That also creates a magnetic field, but that field is not sufficient to switch anybody. Now remaining 50% I am sending through the top. Then what happens? At the junction, two magnetic fields superimpose. So at the junction, two magnetic fields superimpose, you can change from 0 state to 1 state. So now, earlier when I was talking about hard disk, a disk was rotating, my read head was going like in and out. Now what happens? I have all these lines, ith row, jth column. I measure the resistance. Low resistance state, I know that element at the ith row, jth column is in the 0 state. If I measure the resistance high, I know ith row, jth column is 1 state. Now, without going to individual location, I am able to find out whether it's a 0 state or 1 state. So that's what is happening in a random access memory. No movement. In our computer hard disk, this movement is the one that takes time. Reading and writing takes only nanosecond. So that is why you can make a RAM out of it. This is called magnetic RAM. And similarly, if I want to change the 0 to 1, I pass high current through ith row, jth column. I can switch. And I want to switch back, reverse the current direction. So now, without going to an individual bit, I am able to switch its state, 0 or 1. And without going there, I can do it. I can measure. So that means I have a random access memory, and this is called magnetic random access memory. Let me ask a question. How many of you are using magnetic random access memory? Raise your hand. Okay. The bad news is that you are not using it, right? But it is very, very soon that you will be using it. The reason why you will be using it very soon is this particular table will tell you. Don't look at the last two. Look at DRAM and MRAM, which is there in our computer thing. The DRAM in our computer is non-volatile. Non-volatile means if you don't have a battery backup, your information is lost. So that time, that's why each time when you boot the computer, you start putting the information back there. So it's a non-volatile memory. Whereas it's a volatile memory, whereas MRAM is non-volatile. Once you write the information, unless you change this information, it's kept there forever. You don't have to do anything. So that's why, for example, missile heads, you need a non-volatile memory, because every day morning you cannot go and check whether the battery is firing. So the non-volatile memory that is available today was costing $1 per bit. Imagine if you want 1 megabyte, $1 million goes there. So for those kind of applications, now this magnetic random access memory is used because it is cheap. But it has not come to our computers, because the cost is too high to be affordable to our computers. But it's only a matter of time. It will happen. The write time, 50 nanosecond. Here it is 10 to 50 nanosecond. Read time, 50 nanosecond. 10 nanosecond to 1 microsecond. Read method. In a DRAM that we have, the read method is destructive. So it's like, can I use this to store memory? Can I use this bottle of water to store memory? Again, we'll have to think. Answer is yes. Give me eight bottles, and I fill all filled bottle, I'll say it's a 0 state. Empty bottle, I say it's a 1 state. Now, if I have 8 such bottles, I can fill all 8 and say 0, 0, 0, 0, 0. And I empty one bottle, it becomes 0, 0, 0, 0, 1. So like that, I can make a memory, but it takes a lot of space, not like the magnet. So now, DRAM is something like this. It's a full bottle of water. Imagine it is painted dark. I don't know which color it is. Now, how do I know whether it's a 0 or 1 state? I open the bottle and throw the water out. If the water is coming out, I know it was full. So it was a 0 state. If the water is not coming out, I know it was a 1 state. So, in order to find out whether it's a 0 or 1, I have to throw the water out. Similarly, in a DRAM, like an electronic circuit, you have to discharge and see whether the charge is coming out. When the charge is coming out, oh, I know it's a 1 state. If charge is not coming out, I know it's a 0 state. Now the problem, if it was 1 state and if I take the water out, I have to fill it back. Otherwise, I'm changing the memory. So immediately after this, I'll fill it back. So in that sense, the read method is destructive here. Both have around 10 power 15 rewrite cycle. The operating current for a DRAM, you need huge current to operate. Whereas MRAM, now it has come even much lower than this. See, the power consumption is an important aspect, you know, the data centers in the world. So very recently I was there for a lecture. I was told that the entire city of San Francisco uses less electricity than the data centers in the world. And the data centers in the world, 90% of its power is going in cooling the system, not for computation. Because everything gets heated up. So in that sense, you need to make newer and newer devices that consumes less and less power, so that your cooling is, that's why people thought about putting a data center in Antarctica, because cooling is free. Somebody has put a data center in the underwater, in the sea, because you have to save power, right? So the operating current, similarly the standby current. If it's a DRAM, if charge is there, charge always leaks. So I keep always a tap open on top of this in order to maintain. Whatever is leaking out, I have to keep it back. Whereas for MRAM, that is not needed. So the power consumption of MRAM will be much lower. Imagine you have a computer with a 2 TB RAM, how it will be. That is what we are going to get in future. It's not, you know, far from now. So what is going to happen? The MRAM will take over the DRAM soon. So I think I can keep on going, and maybe I'll show you one more interesting thing what is happening. So in future, what is going to happen? There are work which is going on to integrate the memory vertically, like 15-floor building, 100-floor building, each house. Similarly, if I imagine that with the same area, if we can put 1,000 units up, 1 TB becomes 1,000 TB for you. So that's where this kind of research is heading, and we have not reached nowhere near its full capacity. That's what I am telling you, all of you. Scientists are needed to do this. And you are at the right age to think that you should become a scientist, and plenty of things can be done for the mankind. Yeah. So with this, let me stop. Thank you for your attention.
So we'll take 10 minutes questions. So please.
Good evening, sir. I'm Karthik Pradhan of PMC Kendra Barampur. I have a question that due to the bits made up of magnet, can the strongest magnet, which is neodymium, or any magnet can cause it to malfunction?
Yeah, the thing is that all these computer hard disks are insulated from the external magnetic field. Unless you tear open your computer hard disk and put inside a magnetic field, nothing will happen because enough magnetic shielding has gone around it. Right, so that's why even if you bring a magnet near to your computer hard disk, nothing will happen because lot of shielding around it so that this magnetic lines of force will not penetrate inside this material. In labs, we are even making experiments such a way that even Earth's magnetic field won't penetrate inside a chamber. We give a new metal coating.
Okay, next question.
Good evening, sir. I'm Shriyan from DePaul School. Sir, when you explained the sound that comes from hard disk running, it was because of the read-write head brushing over the disk, magnetic
No,
disk.
it won't touch. If it touch, it crashes. That's what you say hard disk has crashed. It is at a small distance between these two. The distance should be so small so that a stray magnetic field can be picked up and the disk is rotating. That the sound is coming from that disk rotation. Yes.
So I'm talking about, what about SSDs, the one that's really
That is
popular?
totally different. That is not by this, hard disk, with magnets. It's not magnet based. It's electronic based.
Oh.
Okay. Any other? Yeah. Okay.
Sir, I'm Aishwarya. Sir, I wanted to ask, why do certain computers go slow? Means while we are searching something in a PC, why does it suddenly become slow after a few years? I own a computer which was from 2002, and sometimes when I search something on it, it will take a lot of time to load the information. Why does it happen?
See, what's happening is that there is I think a better person is here who can tell this. See, these are all segmented, right? So the system should know where to go and search this thing. As the system becomes, more and more full, it takes more time. One thing. Second thing, from the magnetism point of view, what happens? You write your information in a computer hard disk. If you don't touch for 10 years, everything gets wiped out statistically. The reason is you have a magnet and you don't, suppose if you want to keep the information for a longer time, you need a stronger magnet. If you make the magnet stronger, then you need that much magnetic field to switch the magnetization. So the compromise in the industry is that the lifetime can be 10 years. Because statistically in 10 years, the thermal energy will flip the magnetization. So it gets corrupted also. So certain tracks will get corrupted because of this. So the trick is that once in few years, rewrite your file. Again, it starts fresh. The other one, when the computer becomes full, more and more this thing, searching around will take time. Best thing is copy your data, reformat, put it back again.
So any way to extend the storage?
No, the storage means the capacity or the time.
Time.
No, not. For a given material, the time is already known. For a given material, the time is already known. Once your hard disk is made at time t equal to 0, it is already decided what should be the coercivity of the material. That you can't change it.
A very good evening, sir.
Yeah.
Very good evening, sir. So I'm Ganesh Ranjan from APS Gopalpur, sir. Army Public School Gopalpur. So I have a doubt. I didn't really got the science behind storing the memory in water bottles. I didn't get the science at all.
Okay. What is it? Story of the water bottle.
No, water bottle is a totally different concept. The magnet, I said zeros and one. I was just giving you an example. The memory need not be only with the magnet.
Exactly.
If I have enough space with 8 such bottles, I can create 1 byte.
Yes, sir, you could.
Right?
Yes.
Similarly, what I was trying to tell you, don't stick yourself only to magnetism or this bottle of water. Think about other means of storing information.
Oh, sure, sir.
Any other
Thank
question?
you so much, sir.
Good
Yeah.
afternoon, sir.
Yeah.
So my question is that can the magnetic information storage process be applicable on the modern days quantum computers?
See, this I was talking about not the computing part, right? I'm only telling about the information storage. In the modern qubits also, after the computation, you need space to store the information, and this addresses storing the information. Very interestingly, now what happens? All these years, we were all working towards room temperature storage of information. Now with the quantum computers, which is working, at least the superconducting quantum computer, which is working at 20 millikelvin, 100 millikelvin, now we all started looking at memory at low temperature. And then DRAMs will not work there because the semiconductors will freeze out at those temperatures. So now we started, all these years we were working towards getting a room temperature operation. Now with this quantum computing, we all started working towards a 100 millikelvin operation of then the physics changes, the coercivity of the material changes, so many things changes. So the quantum computing is only from the computation point of view. The storage remains same, whatever I was talking about will remain. For storing that information after the computation, this is needed.
Sir, my name is Swarup Narayan Patnaik
from
PM Shri Kendra Vidyalaya Barampur. Sir, I have a question that how DRAM is more better than that of ferroram?
Okay. You mean to say ferromagnetic RAM?
Yes, sir, ferromagnetic RAM.
See, the thing is that there is lot of hype about SSDs, which is more than what it is needed. The point is that SSD, the endurance, the number of rewrite cycle will not go as good as this one. Because the problem is that most of the people who are using SSD will change their computer before you realize. Whereas this kind of things, even 20-year computers in the lab works. And this is the warm storage. There is something called cold storage, where we do, the old tapes. So in the data centers and all, if the data you need not access immediately, it goes to cold storage. That means that can run for, tens and tens of years. Whereas the hard disk only 10 years. SSD, it won't last even that much. It is faster. I would say maybe 3 or 4 times. It's not that orders of magnitude change.
Good morning, sir. Sir, like you said, if we keep the beats on one on another like a building,
Yeah.
like a building, then there is a chance that the data will be copied, right?
Data will be
Copied
by,
data will be duplicated, sorry.
No. What is happening is, this is here. So what's happening is, in this vertical wire, this small segment is the bit. So then what happens? You push the next bit here, so that at any given point of time, we are only looking at one bit. No cross, that is a challenge at this. Getting this vertical is the biggest challenge. In plane, it is demonstrated. Now, there's a lot of work going on around the world to make it vertical like this. It will take time. Yeah, you can ask. I'll repeat. You can ask, I'll repeat. Tell me.
My question is, what is the demerits of MRAM?
Okay. What she's asking, what is the demerits of MRAM? As on today, price is the demerit. If I want to have one MRAM in my computer hard disk, I may spend around $5,000 to keep one small MRAM there. So I don't get that much advantage as a DRAM. So today DRAM will continue. And when the price becomes much more affordable, this will move to MRAP. So I would say right now the demerit, the main factor is the price.
He is one of the finest physicists of our country. As I said, he is the president of the International Union of Materials Research Society, and he gave such a beautiful explanation of magnetic memories, which all of you are using all the time. But what are the fundamentals of the magnetic memory? So let's thank Professor. So now it is my pleasure to change from science to social science. So we have a very learned professor who is Vice Chancellor of Berhampur University, and none other than Professor Gitanjali Das is with us. And we are very thankful to her for accepted our invitation, because we wanted to say that, you know, you have to grow as an individual. You not only are a scientist, you are a social being, and you need to know about society, laws, and rights. And she is really good at women's rights. So we had invited her, and she gracefully accepted. She is the first woman Vice Chancellor of Berhampur University, and was a professor of political science at Fakir Mohan University, Balasore. She has held several key positions at Balasore, and she has major project from ICSSR on tribal women, climate change, and social equity in selected districts of Odisha. With more than 35 years of teaching experience in Delhi University, Allahabad, Utkal University, and Berhampur University. She is, I think, the president of the Indian Political Science Association. She was, I think, the president of the Indian Political Science Association, and has widely traveled and given invited and keynote talks in several countries, and authored and edited 5 books, and has published several research publications and book chapters. She is a member of national institutes like IIPA, IPSA, OPSA, etc., and also a life member of Gaveshana Chakra, Odisha, Secretary of Gaveshana Chakra during 11 to 20. She has been assigned also the additional responsibility recently as Vice Chancellor of Kalikot Unitary University. She's, as I said, she's currently the President of International Political Science Association and Secretary General of NAPCPAC, the Network of Asia Pacific Schools and Institutes of Public Administration and Governance. It is with pleasure I invite Professor Gitanjali Das to speak to us on women's rights in Indian Constitution. She has unfortunately developed some cramp, and still she agreed to come and deliver this lecture. So thanks to her.
Thank you so much. This will be an interactive mode. I'll just interact with the students. Mostly it will be bilingual. ମୁଁ ଭାବୁଛି ପିଲାମାନେ ଓଡ଼ିଆ ବୁଝୁଛ? ଓଡ଼ିଆ ବୁଝୁଛ? ହଁ, ମୁଁ ଓଡ଼ିଆରେ ଟିକେ ଟିକେ କହିବି, ଓଡ଼ିଆରେ ବେଶୀ କହିବି, ଇଂଲିଶ ଟିକେ ମିଶେଇ ମିଶେଇ କହିବି। ହଁ, ସନ୍ଧ୍ୟା ହେଇଗଲାଣି, ବହୁତ ଦିନ ସାରା ବସି ବସି ବୋର ହେଇଗଲାଣି, ତେଣୁ we will have a dialogue. And I hope all of you understand Odia also a little bit. No, no, not at all. Acha. Hindi, Odia, English, सब चलियो. English. English is always good. Anyway, chalo, mise kaiba. You can understand Odia, I believe. I have some problem with my leg, otherwise it's not the right posture to sit down and talk, but I'm unable to stand for a long time today. So what we will discuss is women's rights in India, but we will have a comparative analysis of women's rights around the world and how India is maintaining these rights of women. We are a largest democracy. We are the largest democracy, and our constitution is also the longest written constitution. Longest written constitution in the world. All of you know that. But we got most of the portions, most of the aspects and dimensions of the constitution from which country? Ireland, England. England. Because we were a colony for around 200 years. We were a British colony. So British only, to our good fortune or bad fortune, superimposed democracy on us. But as a nation, we are a democracy. As a society, we were not. Why we were not a democratic society? You must have a society which were deeply hierarchical and democratic institutions came from Great Britain, because it is all, we derived it from Government of India Act 1919, Government of India Act 1935, etc., etc. So what happened? That Indian constitution gives, it's a very good aspect of the constitution, that we did not have any discrimination between men and women. Why I tell this? Because you know, India as a UK, in United Kingdom, is known as the mother of democracies. It is known as the oldest democracy and the mother of democracies. But you know, when women were given voting rights, who can say? 19? Find out and tell me. Very late. Very late. Huh? So, in a country which is known as the mother of democracies, democratic rights, voting rights, political rights to women were granted very late. Even in a country like United States of America. But we are fortunate. We are fortunate. Why we are so fortunate? Because our women did not have to fight for rights. They didn't have to fight. They didn't have to come to have some agitation, rally, and demonstration like what happened in UK. We didn't have to do that. Why it was so? It was so because our women were very much part and parcel of the nationalist movement. Men and women in large number, under the leadership of Mahatma Gandhi, took equal part in the freedom movement. So we never doubted that whether we should give voting rights to women or not. That is the reason why women were given equal right in every aspect in the constitution since independence. Since independence. So we were given political rights, economic rights, social rights. Every right was given equally, it was granted equally to all women in India. So the concept of right came from the Universal Declaration of Human Rights, which was given by United Nations in Goa. କେବେ ହେଇଥିଲା UDHR କେବେ ହେଇଥିଲା? These are all simple GK. Who can say? $45, $48, $45 United Nations was established. So it was in 48. Google करके कहूँ कि पिला मने so it was granted and it was accepted by all the sovereign nation states. So accordingly, our constitution also had extended rights to all individuals, irrespective of caste, class, and gender. I will not go to the Article 14, 15. These are very, very monotonous. You know that what is there in Article 14, Article 15, and Article 16, and Article 23, 21. Right to life, right against exploitation. Padicha na nai? Padicha. Padina? You have not read it? Padicha. Article 14 kona? Right to book. Nidda lagilani kire? Kichi kauna kichi? Right to equality. 15? Equal protection of law. Chalo, se guda padivani. So what happened, you know, we were granted equal rights. And that is a very good feature of Indian Constitution. Nobody had to fight for his or her own rights. In theory, I underline. Theoretically, we are equal with all men and other individuals. But are we equal? Do we really, we have extended equal rights to women or not? No. Why no? I'll give you some analysis. ତମେ ତ ଜଣେ ଜଣେ କେହି କହୁନ ଗୁଗଲ କରୁଛ ସବୁ ପଚାରିଲେ. So I will discuss. One report came when in 1947 we granted equal rights, equal voting rights, that is called first generation rights. So we granted first generation rights to all women, and we thought we have given enough. Nothing more is required because we have given them political rights, so that is enough, and we have extended everything, every right to women. Then we passed up to 74, maybe 25 years. Then in 74, a report came. The report was known as Towards Equality Report. The report was edited by Professor Beena Majumdar, Latika Sarkar, and Leela Dubey. Some other women, the feminists were also there, but these 2-3 members were the champions of this report. The report had done lot of exercise. Some of the feminists, leading feminists of the country, they had done lot of exercise in preparing the reports. They got data from ground, from every part of the country, from grassroots level, did excellent analysis, had some survey, and they reached a conclusion that all is not well with women in India. So there was a shock wave. Why all is not well with women in India? So they had given data, they provided a lot of evidence in various spheres. This tried to show that socially, culturally, and economically, women are not equal. They are not at par with men in India. Okay. So socially, how? Family is an institution. And the major institution in family is, it depends on the marriage as an institution. What happens in marriage? Do you think that marriage is of equal relationship? Is there an equal relationship within a marriage between a man and a woman? No, ma'am. All boys will say yes, ma'am. All girls will say no, ma'am. The reality is no, ma'am. So why it happens? Culturally, we do not accept at community level, at societal level, that women are equal. Innumerable instances are there. I always say, in a family, what happens? A toy will come, there will be a kitchen set given to a girl. An aeroplane will be given to a boy. So we choose. There are some gender stereotypes. So accordingly, a girl grows inside a family. The girl is taught to help her mother in the kitchen. The boy is taught to go outside for teaching and for learning and also extracurricular activities. If a girl is doing very good in games and sports, very few parents will encourage her. So this happens. So, that's what I am saying. So culturally, socially, economically also we found what happens economically. All belong to Ganjam, all of you. Ganjam re gote bolli achi, Reja kulli. Janicho? Reja. Semane hele khuchura. All women workers, they are called Reja. ଆଉ ସବୁଠୁ କମ ପଇସାରେ ତାଙ୍କୁ ଏମ୍ପ୍ଲୟ କରିହବ ହଁ କି ନାହିଁ so the equal pay for equal work is also a myth. Article 39 जो इंडियन कॉन्स्टिट्यूशन ने कहा है equal directive principles of state policy says that equal work for equal pay for equal work, that also is not there practically. Politically, what happens? What is the percentage of women representatives in parliament and state legislative assemblies? It is around 11 to 12%. Very, very less in number. We are half of the population, but when it comes to political representation, it is only 10-12%. How many are there in the decision making bodies, in executives? Even less. Even less. You know, there are 1100 universities these days, according to AISHE data. You know how many women vice chancellors are there like me? Around 50 to 60 only. Nowadays, there is a trend of giving women leadership in various institutions. It's very, very minimal. So there is always a discrimination in every field, as I told you, in every field. I'll give you some example of the economic participation. Women are half of the world population. They contribute to the work. 2/3 of the work in the world is done by women. 1/10 of income it goes to women. 1% of asset is with women. So this is UN data. So can you imagine how many parents have done a patta? Ame Jamira patta dauche. Can they give a patta in the name of their daughters? Very difficult. Very difficult. They will give a little bit as dowry, and the entire permanent asset will go to the son. So this is discrimination. This goes against the constitution. So constitution gave all rights, but if we analyze, if we go through various survey reports, then we find that very little is actually given to women in India. Not only in India, this is a pattern in all the countries, more or less. In socialist countries, women are in a much better position. But in capitalist countries, women are even sidelined more and more. And what happens now? There is a new trend. The new trend is set by globalization. Globalization. What is it? Globalization, marketization, and privatization. Globalization always opts for a market-driven society. Market-driven society. When we say a market-driven society, market is always based on profit. Profit. Consumable goods, products, and profit is its basis. When it comes to adding economic value to a product, women are sidelined. I'll give you a very good example, which happens in every family, and I always question it. We say, my mother is the best cook on earth because my mother feeds me. You go to any 5-star hotel, how many women are there as cook? All mothers are good cooks. They are very good cook inside their homes because that is non-economical. Nobody pays. Your father doesn't pay to his wife for cooking. When it goes for marketing, women are not taken. In no star hotel, you find a woman as a cook. So that is what is my concern. I always question this because you know what happens? Globalization goes for a technical skill, mechanization, machines, using of machines, and machine using also depends on skill. Skill depends on training. Training is given in a, not at every place, not at every place. Very few training centers are there in Berhampur. Our students do not get training. They are located in distant places. And very few girls are allowed to go far from their home and to get trained. I always say that your mother will say, "Ei pakhaku pala Berhampur University re arts पढ़ी दे, arts पढ़ी दे, MA pass कर जू, तोरो degree ही जीवो, हो कि नहीं?" So we are always, when training comes, when competition comes, girls are far behind. But there is a good trend, there is some positive hope. I always try to find out in STEM education. What is STEM education? Engineering, mathematics. In STEM education, number of women was very less, very, very less, around 8% or even lesser than that. But a current research, it says that in the number in STEM education is increasing day by day. And in STEM research, women are sometimes outnumbering men. Girls are outnumbering boys. So this is a good positive side. The stereotype is breaking. Stereotype is breaking that a girl should go for arts and humanities and a boy should go for a engineering subject. I was one of the toppers when my parents told, "You will opt for yourself." I opted myself for arts. I was not forced for science because I never liked it. So it happens. So what I mean to say, even though the Constitution guarantees equality, it guarantees equal opportunities, because of our long-standing customs, conventions, traditions, and patriarchy. All whatever I told, examples I gave, is an example of patriarchy. Patriarchy is deep-rooted in this country. Very, very deep-rooted. It's so very difficult to break patriarchy and to have an egalitarian society filled with equality and equity. Equity is what? Equality plus social justice. That gives us equity. It is very difficult to maintain equity in a deeply diversified, feudal, hierarchical society. We were given a parliament, we were given democracy, we were given state legislative assemblies, all democratic institutions, but society still remains patriarchal. That is why this disparity. One more factor is there. Apart from patriarchy, there is a big factor. That factor is has a very ugly picture in the society. That is violence. Violence. violence is widespread. We call it in feminist terms, personal is political. Violence is all pervading. Can the girls sitting in this front row, can you dare to go out in late evening? Let us not talk in late night, late evening. Can you go out? Very difficult. Very difficult. It's very, very difficult. Inside the family, it is told, research shows, two-thirds of women are somehow, in some form or other, they face violence. May not be beating in every family, but some sort of mental harassment also is a violence. At societal level, what happens? तू झियो पिलाटा तू केमती जीवु अब गंजाम रे तो बहुत अच्छी आई ऑल्सो बिलोंग टू दिस प्लेस गंजाम रो माँ मान को बुझेवा भारी कष्ट झियो पिलाटा किछि कर परिबरनी कहउछ देख नहीं कहउछन कहयो निश्चय कहउतबे so this is also there. This is a great factor, great hindrance in realizing all the articles of the Constitution. At community level, what happens? What happens at a community level? Women are harassed at community level also. तुम पंजाब रे गोटे खाप पंचायत अच्छी सुनिच there is a concept called खाप पंचायत हरियाणा not पंजाब हरियाणा राजस्थान ने गोटे सती बोली गोटे सिस्टम अच्छी जानिच हाँ तम if your husband dies you will be thrown into the funeral pyre of your husband मरी गले you have no right to leave. Ancient एबे सती मंदिर होची बापा सती मंदिर तयारी होची still community people are they are praying idolizing होची do some research read some literature it is still there you cannot say just simply no to it. So community also discriminates. At state level, what happens? It is many a times it is criticized that even the executive, the legislature, the judiciary is also having a patriarchal undertone. So that is why every time it is said there has to be some sensitization program. We have to sensitize our male members, even female members. I don't say all women are too good to women, not at all. Okay, so that is why sensitization programs are being conducted. Now I'll give you some examples of such happenings and how some proactive laws were formulated. There was a lady in Rajasthan called Bhauri Devi. She belonged to a lower caste, but she was very progressive in her attitude, mindset. She tried to stop child marriage in those areas. So some Brahmins, some people of the higher caste, they started opposing her, and when she did not succumb to their pressure, they had a gang rape on that lady. She was not very old also. I don't remember her exact age, but she was quite young. So she did not give up, and she was gang raped. Then even after that, she did not succumb to the pressure of these people. And with the help of some social, non-governmental sectors from civil society organizations, a case was filed. A case was filed, and a proactive legislation was given by the Supreme Court of India to provide protection, to give protection to all women who are working in various fields. Understand? You get my point? So this happened. So judiciary also plays some very proactive role. But with the, definitely it has been, it is the result of some such effort by one lady or one community or one group of girls or something like that. Another case was there, I found out today only, that was Saira Banu versus State of India, Union of India. In 2017, there was another case. You must be knowing the triple talaq. Talaq. You have to go. Husband comes drunk. He is very angry. Then he will utter talaq. You have to go. You have to leave the house. Why? Because he said talaq. Talaq was unilaterally granted by him. You don't have any say. You cannot defy. So this was made unconstitutional. This was a very proactive step. So like this, we are having some proactive steps, proactive legislations, proactive judgments. Courts at various points of time, they have given judgments for protecting the women. Hindu Succession Act is also a very important milestone for protecting women's rights. That is also a milestone. Then the most important step which was taken by the government is the 73rd and 74th Amendment. What happened with that? It gave reservation at the grassroots level, Panchayati Raj. Panchayati Raj. You go to any panchayat, you see a woman sarpanch. A woman sarpanch. But again, sarpanch pati becomes very important. I'll give you a funny example, because these are very useful. Theory you get in books. You Google it, you will get everything. 3 women came to me when I joined. 3 men came to me when I joined. I closed some gates of the university campus, there are 8 to 10 gates. I closed 5 gates. Only 2 gates were open. So they came to me. I told, what happened? No, there was a thoroughfare inside the campus. You have to open the gate. I told, who are you? May I know your identity? They told, our wives are sarpans. Then I asked him, then you are sarpanch patis? So they said, yes. Then I told, if I wish to talk to the sarpanch, not to the sarpanch pati. If there is some problem with the villagers, then let the sarpanch come to me. They felt very offended. They said, how can you say like this? They cannot talk. If they cannot talk, then how could they fight the election? Who gave them votes? Now we canvassed for them. Canvassing was going on by us. Then I compelled their wives to come to me. And I told, I am a woman. If you can't talk in front of me, then how can you go and talk to the Tahsildar, BDO, executive officers, etc., etc. So this is what is happening. Even if we give some reservation in the Panchayati Raj system, in the state legislatures or in the parliaments, it is yet to be given. Again, the same patriarchal mindset is predominant. That her brother will come, or her father will come, or her husband will come. She has hardly any role to play. So what I mean to say here, what I mean to emphasize here, unless we get rid of these evil practices like this, like discrimination, like violence, like patriarchy, like gender stereotyping, there are so many stereotypes. Your dress, your culture, your etiquettes, your appearance, your look, your how you walk. ଝିଅଟା ହେଇଛୁ ଏତେ ଜୋରେ କେନ୍ ଚାଲୁଛୁ? ଧୀରେ ଚାଲେ. ଝିଅଟା ହେଇଛୁ ଖେଁ ଖେଁ ହେଇକିରି କ'ଣ ହସୁଛୁ? ଧୀରେ ହସିବୁ. These are all gender stereotypes. All gender stereotypes. We cannot realize it. Many a times when we speak, we cannot realize what is wrong in it. Because the culture is a deeply rooted institution. Our books, our pictures, gestures also speak for that. Behavior, everything is rooted in culture. So we have to, before we change our constitution, before we change our legislation, before we change our judgments or executive implementation part, we have to change our attitude. The most important thing is to change our attitude. Amartya Sen, when the question of reservation came, Amartya Sen, a Nobel laureate, he once said, 1 million women were missing in South Asia, South Asian countries. So Amartya Sen had given a concept called missing women. Missing women, because we kill them in mother's womb. A child, a fetus, has no right to come out of her mother's womb. So Amartya Sen had given a statement. Many a times, many people have also spoken like this. Before you ask for reservation in the parliament, you should have reservation of the fetus in her mother's womb. She should have the right to come out of her mother's womb to see the sunlight. She is killed in the mother's womb. Why to speak of women outside the home? Inside the womb also, she is not safe. Many a times there are examples. I still vividly remember I was getting down the train to go home. I saw a big poster in Master Canteen Square in Bhubaneswar. It was written, pay 500 and save 5 lakhs. First, I just couldn't realize what is it. There was the link was given for what is that test? Amniocentesis test. Some hospital, something was given. So you can have the test just by paying 500 rupees so that you can save 5 lakhs in terms of dowry. So look at the attitude. Look at the psyche in the society. It is we who can change it. It is only the youngsters, our young minds, they can rebel. Our young girls can rebel at every step, be it inside the family, be it outside the family, whether it is school, whether it is college or a workplace. Nowhere violence can be promoted. Nowhere violence can be tolerated. Then only we can have an egalitarian society, we can have a just society, we can have a safe society where a girl can also walk down the street in the midnight. Then only you can have a Ramarajya as conceived by Mahatma Gandhi. Thank you. I think I have given you some food for thought. And you can think that only theoretically a constitution cannot bring any change. It is people in the society who can bring change. Wow. Questions?
Good evening, ma'am. I'm Akshi from APS Gopalpur. Ma'am, my question is, when it comes to socialization, globalization, we try to match the competition level with various countries. But when it comes to prioritizing women ideologies and women are being judged over their preferences.
They are being judged.
Yes, ma'am.
That is also a part judgment. They become judgmental. People become judgmental, and there is no parity.
Ma'am, but there should be some implementations of laws that...
Laws are there. Laws are there.
Ma'am, but they are not still followed, and
That's what.
people are not following the laws.
Exactly. That is what I was saying. Whatever I told you,
Yes,
that
ma'am.
is, I meant that only, that laws are there in place. Implementation is poor. Because we don't have the right attitude. Our attitude is, again, judgmental.
Okay, there is one question here.
Thank you, ma'am.
Quick, keep your question short and focused so that she can answer.
Good evening, ma'am. Hello. Good evening, ma'am. My name is Bhavesh Panigray of Delhi Public Senior Secondary School. Ma'am, as you told that the theory of the society is we should all be equal. And you told many things about the women's right and how they are sexually harassed, raped. But there is a section 498A which says that 498A was aimed at preventing cruelty committed upon a woman by her husband and her inner laws. So why don't men get this right? And another question is, the feminists are oppressing and are being so unhuman. Ma'am, for example, ma'am, the recent case, Atul Shubha's case, and 4 years ago,
The girls are also clapping.
ma'am, Sushant Singh Rajput case. Ma'am, why are feminists being
Okay,
so
you
unhuman?
made your
ma'am?
point. You got it. Yeah. You want to answer? Do you want to answer?
I got your point, but these are Sushant Rajput or the other name we said, they are stray cases. Every day you open the newspaper, who is the victim? Whether it's a girl or a boy.
Yeah.
So patriarchy is dominant. That you cannot say. To
majority-
give protection, how many boys are killed in mother's womb? You tell me. You give me one example.
There it is. When I'll go to her and
It is changing. I don't say no to it. It is changing. Even this.
Good evening, ma'am.
Just a minute. This particular case you cited, 498 clause. This is
Okay,
misused. I don't say no to it. This is sometimes it is misused, but we have to go very carefully. We have to go very carefully. That's what.
Good evening, ma'am. I'm Archita Naik from DPS. As you said that Sarpanch thing, so although the answer is very clear, but I would still like you to say, okay. So, is the fragile male ego one of the factors for the discouragement for the advancement of women?
Of course.
Yes, it is.
Of course, yes.
Good evening, ma'am. I am Nano Singh from APS Gopalpur. Ma'am, talking about equality and rights, what more can be done to ensure the effective implementation of the constitutional law that protects women's rights? What should we do to overcome this situation?
Start it from the home. Start from your family. Then only constitutional rights can be, realized.
A very good evening, ma'am. I'm Gyanesh Ranjan Behra from APS Gopalpur. I was having a general doubt, and as we clearly know that women are really clearly skyrocketing in their careers and making us very much proud. As we can clearly take your example, as you're the first Vice Chancellor of Berhampur University, and we can take the example of the CDO, ma'am, who came today as a chief guest with an IAS officer.
can you ask a question rather than give a long lecture? Please.
Sure, sir. Sure, sir.
No, we don't have time for the lecture.
Sure, sir. So as women are already boosting up, so all the rights were given to women and the quotas, is it required still? Just a question, ma'am.
Quota is not required. If you allow equality to be there in the society, no quota is required.
Good evening, ma'am. This is Banshika Panda from DPS, DePaul School. Feminism, by definition, is equality among women and men. But why feminism has become one of the unpopular word, and it is such a shame to be a feminist today.
It's such a shame to be
Why
a feminist.
Is it such a shame to be a feminist today?
No, it is never a shame. I feel proud to be a feminist. I always say, I feel proud. I am so proud of my feminism, feminist ideology. It's not a, it is never a shame.
Hello. Good evening, Miss. I am Prabhas Ranjan Patro from DPOL. First of all, thank you for such an amazing lecture. I would like to ask a question in Odia so that you can have a clear understanding. जेहेतु कि आम कॉन्स्टिट्यूशन बिंग आम एत बड़ डेमोक्रेटिक कंट्री एत बड़ लार्जेस्ट पॉपुलेशन थाई रेले आमे जो आमर जो कॉन्स्टिट्यूशन को अडॉप्ट करछु इंग्लैंड रु बहुत मेजर पोर्शन तारु ये आमे जेहेतु देखिले इंग्लैंड रे बहुत पावरफुल रूलर्स जो मानथिले से माने फीमेल थिले बट सेडा आमे अडॉप्ट करिया बावजूद तार मेजर पोर्शन अडॉप्ट करिया बावजूद आमर वुमेन्स राइट कोडा जो कॉन्स्टिट्यूशन रचे तार किछि इफेक्ट आमर सेति सिग्निफिकेंटली देखेनी जेहेतु कि आमर माइंडसेट चेंज हेनी कम्युनिटी रो सोसाइटल थिंकिंग चेंज हेनी ताले आमे सब वुमेन्स राइट ऐड करियार कोन वैल्यू रहला एंड ता अलावा आमे कोन सोसाइटल थिंकिंग चेंज करिया ऊपर कोन एफर्ट्स पके परियानी
एफर्ट समस्तଙ୍କ द्वारा हबो efforts cannot be taken up only by government. The most important effect can be spread by civil society. By civil society. And the young mass. Young mass. Jodi pratek school pila, college pila, jodi semane enlightened hebe, fight for equal rights, semane proclaim karibe, tahale sabu hobo.
Ma'am, my name is Anshweta and I am from PM Shri Kendriya Vidyalaya Barampur. My question is that in the North Indian Eastern countries and even in the North Indian states of India, there is no concept of patriarchy, and I have even heard that most of the boys after marriage goes to the girl's house, but girls don't goes to the boys' house, and even the dowry was provided from the boys' side. Why it is so?
Seti achi, some matriarchal societies are still there, but mostly northeastern is there. Northern is not there. Northern is completely patriarchal. Northeast, there are some matriarchal society. Mostly in Meghalaya. Meghalaya is they have a matriarchal society. Some parts of the country.
Okay. Thank you. Let's thank ma'am for an extremely good. I know we can spend another 1 hour asking questions. This is such a subject, but what she told you, really it has to start from the house. And she is 500% correct. You have not seen families like that. Most of the families, many of you don't know, are still very, very patriarchal. And if you go, there will be a big difference as you grow from district to big city and places. So you will see that many things you speak in Barampur, if you speak that in Bombay or Delhi, that girl will take you to court. Many things you speak openly in Barampur, you may say to someone, very simple thing, even about dress. In Delhi, Bombay or somewhere, you may be taken to court. So you have to know what to speak and what not to speak very, very clearly. There are lots of rights for women, but those rights many times the women don't use. And you should know what is allowed, what is not allowed. And many times they pass away, that is the girl's training. But if the girl comes from a very educated family, then you will have a very tough time. She will file a case and everything. So you have to know exactly what rights you have. You should not speak loosely. Lot of things we speak loosely, but all of them, she was saying violence. Actually, violence is not only beating, it is violation of somebody else's independence. And that you will come to know when you go to very educated places, how they will confront you for even very small thing, which many places you will just pass, that nothing has happened. But as you go to more educated society, say you are in Sweden, you are in Norway, there they are very, very tight what you can do, what you cannot do. So these you will learn as you will grow up, and you will meet many places. You go out of big cities, you will know exactly what to say, what not to say, and what is allowed, what is not allowed. You cannot demean people. You cannot talk on the basis of gender. That's what she gave an example. So all that you will learn, or if you do not learn in one way, you will learn the hard way when somebody takes it up, because laws are there. For everything, laws are there. As she said, laws in India are there much before in United States, even in pay parity and in United Kingdom. So thanks to Professor Gitanjali Das, we had an exciting lecture, but we now have to close this session. And thanks to all the speakers, Professor Anil Kumar and Professor Rajesh Prasad, because I was chairing this session with 3 speakers, outstanding lectures, and wonderful to have all of you here. I'm sorry some of the students could not ask. I'm sure you have a lot of questions, but I think all the girls should make it a point that you can become equal only when you have the freedom to go anywhere you want. You have to see that. Then only you will break the glass ceiling. You should see yourself as presidents in company, as directors, as vice chancellors. You should see yourself there. If you do not see today, you will never reach there. If you see today yourselves there, then one day you will reach. So what she said, out of 1100 universities, only 50 or 60 have women vice chancellors. Actually, no IIT, out of 23 IITs, there is any woman director. There is no ISER where there is a woman director right now. I don't know about IIM, but all the national institutes, IITs, ISERs, they do not have. But in NITs, there are women directors now. There are several NITs in India where they have women directors. So all of you should look forward who have ambitions. So you must have great ambitions in life and you can achieve it. There are lots of role models you can go. One is sitting in front of you. So let us give us a break. Quick.
So because we are running little late, so we are not having that dedicated interaction session today anymore. But we had very interesting questions already, and some few names have been selected who asked the best questions. So now I'll read those names, and if you hear your names, please come up to the stage, and our director sir and Professor Gitanjali Das will give you the book prizes. Okay. So the first name is Aishwarya Panigrahi from DAV Public School. The next one is Karthik Pradhan from KV Berampur. Shrihan Pradhan from DePaul School. Vidyashri Shahu from OAVS Karapalli. Prince Pradhan from Aryan Public School. And Naino Singh from APS Gopalpur. I announced 6 names. Okay. Okay, but I don't know your name. Can you tell me your name? Swarup Nayan Patnaik from which school? KV Barampur. So now we will have a group photo with everyone, So I request Professor Das and Professor Ganguly. Everybody, like this side. Saran ma'am, you have to come this side so that we have a group photo with everyone.
हेलो दयाकरी दुईटी लाइन रे स्नैक्स पाई जिबे स्टूडेंट माने प्लीज दुईटी लाइन रे जिबे एवं काली पाई गोटे इम्पोर्टेंट अनाउंसमेंट अच्छी जोटा कि जो मैंने ट्रांजिट कैंपस को आसुचंती से माने 7:30 सुधा पहुँचे एवं जो मैंने डायरेक्टली परमानेंट कैंपस आसुचंती से माने एठारे 8:30 सुधा पहुँचवा हेबे. One important announcement: those who are coming to the transit campus, please reach to the campus by 7:30 a.m. and those who are coming to the permanent campus, they should